Centralized resources are a game changer. Imagine having all your data, applications, and resources managed in one place. It's like having a well-organized toolbox where everything you need is right at your fingertips. This setup not only simplifies access, but also enhances collaboration, making it easy for teams to share information seamlessly. Now, let's talk security. With servers, you can implement strict security protocols that ensure only authorized clients can access sensitive data. It's like having a high-tech lock on your digital vault, keeping your information safe from prying eyes. And scalability? That's where servers truly shine. They can effortlessly handle multiple clients at once, allowing your operations to grow without a hitch. As your business expands, your server infrastructure can adapt, ensuring you're always ready for the next challenge. Centralized resources, robust security, and seamless scalability. This is the future of efficient operations. In the world of computing, we often find ourselves navigating two distinct architectures, client-server and peer-to-peer. Picture the client-server model as a bustling restaurant. The server, a powerful entity, manages resources and dishes out services, while the clients, your devices, place their orders, waiting for that delicious data to arrive. This setup is the backbone of our daily digital experiences, from browsing web to sending emails. Now, shift your perspective to peer-to-peer, or P2P. Here, every device is both a client and a server, like a potluck dinner where everyone brings a dish to share. Each peer connects directly with others, sharing resources without a central authority. This decentralized approach fosters collaboration and efficiency, making it perfect for file sharing and online gaming. In essence, while client-server architecture centralizes power and resources, peer-to-peer democratizes them, allowing for a more interconnected and resourceful digital landscape. Both have their strengths, shaping how we interact with technology every day. When we talk about network operating systems, Microsoft Windows Server stands out as a powerhouse, providing essential network services, file sharing, and centralized management that businesses rely on. Then we have Unix and Linux-based systems, which, with the right networking software like Samba or NFS, can transform into robust NOS solutions, offering flexibility and control. Remember Novell NetWare? It was the king of the 90s, delivering reliable file and print services across networks, making it a staple in many organizations. And let's not forget macOS Server, designed specifically for managing network resources for macOS clients, ensuring seamless integration and efficiency. Each of these systems plays a unique role in the networking landscape, catering to diverse needs and preferences. When we talk about network operating systems, Microsoft Windows Server stands out as a powerhouse, providing essential network services, file sharing, and centralized management that businesses rely on. Client-server architecture is like a dynamic duo in the world of computing. Imagine a bustling restaurant. The server takes orders and delivers food, while clients, best diners, enjoy the meal. In this model, clients are devices like your smartphone or phone or laptop, sending requests for data or services. The server, on the other hand, is a powerhouse that processes these requests, manages resources, and delivers the needed information back to the clients. This architecture is built on a few key components. First, we have the client, which initiates requests. Then there's the server, equipped with necessary software and hardware to handle those requests. Communication happens over a network, often using protocols like HTTP or FTP, ensuring smooth interaction. Scalability is another highlight. As demand grows, servers can be upgraded or more can be added, keeping everything running efficiently. This model not only enhances performance, but also promotes resource sharing, making it a cornerstone of modern networking and distributed systems. It's a brilliant way to keep everything organized and responsive in our digital world. Imagine a powerful machine, tirelessly working behind the scenes, ready to serve your every digital need. That's a server for you. It's not just a computer, it's a dedicated system that provides services, resources, or data to clients like you. When you click on a website, your request zips off to a web server, which then fetches the web page and sends it back to your screen. But servers do more than just serve web pages. Think about file servers. They store your documents, photos, and videos, making them accessible whenever you need them. And then there are database servers, the unsung heroes that manage vast amounts of data, ensuring everything is organized and retrievable at lightning speed. So the next time you browse the internet, remember the silent workhorses behind all, tirelessly handling requests and delivering information right to your fingertips. Servers are the backbone of our digital world, making everything possible with just a click. Imagine a powerful machine tirelessly working behind the scenes, ready to serve your every digital need. That's a server for you. Imagine a world where every time you click a button, a silent conversation begins between your device and a server. This is the request-response model in action. You send a request, maybe for your favorite cat video or the latest news, and the server, like a diligent librarian, processes that request and sends back the information you need. But it doesn't stop there. Servers are like busy hubs, juggling multiple requests simultaneously, ensuring everything runs smoothly. This centralized management simplifies tasks like data administration and security, making it easier to keep everything in check. Communication happens over networks using standard protocols. Think HTTP for web pages, FTP for file transfers, or SMTP for emails. Each protocol is a unique language, ensuring that clients and servers understand each other perfectly. It's a seamless dance of data, all happening in the blink of an eye. In the world of networking, the Network Operating System, or NOS, plays a crucial role in file sharing. Imagine accessing files from any machine on the network as if they were right on your desktop. It's seamless. Then there's print services, which manage print queues, allowing multiple users to share networked printers effortlessly. No more waiting in line for your documents. Centralized data storage is another game changer. It simplifies data management, making backups and access control a breeze across all devices. And let's not forget about networking protocol support. NOS supports essential protocols like TCP/IP, DNS, and DHCP, ensuring smooth communication between devices. This integration not only enhances efficiency, but also strengthens collaboration across the network. It's all about making our digital lives easier and more connected. In the world of networking, the Network Operating System, or NOS, plays a crucial role in file sharing. Imagine accessing files from any machine on the network as if they were right on your desktop. It's seamless. When it comes to Windows Server, Microsoft has tailored editions to meet diverse business needs. For small businesses, there's Windows Server Essentials, perfect for networks with fewer than 25 users and 50 devices, simple and efficient. Then we have Windows Server Standard, designed for smaller to medium-sized businesses, supporting core services and allowing up to 2 virtual machines. If you're in a large organization with advanced virtualization needs, Windows Server Data Center is your go-to, offering unlimited virtual machine licenses and exceptional scalability. And for those focused on web hosting, Windows Server Web is a streamlined version optimized for performance. Each edition is crafted to empower businesses no matter their size or requirements. When it comes to Windows Server, Microsoft tailored editions to meet diverse business needs. For small businesses, there's Windows Server Essentials, perfect for networks with fewer than 25 users and 50 devices, simple and efficient. Then we have Windows Server Standard, designed for smaller to medium-sized businesses, supporting core services and allowing up to 2 virtual machines. Windows Server is the backbone of enterprise IT, serving multiple critical roles. As a domain controller, it runs Active Directory domain services, ensuring centralized authentication and authorization for users and computers, streamlining access across the network. It also shines as a file server, offering shared storage that makes collaboration seamless. Need email services? With Microsoft Exchange Server, it delivers robust email, calendaring, and task management capabilities. For web hosting, powered by IIS is a go-to for hosting websites and applications. It also excels as an application server, supporting enterprise applications like SQL Server and ERP systems. Plus, with Hyper-V, it transforms into a virtualization host, managing multiple virtual machines and optimizing resource use. Windows Server truly is a versatile powerhouse in the IT landscape. Windows Server 2003 marked a pivotal moment in server technology, introducing Active Directory and Internet Information Services, setting the stage for future innovations. Fast forward to 2008 and 2008 R2, where Hyper-V emerged, revolutionizing virtualization for enterprises. Then came 2012 and 2012 R2, which took virtualization to new heights with enhanced cloud integration and storage solutions. By 2016, we saw the introduction of nanoserver containers, pushing the boundaries of security and efficiency. Windows Server 2019 continued this trend, emphasizing hybrid cloud capabilities and containerization improvements. Now, with Windows Server 2022, we're witnessing a focus on robust security features and better support for hybrid environments, cementing its role in modern IT infrastructure. Each version builds on the last, shaping the future of server management. A computer network is a system of interconnected computers and other devices that can share data, resources, and communicate with each other. The devices in a network are connected by physical cables, wireless connections, or both. allowing them to send and receive data over various communication channels. There are different types of computer networks based on their size and purpose. LAN, local area network, is a small network, typically confined to a single building or campus, used to connect devices like computers, printers, and servers. WWAN, wide area network, is a large network that spans a wide geographic area, such as a country or even globally, connecting multiple LANs. MAN, metropolitan area network, is a network that covers a city or a large campus, larger than a LAN, but smaller than a WAN. PAN, personal area network, is a small network used for connecting personal devices, typically within the range of a few meters, like Bluetooth connections. VPN, virtual private network, is a secure private network established over a public network, enabling encrypted communication. A computer network is a system of interconnected computers and other devices that can share data, resources, and communicate with each other. The devices in a network are connected by physical cables, wireless connections, or both, allowing them to send and receive data over various communication channels. In the world of computer networks, the terms hosts and nodes often pop up, and while they might sound similar, they have distinct meanings. A host is any device connected to a network that has an IP address, allowing it to send and receive data. Think of hosts as the active participants in the network party. They can be anything from your desktop computer or laptop to servers, smartphones, and even printers. Each host is assigned a unique IP address, making it easy to identify and communicate with other devices. For instance, when you send an email or browse a website, your device is acting as a host, reaching out to other hosts like servers to exchange information. And let's not forget about IoT devices. These smart gadgets are hosts too, connecting and sharing data seamlessly. So, the next time you connect to the internet, remember, you're part of a vast network of hosts, each playing a crucial role in the digital landscape. A node is essentially any device or point in a network that can send, receive, or forward data. Think of it as a connection point in the vast web of communication. While we often think of hosts, like our computers, smartphones, and servers, as nodes, it's important to remember that not all nodes are hosts. Networking devices like routers, switches, hubs, and gateways also play a crucial role. They manage and direct the flow of data, ensuring that information reaches its destination efficiently. Even intermediate devices that help with data routing and transmission count as nodes. So every time you send a message or stream a video, remember that a whole network of nodes is working behind the scenes to make it happen. A node is essentially any device or point in a network that can send, receive, or forward data. Hosts are always nodes, but nodes are not always hosts. A host is a device capable of directly communicating on the network and usually has an IP address. A node can be any device connected to the network, including networking equipment like routers and switches, which facilitate communication, but don't directly send or receive data in the same way that a host does. A host is typically a device that interacts with users or provides services, like a web server. A node can be any point in the network, not necessarily involved in user interaction, but vital for data transmission or routing, such as a router. To summarize, host equals a device that communicates with other devices or the network, like computers and smartphones. Node equals any device or point in a network, including hosts and networking devices like routers or switches. Hosts are always nodes, but nodes are not always hosts. A host is a device capable of directly communicating on the network and usually has an IP address. Network architecture refers to the design and structure of a computer network, including how different components, devices, connections, protocols, and services are organized and interact. There are several types of network architectures, each with different characteristics and use cases. Some common types of network architecture include: network architecture refers to the design and structure of a computer network, including how different components like devices, connections, protocols, and services are organized and interact. In this architecture, devices are divided into two categories: clients and servers. Clients are devices that request services or resources from the server, such as computers and smartphones. Servers are centralized devices that provide services or resources, like web servers and file servers. Servers are more powerful and manage resources. Clients send requests, and servers respond with data or services. An example of this is a company's internal file sharing system, where employees, acting as clients, access files stored on a server. In this architecture, devices are divided into two categories: clients and servers. Clients are devices that request services or resources from the server, such as computers and smartphones. Servers are centralized devices that provide services or resources, like web servers and file servers. In a P2P network, every device can act as a client and a server. Each peer can share resources with other peers without needing a central server. It has a decentralized structure where devices communicate directly with each other, making it suitable for smaller networks or when centralized control is unnecessary. An example of this is file sharing systems like BitTorrent. The advantages include less dependency on a single point of failure, since there is no central server, and is often used for small networks or home setups. However, security and performance may be harder to manage. In a P2P network, every device can act as both a client and a server. Each peer can share resources with other peers without needing a central server. This architecture combines both client-server and P2P models, offering a balance between central control and decentralized communication. Some devices act as servers, while others can communicate directly. It allows for a combination of centralized and decentralized features. An example of this is some modern file sharing services, where there's a server for managing user data and peer-to-peer communication for sharing files. The advantages include flexibility and efficiency, while the disadvantages are that it can be complex to manage and configure. This architecture combines both client-server and P2P models, offering a balance between central control and decentralized communication. Some devices act as servers, while others can communicate directly. It allows for a combination of centralized and decentralized features. In a centralized network, all devices or nodes communicate through a central hub or server. The central device manages and controls all communications. The central hub holds control over resources and data, and other devices are dependent on the central server for access to network resources. An example of this is traditional LANs, where users access data or services from a single server. The advantages of a centralized architecture include easier management and security, as centralized control simplifies network administration. However, a significant disadvantage is that if the central server fails, the entire network can be affected. In a centralized network, all devices or nodes communicate through a central hub or server. The central device manages and controls all communications. The central hub holds control over resources and data, and other devices are dependent on the central server for access to network resources. A decentralized network lacks a central control point. Devices or nodes can communicate with each other and distribute data or resources without the need for a single central server. Nodes share control and responsibility for resources and communication. Each device can function independently or with minimal reliance on others. Examples include some blockchain networks or mesh networks. The advantages of a decentralized architecture include increased reliability and fault tolerance, as there's no central point of failure. However, it can be more complex to manage and may lack the centralized control needed for large networks. A decentralized network lacks a central control point. Devices or nodes can communicate with each other and distribute data or resources without the need for a single central server. In ring topology, devices are connected in a circular manner, with each device connecting to two others. Data travels in a unidirectional or bidirectional manner along the ring. Data moves in one direction or can move in both directions around the ring. Each device is connected to two others, forming a closed loop. An example of this is token ring networks, which were historically used in office environments. The advantages of ring architecture include being more efficient for small networks and having a simple design.
However, a disadvantage is that failure in one device or connection can break the entire network. In ring topology, devices are connected in a circular manner, with each device connecting to two others. Data travels in a unidirectional or bidirectional manner along the ring.
In a bus topology, all devices are connected to a single central cable called the bus. Devices send data over the bus, and all other devices can access it. All devices are connected to a single shared medium, the bus. Data is transmitted along the bus and received by all devices, but only the intended recipient processes it. An example of this is older Ethernet networks using coaxial cables. The advantages of this topology include being simple and cost-effective for small networks. However, there are disadvantages, such as performance issues with too many devices, and the fact that if the bus cable fails, the entire network can go down. In a mesh network, each device or node is connected to every other device in the network. This offers multiple paths for data transmission. Mesh networks are highly reliable, as data can take multiple routes. They are used for large networks where redundancy and fault tolerance are essential. A common example is wireless mesh networks used in large-scale deployments like citywide internet access or industrial networks. The advantages of mesh networks include their reliability and fault tolerance, as there's no single point of failure, and high performance due to multiple communication paths. However, they can be expensive to set up and maintain because of the large number of connections, and they can become complex in large-scale implementations. In a mesh network, each device or node is connected to every other device in the network. This offers multiple paths for data transmission. In star topology, all devices are connected to a central device, usually a switch or hub. Communication between devices happens via the central point. The central hub acts as the mediator for communication between devices. Each device connects directly to the hub, and the hub forwards data to the appropriate destination. A common example is modern Ethernet networks with a central switch. The advantages of this topology include ease of installation and management, and the fact that the failure of a device doesn't affect the entire network, only that device is impacted. However, there are disadvantages as well. The hub or switch represents a single point of failure, meaning if it fails, the entire network may go down. Architecture in networking is fascinating and diverse. Let's dive into some key types. First, the client-server model, where a centralized server provides services to clients. Think web hosting and email systems. Then there's peer-to-peer, where devices act as both clients and servers, perfect for file sharing and small home networks. Hybrid systems blend these approaches, like cloud storage that uses P2P for backups. Centralized networks rely on a single device to control everything, common in small businesses. In contrast, decentralized networks, like blockchain, distribute responsibility across all devices, enhancing security and resilience. Next, we have the ring architecture, where devices connect a circular pattern reminiscent of the old token ring networks. The bus topology features all devices sharing a single central bus, typical in legacy Ethernet systems. Finally, the mesh architecture connects every device to one another, ideal for large-scale, high-reliability networks. And let's not forget the star topology, where a central hub connects all devices, a staple in modern Ethernet and Wi-Fi networks. Each architecture has its unique strengths, shaping how we connect and communicate today. RFC 791 is a cornerstone of the Internet, defining IPv4, which has been our digital address system since September 1981. Imagine a world where every device needs a unique identifier to communicate. That's where IPv4 comes in, using 32-bit numbers to create addresses. These addresses are cleverly formatted in what we call dotted decimal notation. Picture this: 4 groups of numbers, each ranging from 0 to 255, separated by dots. So, an address might look like 192.168.1.1. Each segment represents 8 bits, making it easy for us to read and understand. This structure not only helps devices find each other, but also plays a crucial role in routing data across the vast expanse of the Internet. Without RFC 791, our online world would be a chaotic mess, proving just how vital this standard is to our connected lives. RFC 791 is a cornerstone of the Internet, defining IPv4, which has been our digital address system since September 1981. Imagine a world where every device needs a unique identifier to communicate. IPv4 addresses are fascinating. They're divided into classes based on their range, each serving a unique purpose. Class A spans from 0.0.0.0 to 127.255 or 2555.255, designed for large networks. Think of it as the VIP section of the Internet. Then we have Class B, ranging from 128.0.0.0 to 191.255.255.255, perfect for medium-sized networks, like a bustling office. Class C, from 192.0.0.0 to 223.255.255.255, caters to small networks, ideal for home users. Class D, on the other hand, is all about multicast addresses, ranging from 224.0.0.0 to 239.255.255.255, allowing efficient data distribution to multiple recipients. Finally, Class E, from 240.0.0.0 to 255.255.255, is reserved for future use. Who knows what innovations await? Each class plays a vital role in how we connect and communicate online, making the Internet a truly dynamic space. IPv4 addresses are fascinating. They're divided into classes based on their range, each serving a unique purpose. Class A spans from 0.0.0.0 to 127.255.255.255, designed for large networks. Think of it as the VIP section of the Internet. An IPv4 address is like a digital address for your devices, split into 2 essential parts: the network address and the host address. The network address pinpoints the specific network, while the host address identifies the individual device within that network. The magic of this division lies in the subnet mask. Take Class A, for instance, with default subnet mask of 255.0.0.0. Here, the first 8 bits are dedicated to the network, leaving the rest for hosts. Now, shift to Class B, which uses a subnet mask of 255.255.0.0, where the first 16 bits represent the network. This structure ensures efficient communication and organization within networks, making it easier for devices to find each other in the vast digital landscape. Understanding this division is crucial for anyone diving into networking. Broadcast addresses are fascinating. They allow us to send data to every device on a network simultaneously. For instance, 255.255.255.255, the universal broadcast address local networks. And there's the loopback address, ranging from 127.0.0.0 to 127.255.255.255, which is like a personal hotline for your device. When you ping 127.0.0.1, you're essentially talking to yourself. Now let's talk about private addresses. These are special ranges reserved for internal use, keeping our local network safe from the chaos of the public Internet. Class A starts with 10.0.0.0 to 10.255.255.255, perfect for large organizations. Class B covers 172.16.0.0 to 172.31.255.255, striking a balance for medium-sized networks. And Class C, the most common, runs from 192.168.0.0 to 192.168.255.255, often found in home routers. Understanding these addresses is key to navigating the digital world. Fragmentation in IPv4 is like a clever puzzle solver, breaking down larger packets into smaller pieces to fit through various network pathways with different maximum transmission unit sizes. This ensures that data travels smoothly, no matter the obstacles. Now let's talk about checksums. Each IPv4 packet carries a checksum field, acting as a vigilant watchdog. It scans the packet header for errors during transmission. If it finds any discrepancies, the packet is tossed aside, ensuring only the most accurate data gets through. Finally, we have routing, the backbone of network communication. Routers utilize routing tables, analyzing the network portion of IP addresses to make split-second decisions on where to send packets next. This dynamic process keeps our data flowing efficiently across the vast web of interconnected devices. Fragmentation, checksums, and routing. These are the unsung heroes of IPv4, working tirelessly behind the scenes to keep our digital world connected. An IPv4 packet consists of 2 main parts: the header, which contains metadata and routing information, such as source and destination IP addresses, protocol type, etc., and the data, which is the actual payload or message being sent. The IPv4 header contains the following key fields: version, which specifies the version of the IP protocol, and for IPv4, this value is 4. IHL, or internet header length, which specifies length of the header. Type of service, which describes the priority of the packet. Total length, which indicates the total length of the packet, including both header and data. Identification, which is used for packet fragmentation. Flags, which are used to control or identify fragments. Fragment offset, which indicates the position of the fragment in the original data. Time to live, which limits lifespan of the packet to prevent infinite loops. Protocol, which indicates the protocol used in the data portion, such as TCP or UDP. Header checksum, which is an error checking field for the header. Source IP address, which is the sender's IP address. And destination IP address, which is the recipient's IP address. An IPv4 packet consists of two main parts: the header, which contains metadata and routing information, such as source and destination IP addresses, protocol type, etc., and the data, which is the actual payload or messaging sent. The IPv4 header contains the following key fields: version, which specifies the version of the IP protocol, and for IPv4, this value is 4. IHL, or internet header length, which specifies the length of the header. Type of service, which describes the priority of the packet. Total length, which indicates the total length of the packet, including both header and data. Identification, which is used for packet fragmentation. Flags, which are used to control or identify fragments. Fragment offset, which indicates the position of the fragment in the original data. IPv addresses are fascinating 32-bit identifiers that play a crucial role in connecting on a network. Imagine them as unique postal addresses for your devices, divided into two parts: the network portion, which tells us where to send the data, and the host portion identifying the specific device. Depending on the size of the network, we use different classes of addresses, ensuring efficient organization. What's really interesting is how IPv4 allows for fragmentation, breaking down data into smaller packets for easier transmission. Plus, it incorporates checksums for error detection, ensuring that the data arrives intact. This structure is the backbone of most networks, enabling seamless communication and efficient routing. Without IPv4, the digital world as we know it would simply function. IPv4 addresses are fascinating 32-bit identifiers that play a crucial role in connecting devices on a network. Imagine them as unique postal addresses for your devices, divided into two parts: the network portion, which tells us where to send the data, and the host portion, find the specific device. An IPv4 packet consists of two main parts: the header, which contains metadata and routing information, such as source and destination IP addresses, protocol type, etc., and data, which is the actual payload or message being sent. The IPv4 header contains the following key fields: version, which is 4 bits and specifies the version of the IP protocol, with a value of 4 for IPv4. IHL, or internet header length, which is 4 bits and specifies the length of the header. Type of service, or TOS, which is 8 bits and describes the priority of the packet. Total length, which is 16 bits and indicates the total length of the packet, including both header and data. Identification, which is 16 bits and is used for packet fragmentation. Flags, which are 3 bits and are used to control or identify fragments. Fragment offset, which is 13 bits and indicates the position of the fragment in the original data. Time to live, or TTL, which is 8 bits and limits the lifespan of the packet to prevent infinite loops. Protocol, which is 8 bits and indicates the protocol used in the data portion, such as TCP or UDP. Header checksum, which is 16 bits and serves as an error checking field for the header. Source IP address, which is 32 bits and represents the sender's IP address. And destination IP address, which is also 32 bits and represents the recipient's IP address. The IPv4 header contains the following key fields: version, which is 4 bits and specifies the version of the IP protocol, with a value of 4 for IPv4. IHL, or internet header length, which is 4 bits and specifies the length of the header. Type of service, or TOS, which is 8 bits and describes the priority of the packet. Total length, which is 16 bits and indicates the total length of the packet, including both header and data. Identification, which is 16 bits and is used for packet fragmentation. Flags, which are 3 bits and are used to control or identify fragments. Fragment offset, which is 13 bits and indicates the position of the fragment in the original data. Time to live, or TTL, which is 8 bits and limits the lifespan of the packet to prevent infinite loops. Protocol, which is 8 bits and indicates the protocol used in the data portion, such as TCP or UDP. Header checksum, which is 16 bits and serves as an error checking field for the header. Source IP address, which is 32 bits and represents the sent IP address. And destination IP address, which is also 32 bits and represents the recipient's IP address. The IPv4 header contains the following key fields: version, which is 4 bits and specifies the version of the IP protocol, with value of 4 for IPv4. IHL, or internet header length, which is 4 bits and specifies the length of the header. Type of service, or TOS, which is 8 bits and describes the priority of the packet. Total length, which is 16 bits and indicates the total length of the packet, including both header and data. Identification, which is 16 bits and is used for packet fragmentation. Flags, which are 3 bits and are used to control or identify fragments. Fragment offset, which is 13 bits and indicates the position of the fragment in the original data. Time to live, TTL, which is 8 bits and limits the lifespan of the packet to prevent infinite loops. Protocol, which is 8 bits and indicates the protocol used in the data portion, such as TCP or UDP. Header checksum, which is 16 bits and serves as an error checking field for the header. source IP address, which is 32 bits and represents the sender's IP address, and destination IP address, which is also 32 bits and represents the recipient's IP address. The terms 32-bit and 64-bit are crucial when we talk about CPU architecture. They define how a processor handles data and memory. A 32-bit processor can manage 232 memory addresses, which equals about 4 gigabytes of RAM. That might sound like a lot, but in today's world, it's quite limiting. On the other hand, a 64-bit processor can address 264 memory locations, translating to a staggering 16 exabytes of RAM. This means it can handle much larger datasets and run more applications simultaneously without breaking a sweat. Additionally, the width of the data bus and the size of the registers play a significant role in performance. A 64-bit CPU can process more data at once, leading to faster computations and improved efficiency. So, whether you're gaming, video editing, or running complex simulations, the architecture of your CPU can make a world of difference. Understanding these terms helps you make informed choices about your hardware and software needs. When we talk about data width, we're diving into the heart of how processors work. A 32-bit CPU processes 32 bits of data in a single clock cycle. Imagine it as a narrow highway, where only a limited number of cars can pass at once. This means it can handle 4 gigabytes of RAM at most, which might seem sufficient for basic tasks, but it can struggle with more demanding applications. Now shift gears to a 64-bit CPU. This powerhouse processes 64 bits of data in one cycle, doubling the data width. Picture a wide highway, allowing for more cars to zoom by simultaneously. This capability not only enhances performance, but also supports a staggering 16 exabytes of RAM. That's a game changer for heavy multitasking, gaming, and professional applications. In essence, the difference in data width isn't just numbers. It's about efficiency and power in computing. The leap from 32-bit to 64-bit is like upgrading from a compact car to a high-speed sports car. Speed, capacity, and performance all take a giant leap forward. Memory addressing is a fascinating topic that highlights the evolution of computing power. With a 32-bit CPU, we're limited to addressing just 4 gigabytes of RAM, about 4.3 billion bytes. That might sound like a lot, but for high-end applications, large databases, or even modern gaming, it can feel like a chokehold. Imagine trying to run a complex simulation or a massive game with that constraint. It's like trying to fit a whale in a bathtub. Now, enter the 64-bit CPU, a game changer in the tech world. It can theoretically address up to 16 exabytes of RAM. Yes, that's 16 billion gigabytes. While most systems today don't even come close to utilizing that capacity, the ability to support far more than 4 GB is crucial for modern applications. It opens the door for smoother multitasking, faster processing, and the ability to handle massive data sets without breaking a sweat. So, whether you're a gamer, a developer, or just someone who loves tech, the leap from 32-bit to 64-bit is a monumental shift that shapes our digital experiences every day. When it comes to software compatibility, the difference between 32-bit and 64-bit CPUs is crucial. A 30-bit CPU is limited to running only 32-bit software. It's like trying to fit a square peg in a round hole. No matter how hard you try, it just won't work. Now, if you have a 64-bit CPU with a 32-bit operating system, you can still run that 32-bit software, but you're not tapping into the full power of your processor. On the flip side, a 64-bit CPU is a powerhouse. It can handle both 32-bit and 64-bit software. But to truly unleash its potential, you need to run 64-bit applications. Why? Because 64-bit software can utilize wider registers and access more memory, which translates to better performance and efficiency. So, if you're looking to maximize your computing experience, embracing 64-bit software is the way to go. It's all about getting the most out of your hardware. When it comes to software compatibility, the difference between 32-bit and 64-bit CPUs is crucial. A 32-bit CPU is limited to running only 32-bit software. It's like trying to fit a square peg in a round hole. No matter how hard you try, it just won't work. When we talk about CPUs, the size of their registers plays a crucial role in performance. A 32-bit CPU, for instance, has registers that can hold only 32 bits of data. This limitation means it struggles with large numbers and complex calculations, making it less efficient for modern applications. Now, shift your focus to a 64-bit CPU. With registers that can handle 64 bits, it opens up a whole new world of possibilities. These larger registers can manage bigger values and process more data simultaneously, allowing for faster computations and smoother multitasking. This leap in architecture not only enhances performance, but also enables more sophisticated software to run seamlessly. In the race of technology, the shift from 32-bit to 64-bit is a game changer, paving the way for innovation and efficiency in computing. Operating systems are like the backbone of our computers, and understanding the difference between 32-bit and 64-bit can really enhance your tech experience. A 32-bit operating system is limited to running only 32-bit applications and can access a maximum of 4 GB RAM. That's it. So if you're running resource-intensive software, you might hit a wall pretty quickly. On the flip side, a 64-bit operating system is a game changer. It can run both 32-bit and 64-bit applications, which means more flexibility for you. Plus, it can address significantly more RAM, typically 8 GB, 16 GB, or even more, depending on the OS version. This allows for smoother multitasking and better performance overall.
Modern operating systems like Windows, Mac OS, and Linux come in both flavors, so choosing the right one can make a huge difference in how your system performs. So, whether you're gaming, editing videos, or just browsing, going 64-bit is usually the way to go for a seamless experience.
When I think of the evolution of CPUs, it's fascinating to see how far we've come. The 32-bit era, with processors like the Intel Pentium 4 and AMD Athlon XP, was groundbreaking for its time. These chips powered everything from early gaming to basic computing tasks, but they had their limits, especially when it came to multitasking and handling large applications. Fast forward to the modern 64-bit CPUs, and we're in a whole new league. Take the Intel Core i5, i7, and i9 series, for example. They not only handle more data at once, but also support advanced features, like hyper-threading, making them perfect for gaming and content creation. Then there's the AMD Ryzen series, which has redefined performance with its multi-core architecture, giving users incredible speed and efficiency. And let's not forget Apple's M1 and M2 chips, which have set new standards for power efficiency and performance in laptops. These processors are not just fast, they integrate seamlessly with the software, providing a smooth user experience. The leap from 32-bit to 64-bit is not just about numbers, it's about transforming how we interact with technology every day. When it comes to computing, the leap from 32-bit to 64-bit is a game changer. First off, let's talk memory. With 64-bit systems, you can access more than 4 GB of RAM. This is a game changer for gamers, video editors, and anyone running demanding applications. Imagine editing a high-resolution video without lag. Sounds great, right? Then there's performance. 64-bit processors can handle larger chunks of data at once, meaning they can process more information in parallel. This translates to faster load times and smoother multitasking. And let's not forget security. 64-bit CPUs come with enhanced security features like hardware-based data protection and advanced encryption algorithms. This means your data is safer from threats. In a nutshell, 64-bit technology is not just about numbers, it's about unlocking the full potential of your computing experience. The CPU is the brain of the computer. It performs all the instructions from programs by executing basic arithmetic, logic, control, and input-output operations. It processes data and manages tasks, coordinating with other components in the computer. The speed and performance of a CPU are measured in GHz. RAM is a type of volatile memory used to store data that is actively being used or processed by the CPU. It provides quick access to data for running programs and the operating system. RAM is temporary storage, meaning the data is lost when the computer is turned off. A hard disk is the primary long-term storage device in a computer where data, applications, and the operating system are stored. HDD uses spinning disks to read out-write data, while SSD uses flash memory for faster performance and no moving parts. SSDs are faster and more durable than HDDs, but tend to be more expensive. Each of these components plays a crucial role in the overall performance and functionality of a computer. Blade servers and tower servers are two types of server designs, and they differ in their physical form, scalability, and use cases. Blade servers are slim, modular servers that are mounted in a central chassis. Each blade is essentially a server without its own power supply, cooling system, or individual case. These components are managed by chassis. Blade servers are designed to maximize space. A single chassis can house multiple server blades, allowing organizations to pack a lot of processing power into a smaller physical space. They are highly scalable, as additional blades can be added to the chassis as needed. This is ideal for businesses that require high-density server environments. Blade servers are often used in data centers or enterprise environments where space, power, and cooling need to be optimized. They are ideal for applications requiring significant compute power and central management. On the other hand, tower servers are standalone servers that resemble desktop PCs in shape and size. They have their own individual case, power supply, and cooling system. Tower servers take up more physical space compared to blade servers because each server is independent. However, they can still be placed in a rack if needed, as rack-mountable versions exist. While they can be upgraded with additional components like RAM or hard drives, they are less scalable than blade servers. Each server is standalone, so you'd need additional physical space for more servers. Tower servers are ideal for small to medium-sized businesses or remote offices where space constraints are less of an issue and a simple server solution is needed. They are also useful for non-enterprise environments where ease of setup and maintenance is important. In summary, blade servers are compact, modular, scalable, efficient, but more expensive and suited for large-scale data centers. Tower servers are standalone, simpler, less expensive, but less scalable and efficient for large operations. They are ideal for small businesses or remote locations. Which one to choose depends on the scale of your operations, the physical space you have, and your needs. Windows Server has undergone a remarkable evolution over the years, adapting to the dynamic needs of enterprise environments. Starting with Windows NT Server 3.1 in 1993, we saw the introduction of a 2-bit architecture and multi-user capability, setting the stage for future innovations. Fast forward to Windows 2000 Server, which revolutionized networking with Active Directory, a game changer for user and resource management. The 2003 era brought us Windows Server 2003, enhancing security and introducing the .NET framework. Then came the virtualization era with Windows Server 2008, where Hyper-V transformed server management, allowing for efficient virtualization. Windows Server 2012 took this further, emphasizing cloud computing and virtualization with its modern UI. Moved into the cloud and hybrid era, Windows Server 2016 introduced nano Windows containers, aligning with the growing trend of containerized applications. Windows Server 2019 continued this trajectory, enhancing hybrid cloud capabilities and Kubernetes support. Now, with Windows Server 2022, the focus is on cybersecurity and seamless integration with Microsoft Azure, ensuring performance and scalability for containers and virtual machines. Each version reflects the increasing demand for cloud readiness, security, and scalability in modern IT infrastructures. Windows Server 2025, released on November 1st, 2024, introduces several enhancements aimed at improving security, performance, and flexibility. Key features include advanced security measures with Credential Guard now enabled by default on devices that meet the requirements, enhancing protection against credential theft. The operating integrates more efficiently with NVMe technology, enabling significantly improved IOPS. Windows Server 2025 offers enhanced virtualization support, providing a more efficient and scalable environment for organizations that need to handle complex workloads. Additionally, the server strengthens its support for containers and Kubernetes, enabling IT administrators to efficiently deploy modern applications. Windows Server 2025 is available in several editions to cater to different organizational needs. The Standard Edition is ideal for physical or minimally virtualized environments. The Data Center Edition is designed for highly virtualized data center environments. The Essentials Edition is targeted at small businesses with up to 25 users and 50 devices. Finally, the Azure Edition is optimized for hybrid cloud environments, offering seamless integration with Microsoft Azure services. Each edition is tailored to meet specific requirements, ensuring organizations can choose the version that best fits their infrastructure and operational needs. While Windows Server 2025 does several new features and improvements over Windows Server 2022, differences are primarily related to advancements in security, virtualization, cloud integration, and performance. Here's a breakdown of the key differences between the two. Windows Server 2025 has Credential Guard enabled by default, providing robust protection against credential attacks. It features security with Secured Core Server, which includes more hardened security, improved firmware, and boot security. Additionally, Windows Defender antivirus and ATP features are enhanced, offering more proactive detection and automated threat response. In contrast, Windows Server 2022 introduced Secured Core Server to protect hardware-level attacks, with a focus on securing the boot process. It supports TLS 1.3 for improved secure communication and has enhanced Windows Defender for real-time security improvements, but it is not as advanced as in 2025. When it comes to cloud integration, Windows Server 2025 offers more advancement with Microsoft Azure and hybrid cloud environments. It introduces Azure Edition, optimized cloud-first strategies, providing seamless integration for hybrid cloud workloads. Improved cloud management tools like APC and Azure Stack HCI make it easier to manage both on-premises and cloud-based systems. In terms of storage improvements, Windows Server 2025 enhances support for NVMe storage technologies, delivering faster storage performance. It also features improvements in Storage Spaces Direct for more efficient management of storage, virtualized environment, and an enhanced storage migration service for better handling of large data migrations. Windows Server 2022 introduced Storage Spaces Direct, but it has fewer optimizations for newer hardware like NVMe. While it offers replica and storage services, they lack the advanced improvements seen in Windows Server 2025. For virtualization and containers, Windows Server 2025 includes further advancements in Hyper-V for high-performance virtualized environments and strengthened support for Windows containers and Kubernetes, making it easy to deploy and manage modern applications in hybrid cloud environments. It also introduces new container features to improve DevOps and CI/CD workflows in Kubernetes-based environments. In contrast, Windows Server 2022 has Hyper-V improvements for better scalability and performance, but it focuses less on hybrid cloud containerized workloads. Windows container support is available, but Kubernetes integration is more basic compared to Windows Server 2025. Regarding performance and scalability, Windows Server 2020 is designed for higher speed in large data centers, supporting more CPU cores and memory. It offers better multi-cloud and hybrid cloud configurations, enabling businesses to run workloads more effectively across different platforms. Enhanced performance on high-end hardware and more efficient resource management in cloud environments are also features. Windows Server 2022 is less optimized for cloud-first deployments and focuses more on performance for on-premises and edge environments rather than hybrid cloud. In terms of user experience and management tools, Windows Server 2025 improves the Windows Admin Center experience, better central management for hybrid environments. It also provides more PowerShell scripting and automation capabilities tailored for modern, containerized, and cloud workloads. Windows Server 2022 has enhanced Admin Center and PowerShell support, but it is integrated with cloud-based tools and focuses more on on-premises management with some hybrid cloud capabilities. Finally, regarding additions and deployment options, Windows Server 2025 features Azure Edition, optimized for hybrid and cloud-first environments, improved flexibility and better support for containers and microservices architectures. Windows Server 2022 focuses on traditional data center environments and cloud, but is less cloud optimized compared to Windows Server 2025. In summary, Windows Server 2025 introduces more aggressive cloud-first features and hybrid cloud integration with better security, advanced container support, and enhanced NVMe storage capabilities. Windows Server 2022 is strong in traditional center environments with improved security and virtualization features, but lags behind in cloud and containerized environments compared to Windows Server 2025. Ultimately, Windows Server 2025 is designed for organizations embracing modern cloud architectures and containerized applications, while Windows Server 2022 is more suited for businesses with traditional on-premises data center setups or less complex cloud needs. Windows Center, also WWAC, is a web-based management tool for managing Windows Server, Windows 10, and Windows 11 systems. It provides a central interface for IT administrators to monitor and manage their infrastructure from a single place. Here are the key features of Windows Admin Center. WAS allows for remote management of physical and virtual servers without needing to use Remote Desktop Protocol, RDP. You can monitor system performance, events, updates, storage usage, network configurations, etc. It includes tools to manage Active Directory, group policies, and user accounts. You can manage Hyper-V hosts and virtual machines, VMs, including starting, stopping, or migrating VMs. PowerShell scripts can be run directly within the WAC interface. It allows monitoring of storage health and also integrates with Windows Server Backup. WAC provides insights on system security, updates, and troubleshooting capabilities. Windows Admin Center is particularly useful for hybrid IT environments that include both on-premises servers and cloud-based systems, as it integrates with Azure for extended functionality. You can access WAC via a web browser once it's installed on a server or machine in your network. Would you like to know more about how to set it up or specific use cases? The Windows file system is fascinating, acting as a backbone for how we store and manage our digital lives. At its core, we have two main types, FAT and NTFS. FAT is the simpler, older system, for small drives like USBs, while NTFS is the for internal drives, offering advanced features like file permissions and encryption. Imagine navigating through volumes like CEC or DEC. Directories and subfolders create a neat hierarchy for our files, images, applications, all organized for easy access. The master file table, or MFT, is like the brain of NTFS, keeping track of every file's metadata. And let's not forget about file names. You can use up to 255 characters, treats file.txt and file.txt as the same. Accessing files is a breeze with paths, and File Explorer makes it even simpler with its drag and drop functionality. Plus, NTFS brings extra features to the table, like compression to save space, encryption for security, and shadow copies for backups. In essence, the Windows file system is designed for efficiency and security, making our digital experience seamless and reliable. The Windows file system is fascinating, acting as the backbone for how we store and manage our digital lives. At its core, we have two main types, FAT and NTFS. FAT is the simpler, older system, perfect for small drives like USBs, while NTFS is the powerhouse for internal drives, offering advanced features like file permissions and encryption. The Windows file system is the structure used by Microsoft Windows operating systems to store, organize, and manage files on storage devices like hard drives, SSDs, or USB drives. Windows primarily uses two types of file systems, FAT, which is an older and simpler file system used mainly for small drive movable storage, and NTFS, which is more advanced and used for internal hard drives and larger, more complex storage. NTFS supports features like file permissions, encryption, disk quotas, and larger files, and it is the default for modern versions of Windows. A storage device or partition is called a volume, with C or DAS typically being the main drive letters. A hierarchy of folders and subfolders is used to organize files, with individual items like documents, images, or applications stored in directories. Key components of NTFS include the master file table, which is a database that stores metadata about every file, including name, size, location, and permissions. Clusters are the smallest unit of disk space that files are stored in, and NTFS supports file-level security by allowing users and groups to set permissions, specifying who can read, write, or execute files. Windows uses file names that can include up to 255 characters, with certain restrictions on symbols, and supports long file names and case-insensitive naming. Files are accessed by file paths, like C, name, documents, file.txt, and Windows uses Explorer for graphical management of files, with drag-and-drop capabilities. Additional features of NTFS include support for file and folder compression disks, the ability to encrypt files with the encrypting file system, and the capability to create backups of files even if they're in use. In summary, Windows file systems like FAT and NTFS provide efficient and secure methods for storing and organizing data, with NTFS being the primary file system for most modern Windows environments due to its advanced features. In Windows, a partition is essentially a section of your storage device, like a hard drive or SSD, that operates as an independent unit. There are two main types, MBR and GPT. MBR is the older scheme, allowing only 4 primary partitions and a maximum of 2 TB per disk. It's like a vintage car, reliable but limited. On the other hand, GPT is the modern powerhouse, supporting unlimited partitions and massive drives up to 9.4 zettabytes. It's built for today's tech, especially with UEFI systems. Then we have primary and extended partitions. Primary ones can host operating systems, while extended partitions serve as containers for logical partitions, letting you create more than 4 on an MBR disk. Dynamic disks take it a step further, offering features like spanning and RAID configurations for enhanced performance and redundancy. Don't forget about recovery and OEM partitions. Recovery partitions hold the tools to fix a corrupted system, while OEM partitions are created by manufacturers for system recovery and pre-installed. Understanding these partition types is crucial for managing your storage effectively. UEFI, or Unified Extensible Firmware Interface Boot, is a modern system for booting up computers and replacing the older BIOS, or Basic Input-Output System. It's a firmware interface that connects the computer's hardware to the operating system and provides the instructions to boot the system. UEFI was designed to address the limitations of the older BIOS system, providing better performance, security, and features for modern hardware. Unlike BIOS, which has a text-based interface, UEFI can provide a graphical interface with mouse support, which makes it easier to interact with. UEFI support drives larger than 2 TB, which is a limitation in BIOS. It uses the gig partition table, or GPT, rather than the older master boot record, or MBR, allowing for larger and more flexible partitioning. UEFI typically allows for faster boot times than BIOS because it can initialize hardware more efficiently. UEFI includes a feature called Secure Boot, which ensures that only trusted software, signed by Microsoft or the hardware manufacturer, can run during boot process. This helps protect the system from rootkits and malware. UEFI is designed to work with modern hardware and operating systems, and it supports both 32-bit and 64-bit systems. UEFI provides a pre-boot environment, allowing the computer to run diagnostics, update firmware, or load other utilities before the OS starts. UEFI is modular, meaning it can be extended with drivers or other software, allowing for more flexibility in the boot process. When you turn on your computer, UEFI firmware initializes the hardware components, such as the CPU, RAM, and storage, and then loads the operating system's bootloader, such as Windows Boot Manager or GRUB for Linux. The bootloader then takes over, loading the OS into memory and starting the operating system. In comparison, BIOS is an older, simpler system with a text-based interface, limited hardware support, and slower boot times, while UEFI is a modern, more feature-rich system with faster boot times, support for larger drives, better security, and an advanced graphical interface. Overall, UEFI boot provides a more robust, secure, and efficient way to start a computer compared to the traditional BIOS. Let's break down TPM, Trusted Platform Module, and GPT, Guide Partition Table, Partitions. TPM is a hardware-based security module that is used to enhance the security of a computer by providing encryption and protecting sensitive information, like encryption keys and passwords. It is a small chip, usually integrated into the motherboard, that works with the system's software to perform security-related functions. Key features of TPM include hardware-based security, which provides physical isolation of sensitive data from the rest of the system, making it harder for malware or unauthorized users to access or tamper with it. It securely stores encryption keys, such as those used in BitLocker encryption in Windows or other disk encryption solutions. TPM helps with secure boot, ensuring that only trusted firmware or operating systems are allowed to run, protecting against bootkits and rootkits. It can measure and verify system integrity, checking whether system files or firmware have been tampered with. TPM is also used for strong authentication, providing a secure method for users to authenticate to a device using biometrics, PINs, or passwords. Use cases for TPM include BitLocker, a disk encryption tool in Windows that uses TPM to securely store the encryption keys, Windows Hello, a biometric authentication method for logging into Windows using facial recognition or fingerprints, and Secure Boot, which ensures the OS and firmware haven't been tampered with by checking digital signatures. Now let's discuss GPT, Guide Partition Table. GPT is a modern partitioning scheme that replaces the older MBR, Master Boot Record, partitioning system. It defines how data is organized and stored on a storage device, such as a hard drive or SSD. Key features of GPT include larger disk support, as it supports disks larger than 2 TB, making it ideal for modern drives. GPT allows for up to 128 primary partitions, depending on the OS, without needing to create extended or logical partitions like an MBR. It stores multiple copies of the partition table, both at the beginning and the end of the disk, making it more resilient to corruption or data loss. GPT includes CRC protection to verify the partition table has not been corrupted and is part of the UEFI standard required for booting UEFI-based systems, unlike MBR, which is used with legacy BIOS systems. When comparing GPT and MBR, MBR is the older partitioning scheme that supports a maximum of 4 primary partitions and disks, up to 2 TB, becoming obsolete in favor of GPT for newer systems. GPT is modern, flexible, and more robust, supporting larger drives, more partitions, and is needed for systems that use UEFI instead of BIOS. An example partition layout with GPT includes the EFI System Partition, ESP, which is a small partition used by UEFI to store boot files, primary partitions, where your operating system and data are stored, and a recovery partition used by the operating system to store recovery files. TPM and GPT serve different but complementary purposes in modern computing. TPM enhances security by storing encryption keys and ensuring system integrity through secure boot. GPT is about how data is organized on the disk and ensures that modern disks are partitioned correctly and efficiently. For example, on a UEFI-based system, Secure Boot, enabled by TPM, can ensure that only signed bootloaders from a trusted source are executed. Meanwhile, GPT enables the system to use a UEFI-compatible boot partition, such as the EFI System Partition, to load the OS. In summary, TPM is a hardware security chip that provides encryption and system integrity features, like Secure Boot and disk encryption. GPT is a modern partitioning scheme that allows for larger drives, or partitions, and better data integrity compared to the older MBR partitioning system. Together, they contribute to the security and efficiency of modern computers by ensuring safe booting, data encryption, and proper disk management. Boot MGR, or Boot Manager, is a crucial component in modern Windows systems, starting from Vista all the way to Windows 10. It replaces the older TLDR and is primarily used in UEFI systems, which utilize the Guide Partition Table for disk management. One of its key functions is to read the boot configuration data, or BCD, which stores vital information about your operating system and boot options. When you power on your computer, the UEFI or BIOS initializes the hardware. And if UEFI is in play, it loads the EFI system partition containing BootMGR. Once BootMGR is in memory, it reads the BCD to determine which OS to load, then kicks off the Windows kernel and essential drivers. However, if something goes wrong, like a missing BootMGR file or a misconfigured boot device, you might see errors like BootMGR missing. This can be frustrating, but BootMGR also has recovery capabilities, launching the Windows recovery environment to help you troubleshoot. It even manages dual boot scenarios, letting you choose between multiple operating systems. Understanding BootMGR is key to navigating the boot process smoothly. BootMGR, or Boot Manager, is a crucial component in modern Windows systems, starting from Vista all the way to Windows 10. It replaces the older NTLDR and is primarily used in UEFI systems, which utilize the Guide Partition Table for disk management. NTLDR was the backbone of booting older Windows versions, handling BIOS and MBR partitions like a pro. It was reliable, but as technology evolved, so did our needs. Enter BootMGR, the modern hero that took the stage with Windows Vista. BootMGR brought along support for UEFI and GPT partitions, making it a game changer for today's hardware. Imagine trying to fit a square peg in a round hole. NTLDR just couldn't keep up with the demands of modern PCs. BootMGR not only simplifies the boot process, but also enhances security and performance. So while both NTLDR and BootMGR share the same goal of booting Windows, BootMGR is like upgrading from a flip phone to a smartphone. It's just smart and more efficient for the tech-savvy world we live in. NTLDR was the backbone of booting older Windows versions, handling BIOS and MBR partitions like a pro. It was reliable, but as technology evolved, so did our needs. Enter BootMGR, the modern hero that took the stage with Windows Vista. BootMGR brought along support for UEFI and GPT partitions, making it a game changer for today's hardware. Windows Device Manager is a built-in utility in Windows operating systems that allows users to view and manage the hardware devices installed on their computer. Centralized location for managing devices, drivers, and device settings. It displays all the hardware components such as processors, display adapters, network adapters, disk drives, sound devices, and more in a categorized tree structure. You can install, update, rollback, or uninstall drivers for individual devices. It shows error codes or warnings for devices that may not be functioning correctly, helping users diagnose issues. It allows users to change settings or properties for specific devices. Common use cases include installing or updating drivers, enabling or disabling hardware, diagnosing hardware issues, and checking device status or resolving conflicts. To access it, you can right-click the Start button and choose Device Manager, or type Device Manager in the search bar. Windows Device Manager is a built-in utility in Windows operating systems that allows users to view and manage the hardware devices installed on their computer. It provides a centralized location for managing devices, drivers, and device settings. The server registry refers to the Windows registry on a server system. It's a critical database that's configuration settings and options for the operating system, software, and user preferences. It's essentially a hierarchical database that allows the operating system and installed programs to access and modify configuration information. The registry is organized into a tree-like structure with keys and values. The keys are folders, values, or other subkeys. Major sections or branches in the registry include HKI, local machine, current user, and others. Individual data entries associated with each key can be string registers or binary data. Common registry types include HKEY, local machine, which contains configuration settings for the local computer. HKEY, current user, for settings specific to the current user. HKey classes root, which contains file association and COM object addition. HKey, which stores settings for all user profiles on the machine. And HK current config, which contains information about the current hardware profile in use. On a Windows server, the registry is used to manage a variety of settings, such as system configuration, software installation and configuration, hardware management, and user profiles and permissions. The registry can be edited using the registry editor, but modifying it directly should be done with caution, as incorrect changes can cause system instability or failures. On servers, the registry is vital for configuring server-specific services such as Active Directory, IIS, SQL Server settings, and remote desktop services. The Windows registry is critical for system functionality. It's important to back up the registry before making any changes. Errors in registry configurations can lead to serious system issues or even prevent the system from booting properly. In the context of Windows operating systems, local system, network service, and local service are special accounts used to run various system services with different levels of privileges. Each account has different access rights and security restrictions, making them suitable for different types of services. The local system account has the highest privileges and full access to the local machine, including the ability to interact with hardware and manage processes. However, it does not have network access unless granted explicitly. It is typically used by critical system services that need to operate with high-level permissions, such as update or some core system services. The limitation is that it cannot access network resources unless specifically configured. The network service account has a lower privilege level than the local system, but is sufficient for network-based operations. It has more restricted local permissions compared to the local system account and can access network resources with the credentials of the computer account instead of as a specific user. It is designed to run services that need network access but don't require high local privileges. An example is IIS, which often runs under this account. The limitation is that it has limited local success, but is capable of accessing network resources. The local service account has very restricted local permissions and limited network access. It is similar to the network service account in terms of local permissions, but is even restricted. It has the same privileges as a regular user, meaning it cannot perform high-level operations on the local machine. In summary, this account has full local machine access and no network access by default, used for critical system services. The network service account has restricted local access and can access network resources for services needing network access. The local service account has very restricted local access and accesses the network anonymously, used for low privileges. Each of these accounts is designed to follow the principle of least privilege, ensuring services run with only the minimum necessary permissions to mitigate security risks. Active Directory, AD, is a directory service developed by Microsoft to manage and organize resources in a network, such as users, computers, servers, printers, and other devices. It is primarily used in Windows domain networks and provides a central place to manage, authenticate, and authorize access to network resources. Key components and concepts of Active Directory include a domain, which is a logical grouping of networked computers and devices that share a common directory database, with each domain having a unique name, such as company.local. A domain controller, DC, is a server that stores the Active Directory database and is responsible for authenticating and authorizing users and computers within the domain. LDAP, or Lightweight Directory Access Protocol, is a protocol used by Active Directory to allow communication between clients and servers, enabling the querying and modification of the directory. Organizational units, OUs, are containers used to organize objects, such as users, groups, and computers, within a domain, helping with administrative delegation and group policy application. Groups are collections of users, devices, or other groups, often used for simplifying the management of permissions and access to resources. Trusts are relationships between domains that allow users in one domain to access resources in another domain. Group policy, GPO, is a feature that allows administrators to apply specific configurations and restrictions to users and computers within the domain, including security settings and software installation. Active Directory relies on DNS, or Domain Name System, for name resolution, and domain controllers must be registered in DNS for proper function. The Global Catalog is a distributed data store that contains information about every object in the AD forest, providing fast search capabilities across domains. In summary, Active Directory is a critical component for managing network resources, ensuring secure access, and streamlining administrative tasks in corporate or organizational IT environments. Imagine a vast digital landscape where domains are like cities, each with its own unique identity. In this realm, a domain tree is a collection of these cities sharing a contiguous namespace, all organized in a hierarchical structure. Take GlobalCorp, for example. Its root domain, globalcorp.com, branches out into child domains like usglobalcorp.com and uk.globalcorp.com, forming a cohesive domain tree. Now, picture GlobalCorp acquiring TechWorld. Suddenly, we have a new root domain, techworld.com, with its own child domains, us.techworld.com and uk.techworld.com. These two domain trees, globalcorp.com and techworld.com, now coexist within a larger domain forest. This forest is more than just a collection of trees. It shares the same schema and configuration, creating a unified boundary for Active Directory. So, in essence, a domain tree is a tightly knit group of domains, while a domain forest is a broader ecosystem, allowing for diverse namespaces to thrive together. Imagine a vast digital landscape where domains are like cities, each with its own unique identity. In this realm, a domain tree is a collection of these cities, sharing a contiguous namespace, all organized in a hierarchical structure. LDAP, or Lightweight Directory Access Protocol, is like the backbone of directory services, allowing us to manage user and group information across a network. Think of it as a centralized database where you can easily query details about users or check group memberships. In Microsoft Active Directory, LDAP plays a crucial role in accessing this information. Now let's talk about Kerberos. This is a network authentication protocol that secures user logins over potentially insecure networks. Instead of sending passwords around, it uses tickets issued by a trusted key distribution center. When you log in, you get a ticket-granting ticket, which allows you to access various services without exposing your password. Finally, we have SSSD, or System Security Service Daemon. This is essential for Linux systems, enabling them to authenticate users against centralized directories like Active Directory. It integrates LDAP for identity management and Kerberos for secure authentication, ensuring that users can log in seamlessly while maintaining security. Together, LDAP, Kerberos, and SSSD create a robust framework for managing identities and securing access in diverse environments. In the realm of Microsoft Active Directory, the terms PDC, BDC, and ADDS represent key components of domain management. The primary domain controller, or BDC, was the backbone of Windows NT, managing user accounts and security policies. It held the master copy of the domain database, ensuring that everything ran smoothly. Meanwhile, backup domain controllers, or BDCs, provided essential redundancy. They replicated data from the PDC, but couldn't make changes themselves, acting as a safety net in case PDC failed. Fast forward to Active Directory Domain Services, or ADDS, introduced in Windows 2000. This modern system replaced the PDC and BDC model with a multi-master replication approach, allowing any domain controller to handle updates. ADDS not only streamlines user management, but also enhances fault tolerance, making it a robust solution for today's networks. In realm of Microsoft Active Directory, the terms PDC, BDC, and ADDS represent key components of domain management. The primary domain controller, or PDC, was the backbone of Windows NT, managing user accounts and security policies. With the advent of Active Directory in Windows 2000 and later versions of Windows Server, the PDC and BDC concepts were replaced by the Active Directory Domain Services model, which is a much more advanced and flexible system for managing users, groups, and other directory objects. ADDS is the core directory service in Active Directory. It allows for the creation and management of domains, organizational units, user accounts, groups, computers, and more. ADDS is responsible for the storage of directory data, authentication, and authorization services in a Windows network environment. Instead of having a single PDC and multiple BDCs, Active Directory uses a multi-master replication model, meaning any domain controller in the domain can handle updates and changes to the directory database, and changes are replicated across all domain controllers. ADDS ensures redundancy and fault tolerance without relying on a single authoritative PDC. Domain controllers are servers that host Active Directory and authenticate users and machines in the domain. Certain operations, like managing schema or assigning RD pools, are handled by specific DCs that take on FSMO roles. A domain controller can also function as a global catalog server, which contains a partial replica of every object in the AD forest, allowing it to speed up searches for directory objects. In the world of Windows NT, we had the primary domain controller, or PDC, which was the go-to for all domain management. It held the keys to the kingdom, managing user accounts and security policies. Then came the backup domain controller, or BDC, which was like the PDC's trusty sidekick, replicating data to ensure continuity. But as technology evolved, so did our needs. Enter Active Directory Domain Services, or ADDS. This modern marvel revolutionized how we manage domains. With multiple domain controllers working in harmony, updates and authentication are seamless. The PDC and BDC, they've become relics of the past, replaced by a more robust and efficient system that keeps our networks running smoothly. It's a game changer in centralized management. In the world of Windows NT, we had the primary domain controller, or PDC, which was the go-to for all domain management. It held the key to the kingdom, managing user accounts and security policies. Then came the backup domain controller, or BDC, which was like the PDC's trusty sidekick, replicating data to ensure continuity. A domain forest is essentially a collection of one or more Active Directory domains that share a common schema and configuration. Think of it as a big organizational tree where each domain is a branch, and they all work together to manage resources and users efficiently. This structure allows for centralized management, making it easier to implement security policies and share resources across different domains. In a domain forest, you have multiple domains that can trust each other, which means users in one domain can access resources in another without needing separate credentials. This interconnectedness enhances collaboration while maintaining security boundaries. Plus, the forest root domain is like the parent, holding the schema and configuration that all other domains inherit. So, when you think of a domain forest, picture a well-organized ecosystem where everything is interconnected yet distinct, allowing for both flexibility and control in managing IT resources. A domain forest is essentially a collection of one or more Active Directory domains that share a common schema and configuration. Think of it as a big organizational tree where each domain is a branch, and they all work together to manage resources and users efficiently. Active Directory domain is like the backbone of a network, managing everything from user accounts to security policies. Imagine it as a digital directory where all the important information about users, computers, and resources is stored. When you log into your computer at work, Active Directory verifies your credentials, ensuring you have the right access to files and applications. It's not just about logging in, it's about controlling who can do what within the network. With features like group policy, administrators can enforce security settings across all devices, making sure everyone is on the same page. Plus, it simplifies management by allowing bulk updates and changes. In essence, Active Directory domain is crucial for maintaining order and security in an organization's IT environment, making it easier for everyone to work efficiently and safely. Active Directory domain is like the backbone of a network, managing everything from user accounts to security policies. A child domain is like a branch sprouted from the trunk of a tree, rooted in the parent domain but standing on its own. Imagine a vast forest where each tree represents a domain. The child domain inherits the forest schema and configuration, ensuring it has the same foundational structure, but boasts its own unique DNS name and domain controllers. This hierarchical relationship allows for streamlined management and security while maintaining individuality. Think of it as a family tree. Each child domain can have its own policies and permissions, tailored to its specific needs, while still benefiting from the overarching governance of the parent domain. This setup not only enhances organization, but also fosters scalability, making it easier to manage resources across a diverse network. In essence, child domains empower organizations to grow and adapt without losing the benefits of a unified structure. A child domain is like a branch sprouting from the trunk of a tree, rooted in the parent domain but standing on its own. Imagine a vast forest where each tree represents a domain. The relationship between forest domain and child domain looks like this. Forest is the root container for all domains. Each domain within the forest is a discrete unit of administration and security. A child domain is a subdomain of the parent domain, inheriting some configurations but distinct in its own right. This structure allows Active Directory to scale effectively in large organizations, offering the ability to manage complex relationships, autonomy, and replication across many domains. The relationship between forest domain and child domain looks like this. Forest is the root container for all domains. Each domain within the forest is a discrete unit of administration and security. Imagine a global company called Example Corp that has a forest named ExampleCorp.com. Within this forest, the company has different divisions based in various regions, such as Europe, North America, and Asia, and each region needs its own domain for administrative control. The forest is ExampleCorp.com, with the root domain also being ExampleCorp.com. The child domains include us.ExampleCorp.com for North America, EU, ExampleCorp.com for Europe, and Asia, ExampleCorp.com for Asia. The company might have separate IT teams managing each region, with delegated administrative control over their respective child domains. while still maintaining a unified global directory service under the root domain. Imagine a global company called Example Corp that has a forest named examplecorp.com. Within this forest, the company has different divisions based in various regions, such as Europe, North America, and Asia, and each region needs its own domain for administrative control. In the world of Active Directory, think of a forest as a vast ecosystem where each domain acts like a unique habitat. Each domain is responsible for managing user authentication and security policies, ensuring that resources are protected and accessible. Now, picture a child domain as a smaller specialized area within this ecosystem, branching off from a parent domain. It has its own domain controllers, yet it shares a common schema and configuration, creating a seamless connection. This hierarchical structure not only allows organizations to scale their environments efficiently, but also maintains clear visions for effective administration across different regions or business units. It's a smart way to manage complexity while keeping everything organized and secure. In the world of Active Directory, think of forest as a vast ecosystem where each domain acts like a unique habitat. Each domain is responsible for managing user authentication and security policies, ensuring that resources are protected and accessible. In Active Directory, Operation Master roles, or FSMO roles, are essential for maintaining order among domain controllers. There are 5 of these roles, split in 2 categories, forest-wide and domain-wide. First, we have the Schema Master, which controls updates to the directory schema. Think of it as the blueprint for your AD structure. Next is the Domain Naming Master, responsible for ensuring unique domain names within the forest. On the domain-wide side, we have the PDC Emulator, which acts as the primary time source and handles password changes. The RID Master allocates unique identifiers to ensure no 2 objects share the same ID. Finally, the Infrastructure Master updates references to objects in other domains. Each role plays a crucial part in preventing conflicts and ensuring smooth operations, making them the backbone of a well-functioning Active Directory environment. Understanding these roles is key to effective AD management. In Active Directory, Operation Master roles, or FSMO roles, are essential for maintaining order among domain controllers. There are 5 of these roles, split into 2 categories, forest-wide and domain-wide. First, we have the Schema Master, which controls updates to the directory schema. Think of it as the blueprint for your AD structure. The Schema Master role is a crucial component of Active Directory at the forest level. Imagine it as the architect of your digital ecosystem. It's responsible for defining the blueprint of all objects within the forest, users, groups, computers, you name it. Whenever there's a need to make changes to this schema, whether it's adding a new attribute or modifying an existing one, the Schema Master steps in. It ensures that these changes are replicated across all domains, maintaining consistency and integrity throughout the forest. Without the Schema Master, chaos could ensue, as different domains might operate with conflicting definitions. So, in essence, this role is not just about making changes. It's about ensuring that the entire forest functions harmoniously, allowing for seamless communication and management of resources. The Schema Master is vital for the stability and efficiency of the Active Directory environment. As the Domain Naming Master, I hold a crucial role in maintaining the integrity of our forest. My primary responsibility? Ensuring that every domain name is unique, preventing any potential name conflicts. When a new domain is added, I meticulously check to guarantee it doesn't clash with existing names. It's a bit like being a gatekeeper, ensuring that every entry is distinct and clear. Occasionally, I handle the delicate task of renaming domains. While it's not something I do every day, when it comes up, I approach it with precision and care. After all, a well-organized naming structure is vital for smooth operations. In essence, I'm the guardian of our domain names, ensuring seamless communication and functionality across the entire forest. As the PC emulator, I play a crucial role in the smooth operation of your domain. Think of me as the go-to authority for password changes. When a user updates their password, I ensure that change is instantly reflected and replicated across all domain controllers. Time synchronization? That's my specialty. Every DC aligns its clock with me, keeping everything in perfect harmony. I also bridge the gap for legacy clients, ensuring older Windows NT and Windows 9X systems can still function seamlessly in today's environment. When it comes to group policy updates, I'm the one processing those changes and generating the group policy object for the entire domain. Plus, I manage the RID pool, controlling updates in Active Directory domain services. In short, I'm the backbone that keeps everything running smoothly, ensuring both modern and legacy systems can thrive together. As the PDC emulator, I play a crucial role in the smooth operation of your domain. Think of me as the go-to authority for password changes. When a user updates their password, I ensure that change is instantly reflected and replicated across all domain controllers. As the RID Master, I play a crucial role in the Active Directory ecosystem. My primary responsibility? Allocating unique relative identifiers, or RIDs, to domain controllers within the domain. Each domain controller relies on me to provide a pool of RIDs, ensuring that every object, be it a user group or computer, gets its own unique identifier. When a domain controller creates a new object, it pulls from its allocated RID pool. But what happens when it runs out? That's where I come in again. It sends a request my way for a new pool, and I'm right there to keep things running smoothly. With only one RID master per domain, I ensure that there are no conflicts in RID assignments. It's all about maintaining order in the digital realm so every object can coexist without a hitch. My role is vital for seamless operations in Active Directory, and I take pride in keeping everything organized and conflict-free. As the RID master, I play a crucial role in the Active Directory ecosystem. My primary responsibility? allocating unique relative identifiers or RIDs to domain controllers within the domain. As the infrastructure master, my role is crucial in maintaining the integrity of our domain. Imagine a user in one domain who's a member of a group in another. If that user moves or their group changes, it's my job to ensure that all references are updated seamlessly. I track these cross-domain relationships, keeping group memberships accurate and up to date. This prevents any confusion or access issues that could arise from outdated information. Without me, the connection between users and groups could easily become tangled, leading to potential security risks and operational hiccups. So, while I may work behind scenes, my impact is felt across the entire forest, ensuring smooth collaboration and communication. As the infrastructure master, my role is crucial in maintaining the integrity of our domain. Imagine a user in one domain who's a member of a group in another. In the world of Active Directory, we have 5 key FSMO roles, each with its unique function. First up, the schema master, the gatekeeper of schema changes, defining what objects and attributes we can use across the entire forest. Then we have the domain naming master, ensuring that every domain name is unique and managing the creation and removal of domains. Next, the PDC emulator steps in, handling password changes and time synchronization, while also keeping legacy clients happy. Over in the domain realm, the RID master allocates RID pools to domain controllers, making sure they have the identifiers they need. Lastly, the infrastructure master updates cross-domain object references, like group memberships, ensuring everything stays in sync. Each role is crucial for a smooth and efficient Active Directory environment. When it comes to FSMO role placement, there are some key best practices to keep in mind. First off, the schema master and domain naming master should always be on different domain controllers. This is crucial for maintaining stability in your forest. Ideally, you want these roles on a DC in the forest root domain. Now, for the PC emulator, RID master, and infrastructure master, it's best to distribute them across different DCs within the same domain. If you find yourself with just one domain controller, it will automatically take on all these roles, which isn't ideal for redundancy. To ensure high availability, place FSMO roles on stable and well-connected DCs. Just remember, clustering all these roles on a single DC should be a last resort. Balancing the load not only enhances performance, but also safeguards against potential failures. When it comes to FSMO role placement, there are some key best practices to keep in mind. Managing FSMO roles in Active Directory is crucial for maintaining a healthy domain. When it comes to role transfer, think of it as a smooth handoff. You can gracefully transfer roles using tools like NTD-sutil, Active Directory users and computers, or PowerShell. This is perfect for maintenance or when reorganize your infrastructure. Now, role seizure is a different beast. If your current FSMO role holder fails, you can forcefully seize the role with NTD-sutil. But be cautious. This is an emergency measure and can lead to data inconsistencies if not handled properly. So, always weigh your options. Remember, a well-managed Active Directory keeps your network running smoothly and efficiently. Managing FSMO roles in Active Directory is crucial for maintaining a healthy domain. When it comes to role transfer, think of it as a smooth handoff. FSMO roles are the backbone of a healthy Active Directory environment. Think of them as the essential managers that ensure everything runs smoothly. There are 5 key roles: schema master, domain naming master, RID master, PDC emulator, and infrastructure master. Each has its unique responsibilities, from managing schema updates to coordinating domain-wide changes. Understanding where these roles are located is crucial because if one goes down, it can lead to replication issues and administrative headaches. For instance, the PDC emulator is vital for time synchronization and password changes. If it's not functioning properly, users could face delays or even failures in authentication. Regularly monitoring and managing these roles ensures that your directory services remain stable and efficient. So, keep an eye on your FSMO roles, because a well-maintained Active Directory is key to seamless operations and a secure environment. FSMO roles are the backbone of a healthy Active Directory environment. Think of them as the essential managers that ensure everything runs smoothly. When it comes to managing networks, the choice between a domain and a workgroup can make all the difference. A domain powered by a centralized domain controller is designed for large organizations. It offers centralized authentication through Active Directory, allowing for streamlined user management and robust security policies. This means you can enforce security settings across all machines, making it easier to protect sensitive data. On the flip side, we have workgroups, perfect for smaller setups like home networks or small offices. Here, each computer operates independently with local accounts, which means less complexity, but also less control. Security settings are managed individually, making it simpler but potentially riskier. If you're looking to scale and need tight control over your network, a domain is the way to go. But if you prioritize ease of setup and minimal administration, a workgroup will serve you well. Choose wisely based on your needs. Domain functional roles (FLs) in Microsoft Active Directory define the set of features and capabilities available within a domain based on the version of Windows Server that is running on the domain controllers. The functional level affects things like security features, group policies, replication, and the overall functionality of the Active Directory environment. When you raise the domain functional level, you're essentially enabling newer Active Directory features that require a high version of Windows Server. But this action also restricts you from using older versions of Windows Server as domain controllers in that domain. Here's an overview of the common domain functional levels and the corresponding Windows Server versions. Windows 2000. Native supports Active Directory features, but lacks some advanced features. Windows Server 2003 introduces better security and performance features, such as group memberships and DNS integration. Windows Server 2003 R2 introduces DFS, distributed file system, and fine-grained password policies. Windows Server 2008 introduces DFS replication and read-only domain controllers, RODC. Windows Server 2008 R2 introduces managed service accounts and improvements to group policy. Windows Server 2012 includes dynamic access control and KDC, key distribution center enhancements. Windows Server 2012 R2 has enhanced group managed service accounts, GMSA, and KDC enhancements. Windows Server 2016 introduces Kerberos armoring, privileged access management, and domain controller cloning. Windows Server 2019 includes Azure AD join and improvements to security and AD replication. Windows Server 2022 has enhancements to Windows Defender and security features and AD certificate services. When a domain functional level is raised, it enables additional features, but also has certain limitations. Older versions of Windows Server domain controllers cannot be added to a domain that has a higher functional level. For example, if you raise the domain functional level to Windows Server 2008, you can no longer have domain controllers running Windows 2000 Server or Windows Server 2003. Once you raise the domain functional level, you cannot revert it back to a lower level, for example, from Windows Server 2008 to Windows 2000 Native. Newer functional levels unlock new features, such as group managed service accounts, GMSA, from Windows Server 2012, fine-grained password policies from Windows Server 2003, read-only domain controllers, RODC, from Windows Server 2008, Kerberos armoring from Windows Server 2016, and domain controller cloning from Windows Server 2016. To raise the domain functional level, open Active Directory Domains and Trusts. Right-click the domain and select Raise Domain Functional Level. Choose the desired functional level from the available options and click Raise. Once the domain functional level is raised, you can take advantage of the new features, but need to ensure all domain controllers in that domain are running at least the version of Windows Server required for the new functional level. A domain functional level applies to a specific domain, while a forest functional level applies to the entire forest. Both need to be compatible and should be raised carefully. Before raising the domain functional level, check that all domain controllers are running the required version of Windows Server to avoid compatibility issues. Raising the domain functional level is a crucial step in leveraging the latest AD features and ensuring a more secure, feature-rich environment. However, it requires careful planning, especially in large or multi-domain environments. Active Directory has several kinds of data that need to be replicated. Active Directory data is divided in several directory partitions, which are replicated independently. Partitions include the domain partition, which contains all objects in a domain, such as users and groups. The configuration partition contains information about the Active Directory forest configuration, including site topology and replication topology. The schema partition contains the schema for the forest, which includes definitions for object types and attributes, and this is forest-wide. Lastly, the application partition replicates application-specific data, such as DNS data or other application-specific data, across domain controllers in the forest. Active Directory has several kinds of data that need to be replicated. The Global Catalog, or GC, is a crucial component of Active Directory. Think of it as a read-only snapshot of the entire AD database, containing a partial replica of every object across the forest. This means when you're searching for users or resources, the GC speeds up those queries, making it much more efficient, especially in multi-domain environments. Without the Global Catalog, user logons would be a hassle, as it's essential for authentication across different domains. The GC is replicated to specific domain controllers known as Global Catalog servers, ensuring that this vital information is readily available. This replication not only enhances performance, but also boosts reliability, allowing for seamless access to directory information. So, the next time you log in or search for a resource, remember the Global Catalog is working behind the scenes, making it all possible. The Global Catalog, or GC, is a crucial component of Active Directory. Think of it as read-only snapshot of the entire AD database, containing a partial replica of every object across the forest. When change occurs on a domain controller, like creating or updating an object, it sends out a notification to other domain controllers in the domain or forest. This kicks off the replication process, where the updated data is shared with other DCs that hold the same partition data. Each domain controller keeps track of these changes of replication metadata, ensuring that updates and timestamps are meticulously logged. Now, what happens if two DCs modify the same object before replication? That's where conflict resolution comes in. Active Directory uses a last writer wins model, meaning the most recent update is deemed the authoritative version. Timestamps play a critical role here, tagging each change with the exact time and date. In terms of frequency, intra-site replication occurs every 15 minutes by default, while inter-site replication can be adjusted to intervals between 15 and 180 minutes. Plus, Active Directory is efficient. It replicates changes on a per-object basis, ensuring that only modified objects are sent across, which significantly reduces replication traffic. This streamlined process keeps our directory services running smoothly and efficiently. Replication latency is a crucial aspect of maintaining a healthy network of domain controllers. It's all about the time it takes for changes made on one controller to ripple through to others. In a well-connected environment, this usually happens within minutes, but it can vary based on your settings and network conditions. Now let's talk about replication intervals. Within the same site, replication is pretty snappy, defaulting to every 15 minutes. But when you're dealing with remote site over a WAN, things can slow down. The distance and bandwidth limitations come into play, making those intervals less frequent. As an administrator, you have the power to configure these intervals to optimize performance based on your network's capabilities. Understanding and managing replication timing and latency is essential for ensuring that your directory services remain consistent and reliable across the board. Replication latency is a crucial aspect to maintaining a healthy network of domain controllers. It's all about the time it takes for changes made on one controller to ripple through to others. Replication is essential to the health of Active Directory, so it's important to monitor its status. Key tools and methods include repadmin, which allows administrators to monitor and troubleshoot replication in Active Directory. Common commands include repadmin, chosh repl summary, which summarizes the status of replication between domain controllers, and repadmin, chosh show repl, which displays detailed information about the replication status between a specific DC and its replication partners. Active Directory sites and services enables administrators to manage and view replication topology, site links, and replication schedules. Here, administrators can also check the status of specific domain controllers and sites. The event viewer on domain controller logs replication-related events under directory service logs, which can help identify replication errors or conflicts. Lastly, the DCDAG tool is useful for diagnosing health and configuration issues related to domain controllers and can also help detect replication failures. Replication is essential to the health of Active Directory, so it's important to monitor its status. Key tools and methods include repadmin, which allows administrators to monitor and troubleshoot replication in Active Directory. Replication failures can be a real headache in Active Directory. Imagine this. Your domain controllers are like a team of dancers, but if the network connection is shaky, they can't keep in sync. Poor connectivity or bandwidth issues can lead to delays or even complete failures in replication. Then there's DNS. It's the backbone of communication. If DNS goes down, it's like losing your GPS. The domain controllers can't find each other, and replication grinds to a halt. Authentication is another crucial piece. If security settings or certificates are misconfigured, it's like trying to enter a club without the right ID. No access, no replication. And let's not forget about time synchronization. Active Directory relies on precise timing for conflict resolution. If there's a significant time skew between domain controllers, replication can fail, leaving your network in disarray. Understanding these pitfalls is key to keeping your Active Directory running smoothly. Active Directory replication is a fascinating process that keeps our domain controllers in sync, ensuring they all share consistent directory data. It operates on a multi-master model, which means any domain controller can make changes, and those changes ripple throughout the entire environment. This is crucial for maintaining data integrity. Replication works across various partitions, with inter-site replication happening quickly to keep things efficient. However, inter-site replication can be scheduled strategically to optimize network performance, which is a smart move for large organizations. Monitoring and troubleshooting replication is vital. If something goes awry, it can lead to inconsistencies that affect user access and security. By keeping a close eye on replication health, we can swiftly resolve issues and maintain a robust Active Directory environment. Understanding this process not only enhances our IT infrastructure, but also empowers us to manage our networks more effectively. Active Directory replication is a fascinating process that keeps our domain controllers in sync, ensuring they all share consistent directory data. It operates on a multi-master model, which means any domain controller can make changes, and those changes ripple throughout the entire environment. DNS, or Domain Name System, is like the Internet's phone book, translating those easy-to-remember domain names into the numerical IP addresses that computers use to communicate. Imagine trying to navigate the web without DNS, having to memorize a string of numbers for every website. It would be chaos. DNS operates on a hierarchical structure, starting from top-level domains like .com or .org, down to subdomains and specific host names. When you type in a URL, your request travels through the system, querying various servers until it finds the right IP address. This decentralized naming system ensures that we can access websites quickly and efficiently, making our online experience seamless. Without DNS, the Internet as we know it would simply not exist. DNS, or Domain Name System, is like the Internet's phone book, translating those easy-to-remember domain names into the numerical IP addresses that computers use to communicate. Imagine trying to navigate the web without DNS, have to memorize a string of numbers for every website. It would be chaos. A user enters a domain name, e.g., www.example.com, into their web browser. The query is sent to a DNS resolver, often provided by your ISP or a third-party DNS service like Google DNS or Cloudflare. If the resolver has the IP address cached from a previous lookup, it returns it immediately. If the resolver doesn't have the IP cached, it sends a recursive query to find the address, starting from the root DNS servers. The root DNS servers are the top-level DNS servers in the system. They don't know the exact IP but can point to TLD servers, such as .com servers for .com domains. These servers manage the TLDs like .com, .org, .net, etc., and direct the request to the authoritative name servers for the domain, in this case, example.com. The authoritative DNS server for the domain contains the actual IP address of the host, e.g., www.example.com, and returns it to the DNS resolver. Once the IP address is retrieved, it's cached by the DNS resolver and may be cached by your browser for a period of time, reducing the need for repeated queries. The DNS resolver sends the IP address back to the user's browser, allowing the browser to establish a connection and load the website. A user enters a domain name, e.g., www.example.com, into their web browser. The query is sent to a DNS resolver, often provided by your ISP or a third-party DNS service like Google DNS or Cloudflare. If the resolver has the IP address cached from a previous lookup, it returns it immediately. A human-readable address like www.example.com is mapped to an IP address. The DNS resolver is the server or service that receives DNS queries and responds with the appropriate IP address. Different record types are used to map domain names to various types of data. Common ones include the A record, which maps a domain to an IPv4 address, such as www.example.com to 192.168.1.1. The A record maps a domain to an IPv6 address. The MX record specifies the mail server for a domain, which is used for email routing. The CNAME record aliases one domain name to another, for example, www.example.com to example.com. The NS record specifies authoritative DNS servers for the domain. The PTR record is used for reverse DNS lookups, mapping an IP to a domain. Name servers are the servers that hold DNS records for domain names, and the DNS resolver queries them for the correct information. At the pinnacle of the DNS hierarchy, we find the root servers, the unsung heroes of the internet. These servers are like ultimate directory assistants, knowing exactly where to point you for top-level domain servers. Think of them as the gatekeepers to the vast world of domains. Now, dive a little deeper, and you'll encounter the top-level domain servers, managing the likes of .com, .org, and .net. They're the ones that keep the internet organized, ensuring that when you type in a web address, you're directed to the right place. But it doesn't stop there. At the base of this hierarchy are the authoritative DNS servers. These are the real record keepers, holding the actual DNS records for specific domains, like example.com. They tell your browser where to go, translating those friendly domain names into IP addresses. It's a seamless dance of data, all happening in the blink of an eye, connecting us to the digital world we rely on every day. Did you know that every time you website, your browser is playing a loop memory? That's right. DNS resolvers and clients, like your web browser, cache DNS records to speed things up. This caching is all about efficiency. When you request a website, the DNS resolver checks its cache first. If it finds the record, it serves it up instantly, saving time and reducing network traffic. But there's a catch. Each record information. This balance between speed and freshness is crucial for a smooth browsing experience. So the next time you load a page, remember the unsung heroes of caching working behind the scenes. Did you know that every time you visit a website, your browser is playing a little game of memory? That's right. DNS resolvers and clients, like your web browser, cache DNS records to speed things up. Malicious actors might insert fake DNS records into a resolver's cache, causing users to be directed to fraudulent or malicious websites. A security protocol called DNSSEC, or DNS security extensions, adds digital signatures to DNS records, helping prevent DNS spoofing and ensuring the authenticity of the data. Additionally, DNS servers can be targeted in distributed denial of service, or DDoS attacks, which aim to overwhelm servers with traffic and disrupt DNS resolution. Malicious actors might insert fake DNS records into a resolver's cache, causing users to be directed to fraudulent or malicious websites. A security protocol called DNSSEC, or DNS security extensions, adds digital signatures to DNS records, helping prevent DNS spoofing, ensuring the authenticity of the data. Additionally, DNS servers can be targeted in distributed denial of service, or DDoS attacks, which aim to overwhelm servers with traffic and disrupt DNS resolution. When it comes to troubleshooting DNS issues, having the right tools is essential. First up is NSLookup, a command line powerhouse that lets you query DNS records for any domain. It's like having a magnifying glass of your DNS, helping you pinpoint problems quickly. Then there's Dig, which takes it a step further. This tool provides detailed DNS query results, making it a favorite among network engineers. With Dig, you can dive deep into the DNS hierarchy and analyze responses, giving you insights that can save you hours of frustration. And let's not forget Whois. This tool is your gateway to domain registration information. It reveals who owns a domain and even shows you the authoritative name servers. Whether you're investigating a potential domain purchase or tracking down a rogue site, Whois is invaluable. Together, these tools form a trifecta for anyone serious about managing and troubleshooting DNS. They empower you to navigate the complexities of the internet with confidence. DNS is like the internet's phone book, translating those complex numeric IP addresses into easy-to-remember domain names. Imagine trying to remember a string of numbers every time you want to visit a website. Frustrating, right? Thanks to DNS, you can simply type in a name, and a series of queries kicks off, reaching out to various DNS servers in a hierarchical structure. But it doesn't stop there. DNS also uses caching to speed things up, storing recent lookups so you can access your favorite sites faster. Plus, it manages different types of data through DNS records, keeping everything organized. Security is crucial too. Without it, we risk spoofing and other threats that could compromise our online experience. In essence, DNS is the backbone of internet navigation, making it seamless for us to connect with websites and services efficiently. It's a silent hero, working behind the scenes to keep our online world running smoothly. DNS zones are a critical concept in the domain name system, DNS, and define a portion of the DNS namespace that is managed by a specific DNS server. A zone is essentially a container for DNS records and is responsible for maintaining information about one or more domain names and their corresponding resource records, such as A records, MX records, etc. A DNS zone is a segment of the domain namespace that is administered by a specific DNS server. It contains the DNS records for a domain or subdomain, helping to map domain names to IP addresses, define mail servers, and manage various types of data for the domain. A zone can be for a single domain, like example.com, or a subdomain, like sub.example.com. In short, a zone contains DNS records that are used by DNS servers to resolve queries for domain names in the zone. There are several types of DNS zones, each serving different purposes. The primary zone, or master zone, is the original source of truth for a specific domain. It is the authoritative DNS zone, where all the domain's DNS records are stored and edited. Changes can only be made on the primary DNS server. The primary zone contains the complete set of DNS records, and other DNS servers, known as secondary servers, replicate data from the primary zone. A secondary zone, or slave zone, is a read-only copy of a primary zone. It is used to provide redundancy, distribute the load of handling DNS queries. Secondary zones receive updates from the primary zone through zone transfers using protocols like AXFR or IXFR. They can answer queries just like the primary zone, but they cannot make changes to the DNS records. They help with load balancing and provide fault tolerance by ensuring that DNS queries can still be resolved if the primary server is unavailable. A stub-zone is a special kind of DNS zone that contains only the essential records to identify the authoritative DNS servers for another zone. A stub-zone contains only a limited set of records, such as NS, name server records, and SOA, start of authority record. It does not contain the full set of DNS records like A records, MX records, etc. Stub zones are used to delegate DNS resolution between domains, providing a way for a DNS server to forward queries to the authoritative server for a different zone. They are typically used to connect different parts of the DNS hierarchy, especially in large environments. A forward lookup zone is the most common type of zone and is used to map domain names to IP addresses. When a user or application tries to access a website, the DNS system performs a forward lookup by querying the forward lookup zone to get the corresponding A record or the A record. A reverse lookup zone is used to map IP addresses back to domain names. This is the opposite of the forward lookup process. In reverse lookup, the query is initiated with an IP address, and the goal is to find the corresponding PTR, pointer record, that maps the IP address to a domain name. Reverse lookup zones are typically used for reverse DNS lookups, which are commonly used in email systems to validate the source of an email. A DNS zone file is a simple text file that contains all the DNS records for a particular zone. It's used by the DNS server to resolve domain names for the zone. A typical DNS zone file includes SOA record, start of authority, which specifies the primary authoritative DNS server for the zone, along with other information like the email address of the domain administrator and timing parameters. NS records, name servers, specify the authoritative DNS servers for the domain. An A record maps a hostname to an IPv4 address. An AAA record maps a hostname to an IPv6 address. An MX record specifies the mail exchange servers for the domain. A key name record specifies alias names for a domain. A PTR record is used for reverse DNS lookups. A TXT record can contain arbitrary text, often used for verification or for settings like SPF in email. Zone transfer is the process of copying DNS zone data from a primary DNS server to a secondary DNS server. AXFR, full zone transfer, is a complete transfer of all zone records from the master to the slave server. XFR, incremental zone transfer, transfers only the changes made since the last zone transfer, which reduces load on the network. Zone delegation is the process of delegating authority over a subdomain to a different DNS server. It involves creating NS records that point to the DNS servers responsible for the subdomain. For example, a domain example.com may delegate responsibility for a subdomain sub.example.com to a different DNS server by adding an NS record for sub.example.com in the parent zone, example.com. DNSSEC, DNS security extensions, add security to DNS by enabling authentication of DNS data, preventing attacks like cache poisoning and man-in-the-middle attacks. Access control is important as DNS zone files should be protected from unauthorized access, as they contain important configuration data. Proper permissions must be set on DNS server configurations. To prevent unauthorized replication of zone data, zone transfers should be restricted to authorized DNS servers using IP-based ACLs, access control lists. In DNS, a zone is a portion of the DNS namespace managed by a DNS server. It contains DNS records that map domain names to IP addresses, define mail servers, and provide other essential data. There are different types of zones, such as primary, secondary, and subzones, and DNS servers use zone files to store and manage these records. Zones are crucial for the resolution of domain names to IP addresses, ensuring the correct routing of traffic across the internet and private networks. WINS is Microsoft Name Resolution Service, used primarily in Windows-based networks to map NetBIOS names to IP addresses. It was commonly used in Windows NT, Windows 2000, and earlier versions of Windows for networks that still relied on the NetBIOS over TCP/IP protocol. WINS allows clients to resolve NetBIOS names to IP addresses, similar to how DNS resolves domain names to IP addresses. WINS servers maintain a dynamic database of these mappings, allowing devices on network to locate each other. Computers register their NetBIOS names with a WINS server when they start up and renew their registration periodically. WINS servers can replicate data with other WINS servers, providing redundancy and ensuring up-to-date name resolution across larger networks. Before the widespread use of DNS for all network name resolution, WINS was the preferred method for resolving NetBIOS names to IP addresses, especially in local area networks. WINS was particularly useful in environments where legacy applications or older Windows operating systems needed to communicate over a network. As DNS became more widely adopted, WINS was gradually phased out. Today, WINS is considered obsolete and is rarely used in modern networks, as most name resolution is handled by DNS. UNC is a standard for identifying network resources by using a uniform naming convention. It allows computers to access shared resources over a network without needing to know the underlying server's IP address. A UNC path typically follows the format source server name shared resource path or TUF file. UNC path allow users to access network shares such as file servers, printers, or other shared resources by hostname or IP address, rather than relying on mapped network drives or static IP addresses. In a network, you can use UNC path to access shared folders or files. For example, JID file server documents report. DOCX accesses the report.docx file in the documents folder on the file server. UNC paths eliminate the need for mapping network drives, making access to resources more flexible. UNC is supported across various Windows versions and can also be used with other operating systems that support SMB CFS protocols. A UNC path remains consistent regardless of where the system is in the network. Users can type a UNC path into Windows Explorer to access a shared directory or access a shared printer using a UNC path like n.printserver do printer1. WIN was used in legacy Windows networks for resolving NetBIOS names to IP addresses. It has been largely replaced by DNS, which now handles both domain name and name resolution for modern networks. UND is a standardized way to access network resources such as shared files, printers, and other resources via network paths. It simplifies network resource access without requiring IP addresses or mapped drives. In Active Directory, AD, an organizational unit, OU, is a container object that allows administrators to organize and manage AD objects such as users, computers, groups, and printers in a logical way within a domain. OUs provide a means of delegating administrative control and applying group policies, GPOs, to subsets of objects within a domain. OUs are used to create a hierarchical structure for organizing objects in AD. They allow you to structure your AD objects in a way that makes sense for your organization, such as by department, location, or business unit. For example, you might have OUs for the HR department, finance, sales, etc. You can delegate specific administrative tasks or permissions to users or groups at the OU level. This allows you to give local admins control over certain objects, user accounts in a specific OU, without giving them control over the entire domain. A manager might be delegated administrative rights to manage users within the sales OU, but not in other parts of the domain. Group policy objects, GPOs, can be applied to OUs to enforce specific settings and policies for all objects within that OU. This is an essential feature for applying security settings, software installation, login scripts, and other configurations to specific groups of users or computers. You might apply a password policy to the HR OU or deploy software to all computers in the IT OU. OUs are flexible and scalable. As your organization grows, you can create more OUs and sub-OUs, which helps maintain an organized structure that reflects the changes in your organizational structure. OUs provide a way to logically separate objects. For instance, user accounts for employees in the marketing department can be placed in the marketing OU, and their permissions and policies can be managed separately from other departments. OUs can be nested. You can create a hierarchy of OUs within a domain. For example, you can have a top-level OU for each department, and within each department you have sub-OUs for users, computers, groups, etc. This allows for fine-grained delegation and easier management as the organization grows. OUs are often compared to other containers in Active Directory, such as domains and sites. An OU exists within a domain. OUs are primarily for organizational structure, delegation of administrative rights, and applying group policies. You can create as many OUs as needed and structure them as per your organization's needs. A domain is a larger unit in AD that contains all the objects and OUs within it. A domain is used for security management and authentication. It serves as a boundary for user accounts, computers, and group policy objects, GPOs. AD has some default containers like users, computers, domain controllers that cannot be deleted or renamed. These containers are designed to store specific types of objects. The user's container stores all user accounts, but it's not as flexible or customizable as an OU, and you cannot apply GPOs to it. You can create and manage OUs using the following tools. The ADUC console is the most common tool for managing OUs. You can create, move, or delete OUs here. Right-click on a domain or an existing OU, and select New, Organizational Unit to create a new OU. PowerShell is a powerful scripting language and tool for managing Active Directory. You can create OUs with the new AD Organizational Unit CMD-let. Once you've created an OU, you can apply GPOs to it using the Group Policy Management Console, GPMC. Common use of OUs include organizing users and resources based on the organizational departments, creating OUs for different regions or office locations, assigning specific administrators or support staff to manage only a subset of the AD objects within an OU, and applying specific group policies to different OUs based on their role or location. Best practices for using OUs in Active Directory include avoiding overnesting, delegating permissions properly, using group policies wisely, implementing clear naming conventions for OUs, and limiting group policy inheritance. An organizational unit, OU, in Active Directory is a container used to organize objects such as users, groups, and computers in a domain. OUs allow for delegation of administrative control, the application of group policies, and more logical structure for managing resources. They can be nested to create a hierarchical structure, but should be used carefully to maintain simplicity and avoid overly complex configurations. OUs provide flexibility, scalability, and control in Active Directory environments. In Active Directory, default containers are the unsung heroes of organization. These predefined locations, like users, computers, and domain controllers, automatically house objects when no specific organizational unit is assigned. For instance, when you create a new user without designating an OU, they land in the user's container. While it's convenient, it's not always the best practice. These containers don't allow for group policy application, limiting your ability to enforce security settings effectively. Instead, moving objects to custom OUs enhances organization and delegation. You can easily manage permissions and apply specific policies tailored to your needs. Remember, these default containers are fixed and system managed, so understanding their role is crucial for effective AD management. By leveraging OUs, you can create a structured environment that supports your organization's goals. In Active Directory, default containers are essential, predefined spaces where objects land if they aren't assigned to a specific organizational unit. Think of the user's container, where user accounts like user1 or john.doe are automatically placed. It's convenient, but for better organization and group policy application, it's smart to create custom OUs. Then there's the computer's container, which holds all the machines joined to the domain. While it's tempting to leave them there, grouping them into dedicated OU streamlines management. Don't forget the domain controller's container, strictly for domain controllers like DCS01 and DCS02. The built-in container houses critical administrative groups like administrators and domain admins, vital for security but not for everyday tasks. The system container is more behind the scenes, storing system policies and configurations. Understanding these containers helps you navigate AD more effectively, ensuring your objects are organized, secure, and manageable. The Foreign Security Principles container manages objects from trusted external domains. In Active Directory, default containers are essential, predefined spaces where objects land if they aren't assigned to a specific organizational unit. In Active Directory, AD, default containers are predefined, system-managed organizational units, OUs, where certain types of objects are stored if no specific organizational unit, OU, is designated. These containers are set by Active Directory and have fixed names. They cannot be deleted, renamed, or moved. Each container is associated with a specific type of object in AD. Understanding these containers is essential for AD management, as they are used when objects are created without being assigned to a custom OU. Here's a breakdown of the default containers in Active Directory. The user's container is where user objects are placed by default when they are created in AD without being assigned to a specific OU. This container holds user accounts and also group objects. While you can create new users directly in the user's container, it's usually better to assign users to an appropriate OU for better organization and group policy application. The computer's container holds computer accounts created when they are joined to the domain, but aren't assigned to a specific organizational unit. Computer objects, which represent physical or virtual machines that are members of the domain, are stored here. Like the user's container, objects in the computer's container can be managed, but it's generally more efficient to place computers into dedicated OUs. The domain controller's container is used to store computer objects of domain controllers within the AD domain. This container holds the objects of all the domain controllers that are part of the AD domain. The domain controller's container is strictly reserved for domain controller objects. It cannot be used for other types of objects like users or workstations. The built container holds user and group objects that are used for administrative and built-in roles within the domain. These objects are automatically created by Active Directory. Groups such as administrators, guests, enterprise admins, domain admins, and backup operators are placed in this container. While these groups are primarily for built-in administrative tasks, they should not be used for regular organizational purposes. The system container stores system-related objects, such as certain system policies and schema configurations. Various system-specific objects, like certain policies and security-related objects, are stored here. This container is largely invisible to regular users or administrators who don't work with the inner workings of Active Directory. This container is used to store foreign security principles. Foreign security principles represent security objects from trusted domains outside the current domain. Security principles that have been imported from trusted external domains are stored here. This container helps in managing trust relationships and objects from external forests or domains. Key characteristics of default containers include fixed locations, as these containers are always located within the domain root and have fixed names. They are not customizable, meaning they cannot be renamed, deleted, or moved to other parts of the AD structure. These containers are managed by the system and are not intended for regular use in the same way that organizational units, OUs, are. Why should you care about default containers? When you create objects in AD and don't assign them to a specific OU, they are placed in one of these default containers. Knowing where these objects end up helps you understand where the objects reside and how to manage them. Default containers like users and computers do not allow the application of group policy objects, GPOs, directly. If you want to apply specific policies to users or computers, it's recommended to place them in custom OUs. By default, objects placed in these containers lack the level of delegation and organization that you can achieve by assigning them to OUs. Although you can't modify or delete default containers, you can move objects out of them into custom OUs for better management. You can do this using Active Directory Users and Computers, ADUC. By locating the object in the default container, right-clicking on the object and selecting Move. You can also use PowerShell to move objects. Default containers have fixed, predefined names, while organizational units, OUs, have fully customizable names. Default containers do not allow delegation of control, whereas OUs allow full delegation of control. Default containers cannot directly apply GPOs, while OUs can apply group policy objects. Default containers are managed by the system, while OUs are managed by AD admins, allowing for fine-grained control. In summary, default containers in Active Directory are system-managed locations where objects are placed if no specific organizational unit is assigned. These containers include users, computers, domain controllers, built-in system and foreign security principles. While they cannot be renamed, deleted, or moved, they serve an important role in AD management by storing objects and handling system-related tasks. To enhance organization, security, and delegation, it's often best to move objects into custom OUs. Delegating control in Active Directory at the organizational unit level is crucial for effective administrative management. It allows you to assign specific tasks, like user management or group memberships, to designated users or groups without giving them full domain access. This enhances security by limiting permissions, reduces the risk of unauthorized changes, and boosts efficiency by empowering department heads to manage their own areas. You can delegate permissions through the Active Directory Users and Computers console or PowerShell. Common tasks include creating and managing user accounts, resetting passwords, and modifying group policies. Always adhere to the least privilege principle. Grant only the permissions necessary for users to perform their roles. Regularly review these delegations to ensure they remain relevant and secure. By doing this, you maintain a well-organized and secure Active Directory environment. Delegating control in Active Directory, AD, is an important aspect of administrative management. It allows you to assign specific administrative tasks to other users or groups without granting them full access to the entire domain or other OUs. This can be done at the organizational unit OU level, ensuring that administrative rights are granted on a more granular and controlled basis. When you delegate control in an OU, you assign specific tasks like user management or group management to a specific user or group for that OU without giving them rights to other parts of directory. This is essential for efficient administration, especially in larger organizations with different departments or teams that need different levels of access to AD objects. Why delegate control? First, security. Limiting permissions to only what's necessary helps reduce the risk of unauthorized access or changes to AD objects. Second, efficiency. It enables department heads, regional IT staff, or support teams to manage their own areas of responsibility, like user accounts or group memberships, without needing full administrative privileges. When delegating control, there are several predefined permissions that you can assign. Some common permissions that can be delegated include creating, deleting, and managing user accounts, resetting user passwords, managing group membership, creating, deleting, and managing groups, modifying group policy objects, GPOs, and viewing and modifying permissions. To delegate control in Active Directory using the Active Directory Users and Computers ADUC console, first, open ADUC by pressing Windows plus R, typing dsa.msc, and pressing Enter, or opening it from the Administrative Tools menu. Next, navigate to the organizational unit, OU, you want to delegate control over by expanding the domain in the left pane. Right-click the OU and select Delegate Control from the context menu to open the Delegation of Control wizard. In the wizard, click Add to select the user or group you want to delegate control to. If the user or group is not listed, you can type their name or browse the directory to find them. Click Next after selecting the appropriate user or group. You'll then be presented with a list of common tasks you can delegate. Select the tasks that you want a user or group to be able to perform on objects in the OU. Alternatively, you can choose Create a custom task to delegate for more specific control. You can also use PowerShell to delegate control by modifying permissions for specific objects or OUs. For example, to grant reset password permission to a user on a specified OU, you can use the command add AD permission, identity OU user, extended rights, reset password. This command grants the HR admin user the right to reset passwords for users in the HR OU. If you want to create more specific custom permissions beyond the common tasks listed in the Delegation of Control wizard, you can choose Create a custom task delegate during the delegation process. You can then select permissions for specific objects in the OU and define which permissions you want to grant on those objects. These permissions can be set at the object level or the container level. When delegating control, it's important to consider the least privilege principle, always granting users the permissions they need to perform their tasks while avoiding unnecessary or overly broad permissions. Be aware that permissions assigned at the OU level can be inherited by sub-OUs unless explicitly blocked. Regularly review the delegated permissions to ensure they align with the current needs of the organization and maintain a security audit trail for delegation actions. For delegation of control, it's best to add users to security groups rather than delegating control to individual users, making management of permissions easier and more scalable. Best practices for delegating control in Active Directory include using security groups, limiting permissions to specific OUs, following the least privilege principle, regularly reviewing delegated permissions, and documenting your delegations. Delegating control in Active Directory at the OU level provides a way to assign administrative rights to users or groups or specific objects in the OU, allowing for granular control without granting broader administrative rights to the entire domain. This helps maintain security, improves operational efficiency, and ensures accountability. The process can be done using the delegation of Control Wizard in Active Directory users and computers, ADUC, or via PowerShell for more specific tasks. It's important to follow best practices such as using security groups, limiting permissions to the necessary tasks, and reviewing delegated control regularly. In a Windows-based network environment, accounts can be categorized as either domain accounts or local accounts. These two types of accounts serve different purposes and are used in different scenarios within an IT infrastructure. A domain account is an account that is part of a domain within a Windows Server Active Directory environment. It is used for accessing resources that are part of the domain. Key features of domain accounts include centralized authentication, meaning they are stored and managed centrally in the Active Directory database on domain controllers. This allows users to authenticate across the entire network, regardless of the machine or resource they are accessing. Another feature is single sign-on, where once the user logs in with their domain account on one computer, they can access other network resources, servers, and services without needing to log in again. Domain accounts can also be used to log into any computer or server that is part of the same domain, as long as the user has been granted the necessary permissions. Additionally, a domain account has a roaming user profile, allowing user settings to be accessed from any machine in the domain. Domain accounts are subject to group policy objects, which allow administrators to force security settings, software installations, and configurations on user accounts across the domain. Admins can manage domain accounts centrally from Active Directory users and computers, or through PowerShell commands. For example, a user named John Doe has a domain account called john.doecompany.com. John can log into any workstation within the domain, access shared folders, printers, and other resources, all using the same domain credentials. On the other hand, a local account is an account that is created and stored on a local computer rather than an Active Directory. Local accounts can only be used to log into the specific computer on which they are created. Key features of local accounts include local authentication, as they are stored in the local security database of the computer. They have a limited scope, meaning a local account can only be used to log into the local computer or device where it exists. Local accounts are independent of the domain, so they cannot access domain resources unless a corresponding domain user account is granted permissions. Local accounts are not subject to the domain's group policy settings, but they can still have their own local security settings and restrictions. Local accounts can be managed from the local computer via the local user and groups management console or through command line tools like NetUser. For example, a computer has a local account called admin with a username localadmin. This account allows the user to log into the machine itself and manage local settings, but it cannot be used to access domain resources unless specific permissions are granted. The differences between domain and local accounts include scope, authentication, profile, management, group policy, access to resources, and account type. Domain accounts are available across the domain on multiple computers, while local accounts are available only on the specific machine where created. Domain accounts are authenticated by domain controllers, while local accounts are authenticated locally by the computer SAM database. Domain accounts have a roaming profile, whereas local accounts have a local profile. Domain accounts are managed centrally via Active Directory, while local accounts are managed locally on the individual machine. Domain accounts are subject to domain group policy, while local accounts are not. Domain accounts can access resources across the domain, while local accounts can only access resources on the local computer. Domain accounts are primarily used for user accounts, service accounts, etc., while local accounts are used for individual user access to a specific computer. When to use domain accounts versus local accounts. Domain accounts are best for users who need access to multiple computers or resources within the domain. Remote workers need to access domain resources from any machine. Environments where centralized management of user account and security settings is needed, and users who need to benefit from single sign-on across multiple services. Local accounts are useful for isolated systems that don't require domain access, administrator access to a machine when no domain account is available, security or legacy systems that don't support domain membership, and offline access where a machine is not connected to the network but needs to be used for local tasks. In summary, domain accounts are used within a network environment where resources and user management are centralized via Active Directory. They allow users to authenticate across multiple machines and access shared resources, and they are subject to domain-wide policies. Local accounts are used for access to individual computers and are stored locally on each machine. They cannot access domain resources and are generally used for local administrative or isolated accounts on non-domain joined computers. Choosing between a domain account and a local account depends on your need for centralized management, access to domain resources, and local. In the realm of Active Directory, computer and server accounts play a crucial role in maintaining a secure and efficient network. Each computer is represented as an object, allowing administrators to manage permissions and policies seamlessly. These accounts authenticate devices, ensuring only authorized machines access network resources. Think of it as a digital bouncer at a club. Only the right guests get in. Server accounts, on the other hand, are like the VIPs. They run services and applications, requiring specific permissions to function properly. By organizing these accounts into organizational units, we can streamline management and apply group policies effectively. This structure not only enhances security, but also simplifies troubleshooting. In essence, understanding these accounts is key to mastering network administration and ensuring a robust IT environment. In the realm of Active Directory, computer and server accounts play a crucial role in maintaining a secure and efficient network. In Active Directory, groups are essential for managing users and resources efficiently. There are two main types: security groups and distribution groups. Security groups control access to resources like files and printers, allowing administrators to assign permissions effectively. For instance, a domain admins group has full control over the domain, while a sales department group grants access to shared resources for sales staff. On the other hand, distribution groups are all about communication, primarily used for email distribution without any security attributes. Now let's talk about group scopes. Domain local groups are perfect for managing resources within a single domain, while global groups can include users from the same domain but can be used across others for permissions. Universal groups take it a step further, allowing access across multiple domains and forests, making them ideal for larger organizations. Nesting groups add another layer of flexibility, enabling you to create complex access control strategies. Understanding these concepts is crucial for effective network management. In Active Directory, groups are essential for managing users and resources efficiently. There are two main types: secure groups and distribution groups. In Active Directory, group scopes are essential for managing access across domains and forests. We have three main types: domain local, global, and universal groups. Domain local groups are perfect for controlling access to resources within a single domain, allowing members from any domain in the forest. Think of domain local groups as your go-to for file shares or printers in one domain. Global groups, on the other hand, are limited to members from the same domain, but they can be used across domains and added to domain local groups. This makes them ideal for organizing users by department or role. Finally, universal groups are the most flexible, allowing members from any domain and granting access to resources across multiple domains. They're perfect for larger organizations that need consistent access control. By strategically using these group scopes, you can streamline access management and enhance security in your Active Directory environment. Group nesting refers to the practice of placing one group inside another group. In Active Directory, AD, this allows you to create more complex group hierarchies, making it easier to manage access permissions and administrators. By nesting groups, you can manage security and permissions in a more flexible and scalable way, allowing for easier delegation and reduced administrative overhead. Let's explore group nesting in detail. Active Directory supports group nesting to help simplify management by adding groups as members of other groups. The ability to nest groups enables you to create role-based group structures and hierarchical permission models. For example, you can create a global group representing users in the HR department, a domain local group for managing access to HR-specific resources, and you can nest the HR global group into the domain local group to give all HR users access to the resources without having to add each individual user. Group nesting is generally applicable for security groups, where members need to be granted access to resources. In AD, you can nest groups within security groups, domain, local, global, or universal. However, distribution groups cannot be nested inside security groups. Security groups in AD are the most common type used for group nesting because they are used to assign permissions to resources like file shares, applications, or printers. You can nest one group inside another group to manage resource access efficiently. Global groups can be added to domain local groups. Universal groups can be added to domain local or global groups. Domain local groups cannot be added to other groups because they are used to control access to resources within the same domain. For example, a group called HR Department, which is a global group containing users from the HR domain, and the domain local group called HR Resources, which is a domain local group that controls access to our file shares. You can add the HR Department global group to the HR Resources domain local group so that all users in the HR domain can access the file share. In this example, the global group HR Department contains users from the same domain and is nested inside the domain local group HR Resources. All members of HR Department inherit the HR Resources. When it comes to group nesting, it's important to follow best practices to avoid potential issues related to replication, permissions inheritance, and administration complexity. Here are some best practices. First, nesting global groups into domain. Local groups is the most common and recommended nesting scenario. Global groups are used to organize users by role or department. Domain local groups are used to additions to resources within a specific domain. For example, a global called sales team can be added to a local group called sales resources to control access to sales resources within the sales domain. Second, use universal groups for cross-domain permissions. When you need to assign permissions across multiple domains, nest global groups inside local groups. You can then add the universal domain local group in the target domain. For example, a global group called HR team from the HR domain could be nested inside a universal group called all managers. And all managers can be added to a domain local group in the sales domain to give managers access to resources in the sales domain. Third, limit nesting depth. Avoid excessive nesting of groups, as it can make it harder to manage permissions and troubleshoot issues. A group should not be nested too deep, as this can lead to replication issues or confusion about group memberships. The best practice is to keep nesting simple and to use groups at appropriate levels of the hierarchy. And should be avoided. Fifth, consider the impact on replication. Nested groups, especially universal groups, are replicated across all domain controllers in the forest. This can introduce overhead in terms of replication traffic. For large organizations with many nested groups, careful planning is required to ensure efficient replication and avoid performance degradation. Lastly, document group structures. With group nesting, it's easy to lose track of which groups are members of others. This can create administrative challenges in larger environments. Always document your group nesting strategies and keep track of group memberships for efficient management and troubleshooting. Here are some nesting scenarios and how they are typically used in Active Directory. In scenario 1, department-based group nesting for simple access control. You can have a global group called HR staff, which contains users in HR, and a domain local group called HR resources, which manages HR-specific resources. You can add HR staff to HR resources to grant all HR users to the HR file server. In this case, HR staff is a global group, and HR resources is a domain local group. In Windows Server, roles and features are two key concepts used to describe the various functionalities that a server can provide. These elements can be installed, configured, and managed to tailor the server's capabilities to meet the needs of the organization. A role defines the primary function that a server will perform. These are predefined server configurations that determine the services the server will provide to clients and users in a network. Roles typically represent core services that a server can offer in an enterprise environment. Common Windows Server roles include Active Directory Main Services, ADDS, which provides directory services, including authentication and authorization for users and devices within a network. DNS Server, which resolves domain names to IP addresses, allowing the network to route traffic correctly. DHCP Server, which automatically assigns IP addresses to devices on the network, ensuring devices can communicate without manual configuration. File and Storage Services, which manages file sharing, storage, and data access on the server. Web Server, IIS, which hosts web applications and services. Print and Document Services, which provides printing services and manages printers within the network. Hyper-V, a virtualization platform that allows the creation and management of virtual machines. And Remote Desktop Services, RDS, which provides users with remote access to desktops and applications hosted on the server. Features are optional components that can be added to the server to enhance its functionality, but are not essential for the core operation of the server. Features typically supplement or extend the capabilities provided by the roles. Common Windows Server features include Server Core, a minimal installation option that reduces the server's resource footprint and attack surface. Failover clustering, which provides high availability for services and applications by grouping multiple servers together in a cluster. Windows Server Backup, which provides backup and restore functionality for the server. BitLocker Drive Encryption, which encrypts the server's hard drives to protect data. Windows Defender Antivirus, which provides security against malware and other threats. Group Policy Management, which allows centralized management of settings for users and computers within Active Directory environment. And SMB Direct, which provides high-performance file sharing using RDMA. Key differences include that roles are the primary services a server provides, such as DNS Server, Hyper-V, and ADDS, while features are optional components that enhance or supplement the server's capabilities, such as BitLocker and failover clustering. In modern Windows Server versions, roles and features are managed through tools like Server Manager or PowerShell, where administrators can add or remove them based on organizational requirements. In Windows Server, roles and features are two key concepts used to describe various functionalities that a server can provide. These elements can be installed, configured, and managed to tailor the server's capabilities to meet the needs of the organization. A role defines the primary function that a server will perform. Managing a mail server in Windows Server is like having a powerful communication hub at your fingertips. With features like Exchange Server, you can streamline email management, enhance security, and improve collaboration. Imagine having a centralized platform where you can easily set up mailboxes, manage user permissions, and implement robust anti-spam measures. The integration with Active Directory simplifies user management, allowing for seamless access control. Plus, with features like shared calendars and task lists, teamwork becomes effortless. And let's not forget about the mobile access. Employees can stay connected on the go, ensuring productivity never takes a hit. With built-in compliance tools, you can also safeguard sensitive information and meet regulatory requirements. Overall, the Mail Server feature in Windows Server is not just about sending emails. It's about creating an efficient, secure, and collaborative environment that drives your organization forward. When we talk about the key components of Email Server on Windows Server, we can't overlook the Mail Transfer Agent, or MTA. This is the powerhouse that sends and receives emails using protocols like SMTP. Then we have the Mail Delivery Agent, or MDA, which take care of storing incoming emails and delivering them to user mailboxes, often utilizing POP3 or IMAP protocols. Next up is the Mail User Agent, or MUA, the interface we all know and love. Think Microsoft Outlook or the Mail app. Now, at the heart of many Windows Server environments is Microsoft Exchange Server. It's not just an email server. It's a comprehensive solution offering email management, calendaring, contact management, and collaboration tools. With Exchange, you get centralized management of email accounts and policies, making life easier for IT admins. Plus, it allows users to manage appointments and share calendars seamlessly. And let's not forget about public folders, which enable shared access to emails, calendars, and documents across the organization. It's all about enhancing productivity and collaboration in the workplace. SharePoint Server in Windows is like a digital Swiss Army knife for organizations. It's a powerful platform that allows teams to collaborate seamlessly, manage documents, and share information securely. Imagine a central hub where you can create websites, store files, and even automate workflows, all tailored to your specific needs. With SharePoint, you can set up team sites for projects, making it easy to track progress and share updates. Its robust search functionality helps you find documents in seconds, save you time and frustration. Plus, the integration with Microsoft 365 means you can work on files in real time with colleagues, no matter where they are. Security is a top priority, so you control who sees what, ensuring sensitive information stays protected. Whether you're a small business or a large enterprise, SharePoint Server empowers you to enhance productivity and foster collaboration, transforming the way you work together. IIS, Internet Information Services, is a web server developed by Microsoft for hosting and managing web applications, websites, and services on Windows Server. IIS is an essential tool for providing HTTP-based services, such as websites, web applications, FTP services, and more. It's a flexible, extensible platform that supports various web technologies like ASP.NET, PHP, and others, and it can also be used to host RESTful APIs, static content, and media. IIS provides web hosting capabilities for web applications, websites, and services. It supports modern web frameworks such as ASP.NET, PHP, and Node.js, enabling the hosting of dynamic web pages. It offers tools for managing web applications and their configurations, including site-specific settings, logging, and security. IIS has built-in security features like SSL, TLS encryption, HTTPS, IP address and domain name restrictions, and authentication mechanisms. Windows authentication, basic authentication, digest authentication. Request filtering allows administrators to control which types of HTTP requests are allowed based on URL and request headers, offering protection against malicious requests. The URL rewrite module allows the redirection of URLs to secure or optimized versions, supporting SEO and security policies. IIS includes support for FTP, File Transfer Protocol, which allows users to upload or download files securely to and from the server. It supports FTP over SSL, TLS, FTPS for secure file transfers. IIS uses application pools to isolate web applications. This enhances performance, security, and reliability by allowing each application to run in its own environment with its own worker process. If one application crashes, it doesn't affect others within the same server. IIS includes detailed logging capabilities, including logging requests, errors, and other relevant data. It integrates failed request tracing, FRT, for troubleshooting and diagnosing complex issues. IIS logs can provide detailed insights into client requests, server response times, error codes, and much more. IIS can integrate with Windows Network Load Balancing, NLB, for distributing web traffic across multiple web servers in a farm. It also supports integration with Application Request Routing, ARR, for advanced load balancing features, such as HTTP request routing, content caching, and secure communications. IIS supports compression of static content, reducing bandwidth usage, and improving load times for clients. Similar to static content, dynamic content, e.g. ASP.NET pages, can also be compressed to optimize network performance. IIS supports WebSockets, a protocol that enables bi-directional communication between client and server over a single, long-lived connection, essential for real-time applications. IIS provides the IIS Manager, a graphical user interface (GUI) for managing websites, applications, and server-wide settings. You can also manage IIS remotely using remote administration tools. IIS supports easy deployment of web applications via the Web Deploy tool, which allows web applications and sites to be moved between environments, development, staging, production. Web Deploy enables the automated deployment of web applications, databases, and configurations. IIS provides ASP.NET, PHP, and Node.js support, which makes it suitable for hosting a wide variety of web applications. ASP.NET Core and other modern .NET applications are supported natively in IIS. Here are some of the most commonly used network ports, along with their associated services or protocols. Port 20 and 21 are used for FTP, with port 21 serving as the control port for commands and port 20 for data transfer. Port 22 is used for SSH, which allows secure remote login, command execution, and file transfer through SFTP and SCP. Port 23 is used for Telnet, which is for unencrypted remote login, though it's not recommended due to security concerns. Port 25 is used for SMTP, which sends emails from a client to a mail server or between mail servers. Port 53 is used for DNS, resolving domain names to IP addresses. Port 80 is used for HTTP, which handles non-secure web traffic. Port 110 is for POP3, allowing email client to retrieve emails from a mail server. Port 153 is used for IMAP, which helps email clients retrieve and manage emails on a mail server. Port 443 is for HTTPS, securing web traffic by encrypting data between the web server and the browser. Port 3389 is used for RDP, enabling remote desktop connections to Windows systems. Ports 161 and 162 are for SNMP, with port 161 used for SNMP agents and port 162 for SNMP traps. Port 69 is used for TFTP, which facilitates simple file transfers, often for network reading. Port 119 is for NNTP, allowing reading and posting of newsgroup articles. Port 445 is used for Microsoft Directory Services and SMB over TCP. Port 514 is for Syslog, logging messages from devices to a central Syslog server. Ports 5060 and 5061 are for SIP, with port 5060 for non-encrypted communications and port 5061 for encrypted communications using TLS. Port 53432 is used for PostgreSQL database management, while port 3306 is for MySQL database connections. Port 88 is commonly used as an alternative to port 80 for web servers, often for testing or non-standard services. These are just a few of the most commonly used ports, and each one serves a specific role in facilitating communication over a network. Many other ports are used for specialized purposes in different protocols and applications. SCA Certification Authority. Server in Windows Server is a component of the Public Key Infrastructure (PKI) that issues, manages, and revokes digital certificates. These certificates are used for secure communication, authentication, and encryption within an organization's network. The CA server issues digital certificates to users, devices, and applications to verify their identity. These certificates are used for securing network traffic, email encryption, and user authentication. The CA server maintains a certificate revocation list, CRL, which tracks certificates that have been revoked before their expiration date due to compromise or other issues. The CA provides a mechanism for devices and users to request and receive certificates. This process can be automated using tools like auto-enrollment in Active Directory environments. The CA server is a key part of a PKI, where it helps in managing the private and public keys that are used for encryption and decryption of data. There are different types of CA servers. A root CA, which is the top-level CA that issues certificates to subordinate CAs. An intermediate CA, which is signed by the root CA and can issue certificates to end users or devices. And subordinate CA, which is a lower-level CA authorized by the root or intermediate CA to issue certificates. Use cases in Windows Server include SSL TLS encryption for securing web traffic on web servers, email security for encrypting and signing emails, user authentication via smart cards or other certificate-based methods, and VPN access for enabling secure connections to remote systems. Windows Server provides the Active Directory Certificate Services (ADCS) role, which allows you to deploy and manage a CA server. This role enables organizations to integrate PKI-based security for a variety of use cases within the enterprise network. A remote access server, RAS, is a server that allows remote users to connect to a private network securely from a remote location. It enables employees, contractors, or users to access network resources such as files, applications, or internal websites over the internet or other networks, typically via virtual private network, VPN technologies, dial-up connections, or direct remote desktop access. In Windows Server environments, Remote Access Server is commonly managed through Remote Access role, which includes several key services and functionalities. The most common use of RAS is to provide secure VPN access. This allows remote users to securely connect to the corporate network over the internet. It supports different VPN protocols like PPTP, L2TP, IPv2, and SFTP, ensuring that traffic between the remote user and the network is encrypted and secure. Direct Access is a feature in Windows Server that provides seamless and automatic secure access to the corporate network for Windows 7, 8 to 10 clients without requiring a traditional VPN connection. It establishes an always-on encrypted connection between client and the server, working when the user is connected to the internet and automatically enabling access to internal resources without needing to manually initiate a VPN connection. RRS allows a Windows Server to function as a remote access solution, supporting both VPN and dial-up connections. It can be configured to route network traffic between different networks or subnets, connecting remote users to the internal network. RRS supports NAT for shared internet access and IP routing for multiple network segments. NAP is a policy enforcement tool that ensures remote clients meet security requirements before allowing them to connect to the corporate network, helping ensure that only compliant and secure devices can access network resources. Remote Desktop allows users to connect to a Windows desktop remotely, running the full desktop experience. It is a feature that can be configured on a RAS to provide users with access to Windows-based applications or desktops hosted on the server. RDS also supports multiple user sessions and can be used for accessing centralized applications. RAS servers authenticate and authorize users attempting to connect to the network, typically using protocols such as RADIUS or EAP for VPN connections. Integration with Active Directory allows for user authentication, group-based access control, and the enforcement of security policies for remote users. The RAS server can assign IP addresses dynamically to remote clients connecting via VPN or dial-up using DHCP, ensuring clients are assigned valid IP addresses from a pool defined by the server. It ensures proper routing and access to network resources. The server can manage traffic and control bandwidth usage for remote connections, ensuring that remote users do not overwhelm the network with excessive data traffic. Traffic shaping policies can be implemented to prioritize important traffic over less critical traffic. Remote access servers typically include logging and monitoring capabilities to track connection attempts, successful logins, and any failures, which is essential for security auditing and troubleshooting. Tools like Network Policy Server can be used for logging and policy enforcement, while third-party solutions may offer more advanced features like real-time monitoring or alerting. Modern remote access solutions can be integrated with multi-factor authentication methods to increase security when remote users are accessing the network. Types of remote access include VPN, which encrypts traffic over the internet, allowing users to securely connect to a private network. Direct access, a seamless, always-on VPN solution for Windows clients that automatically connects when the user is online. Dial-up connections, an older method for connecting to networks using a phone line. And remote desktop services, which enables users to connect to a desktop session hosted on the server. Use cases for remote access server include remote work, enabling employees working from home or traveling to access internal systems securely. Remote administration, allowing IT administrators to manage servers and network devices remotely. Branch office connectivity, allowing remote offices to securely connect to the central network. And client access, allowing external clients or contractors to access services or applications hosted internally. Security considerations include ensuring all remote access connections use strong encryption to protect data in transit, properly configuring firewalls to allow secure remote access while blocking unauthorized traffic, and using policies and access controls to restrict who can access which resources remotely. In Windows Server, the remote access role integrates these features, and administrators can configure VPN, direct access, and other services based on organizational needs. In a Windows Server environment, the Printer Management Server plays a crucial role in streamlining how we handle printers across network. Imagine a central hub where IT administrators can effortlessly manage printers, print queues, and drivers, all from one powerful interface. With the Print Management Console, you can monitor printer usage, troubleshoot issues, and ensure that the right drivers are deployed to client systems automatically. Queue management is another key feature, allowing users to pause or cancel their print jobs as needed, while administrators maintain order and efficiency. Security is paramount too. Permissions can be set to restrict access based on user roles, ensuring that only authorized personnel can use specific printers. Plus, with remote management capabilities, IT staff can oversee the entire print environment without being physically present. In essence, the Printer Management Server not only simplifies printer management, but also enhances security and efficiency, making life easier for everyone in the organization. In a Windows Server environment, the Printer Management Server plays a crucial role in streamlining how we handle printers across the network. Imagine a central hub where IT administrators can effortlessly manage printers, print queues, and drivers, all from one powerful interface. A Printer Management Server in Windows Server refers to the role or service responsible for managing printers and print queues within a networked environment. It's a component of Windows Server that enables centralized administration of printers, print devices, and print jobs across an organization's network. This feature is commonly used in environments where multiple printers are shared among users, and it helps IT administrators monitor, configure, and troubleshoot printer-related issues efficiently. In a Windows Server environment, the Print Server role acts as the management point for all printers within the domain or network. The Print Server allows IT administrators to share printers across multiple computers and manage printer queues, drivers, and printer settings. It ensures centralized management for installing, configuring, and deploying printers to clients in a corporate or enterprise environment. The Print Management Console, available in Windows Server, is a powerful tool that provides administrators with a centralized interface for managing printers and print servers across an organization. From this console, administrators can view all printers installed on the server, manage printer queues, and track printer usage. Printer drivers are crucial for communication between a computer and a printer. A print server helps manage different drivers for various printers across the network. The print server ensures that the appropriate drivers are available and can automatically deploy printer drivers to client systems. The print server can monitor and manage print queues. It ensures that print jobs are processed in order and manages any errors or issues that might arise in the queue. Users can also be given the ability to pause, resume, or cancel their print jobs through the print server. Once configured, printers on the print server can be accessed and used by clients without the need for each user to directly connect to each printer. Administrators can share printers with specific user groups, applying access permissions as needed. Administrators can set permissions and restrict access to printers based on user roles or groups. The server can be configured to only allow specific users or departments to use certain printers, ensuring more secure and efficient printer usage. The print server can also manage network printers, which are directly connected to the network rather than a single computer. This allows for efficient management of printers that are physically located in different parts of the organization. The print server role in Windows Server can be managed remotely using remote server administration tools or the Print Management Console, making it easier for administrators to manage the print environment without being physically present on site. Key benefits include centralized control over printers and print jobs, simplified deployment of printer drivers across network devices, reduced IT overhead by centralizing printer managed tasks, and better security through user-specific access control to printers. How it works. Printers are installed in the server, and drivers are configured. Printers are shared across the network, and users can add them to their machines using the network printer configuration. Users send print jobs to a printer queue on the server, which manages the order of printing. Administrators monitor printer statuses, troubleshoot, and manage permissions from a single location. In summary, the Printer Management Server in Windows Server centralizes the management of printers, improving efficiency, security, and ease of use for both administrators and users within a networked environment. NTFS permissions are crucial for managing security on Windows systems. They control who can access, modify, or delete files and folders. There are two main types: basic and advanced permissions. Basic permissions include read, write, and full control, allowing users to perform essential actions on files and folders. Advanced permissions take it a step further, offering granular control like traverse folder, which lets users access files without needing permissions on the parent folder. Inherited permissions streamline management by automatically applying parent folder settings to tiled files and folders, but you can override these if needed. Effective permissions show the actual access to users, combining explicit and inherited permissions. Assigning permissions to groups rather than individuals simplifies management, make it easier to control access for multiple users. Understanding these concepts ensures your files are secure, while allowing the right people to access what they need. NTFS permissions refer to the secure settings applied to files and folders in an NTFS, New Technology File System, formatted volume on Windows operating systems. NTFS permissions are used to control who can access, modify, and perform other actions on files and directories, providing a granular level of security and management. There are two types of permissions in NTFS: basic permissions and advanced permissions. Basic permissions, also known as standard permissions, can be assigned to users or groups to control the basic actions they can perform on a file or folder. For files, the permissions include read, which allows the user to view the contents of the file; write, which allows the user to modify the content of the file; read and execute, which allows the user to read the file and run it if it's an executable; modify, which allows the user to read, write, and delete the file, as well as modify its contents; and full control, which grants the user all permissions, along with the ability to change permissions and take ownership of file. For folders, the permissions include read, which allows the user to view contents of the folder and list the files in it. Write, which allows the user to add files and subfolders to the folder. Read and execute, which allows the user to view the contents of the folder and execute programs within it. Modify, which allows the user to read, write, modify, and delete files and subfolders within the folder. And full control, which grants the user complete access to the folder, including the ability to modify permissions and take ownership. Advanced permissions give more granular control and can be configured to refine the standard permissions. These permissions allow more specific control over what users can and cannot do with a file or folder. Advanced permissions options include traverse folder, execute file, which allows or denies the ability to access folders and files in a path without necessarily having permissions on the parent folder itself. List folder, read data, which grants permission to list the contents of a folder or read the contents of a file. Read attributes, which allows or denies access to the basic properties of the file or folder. Read extended attributes, which allows or denies access to additional metadata about a file or folder. Create files. Write data, which allows the user to create files within the folder or write data to a file. Create folders. Append data, which allows the user to create subfolders within a folder or append data to the file. Delete subfolders and files, which grants or denies permission to delete subfolders and files within a folder. Delete, which allows or denies the ability to delete the file or folder. Change permissions, which allows or denies the ability to modify permissions on the file or folder. And take ownership, which allows or denies the ability to take ownership of a file or folder. These permissions provide administrators with flexibility to specify exactly what users can do with a file or folder at a very detailed level. NTFS permissions can be inherited from a parent folder. This means that if you assign permissions to a parent folder, those permissions will automatically apply to all files and subfolders within it. By default, child objects inherit the permission of their parent folder. You can prevent inheritance by disabling the Allow Inheritable Permissions from Parent to Propagate to this object option. However, this can be more complex to manage, and it may require you to set permissions manually on individual files or folders. You can explicitly assign permissions to individual files and folders to override the inherited settings, and in this case, the new settings will be applied directly to the object. Effective permissions refer to the actual permissions a user has on a file or folder after combining all explicit permissions, inherited permissions, and group memberships. These permissions may differ from the individual permissions assigned to a user or group due to inheritance or explicit overrides. You can use the Effective Permissions tool to view exactly what access a user or group has on a particular file or folder. This is useful for troubleshooting when a user is having trouble accessing a resource. NTFS permissions can propagate through directories and subdirectories, allowing for efficient management of permissions across a network. If you assign permissions on a folder, these permissions are propagated down to all files and subfolders within that folder unless explicitly overridden. Subfolders inherit permissions from their parent folder unless you break the inheritance chain and assign permissions directly to the subfolder. If you block inheritance on a folder, it will no longer inherit permissions from its parent, but it will still retain its current permissions until you explicitly change them. In an NTFS environment, you typically assign permissions to users or groups. Users are specific individuals who have accounts on the system, while groups are a collection of users who share common permissions. Assigning permissions to groups is a more efficient method of managing access, as users in the group will automatically inherit the permissions associated with the group. It's considered a best practice to assign NTFS permissions to groups rather than individual users. This way, you can easily manage access for multiple users by simply adding or removing them from the group. For example, in a scenario where you want users to be able to view but not modify files in a folder, you would set folder permissions to give read and list folder contents permissions on the folder, and read permissions on files. In another scenario, if you want a specific user to have full control over a folder and its contents, you would set folder permissions to give full control to the user or admin group. Lastly, if you want users to be able to modify files but not delete them, you would set folder permissions to give modify or write permissions but deny delete permission. In conclusion, NTFS permissions are a powerful tool in Windows for securing access to files and folders. By using basic and advanced permissions, you can grant, restrict, and manage user access at a detailed level. Understanding how to combine and apply these permissions, whether they are inherited or explicitly set, helps ensure that your system remains secure while allowing authorized users the necessary access. policy in Windows Server is a game changer for administrators. Imagine having the power to manage operating system settings, applications, and user preferences across an entire network from a single point. That's what group policy objects, or GPOs, allow you to do. They come in two flavors: user configuration for personal settings and computer configuration for system-wide controls. Using the Group Policy Management Console, or GPMC, you can create, edit, and link these GPOs effortlessly. And let's not forget about GPO inheritance and precedence. Understanding how policies cascade down from domains to organizational units is crucial for effective management. When troubleshooting, tools like Resultant Set Policy and the Group Policy Result Wizard can help you pinpoint issues quickly. Remember, best practices suggest minimizing GPO links and test changes before a full rollout. With Group Policy, you can enforce security, streamline administration, and ensure compliance across your network. It's all about making your life easier while keeping everything secure and organized. Group Policy in Windows Server is a powerful feature that allows administrators to manage and configure operating system settings, applications, and user settings across a network of computers. It is based on Active Directory and enables centralized control over user and computer behavior. Group Policy can be applied to organizational units, sites, domains, or even at the local machine level. A Group Policy object, or GPO, is a collection of settings that can be applied to users or computers in a specific scope. A GPO can be linked to sites, domains, or organizational units. GPOs are made up of two main components: user configuration, which includes settings related to user preferences and environment, such as desktop settings, logon scripts, and security options; and computer configuration, which includes settings that apply to computers, such as security settings, software installation, and hardware settings. The Group Policy Management Console, or GPMC, is the primary tool for managing and troubleshooting GPOs. It provides a centralized interface for creating, editing, and linking GPOs to Active Directory objects like sites, domains, or organizational units. GPO inheritance determines how GPOs are applied in a hierarchical manner. If a GPO is linked to a parent domain, it will affect all child organizational units by default. GPOs can be blocked or overridden at different levels, allowing finer control over policy application. When multiple GPOs are applied to the same object, the last applied GPO takes precedence, which is determined by the order in which GPOs are linked to the object. GPOs applied at a higher level can be overridden by GPOs at a lower level. The processing order starts with local group policy, which is applied to individual computers before Active Directory GPOs. Next, GPOs linked at the site level are applied, followed by GPOs linked to the domain, and finally, GPOs linked to organizational units are applied last. To create and manage GPOs, first launch the Group Policy Management Console by opening Server Manager, then Tools, and selecting Group Policy Management. To create a GPO, click on the Group Policy Objects node and select New. Name the GPO and click OK. To edit a GPO, right-click the newly created GPO and select Edit, which opens the Group Policy Management Editor, where you can configure settings under Computer Configuration or User Configuration. Common group policy settings include security settings, such as password policies and account lockout policies; software deployment, where administrators can use GPOs to deploy applications to computers; desktop settings, which configure desktop wallpaper; lock screen and start menu settings; user environment settings, to redirect user profiles or folders and configure login scripts; and administrative templates, which are a set of predefined settings that control system behavior. Troubleshooting group policy can be done using the Resultant Set of Policy, or RSOP, which is a tool used to simulate or report the group policy settings applied to a user or computer. To run RSOP, open rsop.msc from the Run dialog. The Group Policy Results Wizard in GPMC can generate a report on what policies are being applied to a user or computer, including any conflicts or errors. You can use the command GP update, force to force immediate policy update, and gpresult shows the resultant policy settings for user or computer. Event Viewer contains logs related to group policy processing, including errors and warnings about failed GPO application. Best practices for group policy include avoiding overuse of local GPOs, minimizing GPO links to ensure easier management, testing GPOs before full deployment, and using comments and descriptions for easier management. Group Policy in Windows Server is an essential tool for system administrators, providing centralized control over a network's configuration and security settings. Properly configuring and managing GPOs can streamline administration, enforce security standards, and ensure that the systems comply with organizational policies. Effective group policy management is essential for a secure and manageable IT environment. First, plan your group policy structure to align with your organization's needs, mirroring your Active Directory hierarchy. Minimize the number of GPOs by consolidating settings and avoiding redundancy. Use security filtering to target specific users or computers, and leverage WMI filters for dynamic GPO applications based on system properties. Limit GPO inheritance with block inheritance and no override settings, and utilize group policy modeling to simulate changes before deployment. Always test GPOs in a controlled environment and monitor their application through auditing. Regularly back up your GPOs and keep them updated to reflect the latest settings. By following these best practices, you can secure group policy infrastructure, reduce conflicts, and enhance security across your network. Effective group policy management is for a secure and manageable IT environment. First, plan your group structure to align with your organization's needs, mirroring your Active Directory hierarchy. Group policy management for maintaining a secure, consistent, and manageable IT environment. Following best practices not only improves the efficiency of administrative tasks, but also that policies are applied correctly, reducing the risk of conflicts, securities, and performance problems. Below are some of the best practices for group policy management in Windows Server. First, plan and document your group policy structure. Design a group policy structure to align with your organization's needs. Typically, this structure should mirror your Active Directory hierarchy, including domains, OUs, and sites. Use domain-level GPOs to apply across the domain. OU-level GPO settings that apply to a specific group of users or computers, and local GPOs for things on individual machines, though these should be avoided, if possible. Documentation is essential. Document the purpose, settings, and impact of GPO to track changes over time and make troubleshooting easier. Keep a central repository for GPO documentation. Next, minimize the number of GPOs. Simplify GPOs by consolidating them where possible instead of creating a large number of small granular GPOs. Having too many GPOs can increase processing time and complexity. Avoid redundant settings to ensure that the same settings aren't configured across multiple GPOs, as it increases the chance of conflicting policies and unnecessary complexity. Use security filtering to target specific users or computers. If you only want a GPO to apply to specific users or computers, use security filtering to target the right group or accounts, rather than link entire OUs or domains. This helps avoid unnecessary application of policies. Create security groups for different types of users or computers, and apply GPOs using these groups for efficient targeting. Utilize WMI filters for dynamic GPO application. WMI filters allow you to apply GPOs based on the properties of the computer, such as its operating version or hardware configuration. This can be useful in environments where different machines need different policies. For example, you can apply a GPO only to computers running Windows 10 or later. Limit GPO inheritance with block inheritance and no override. Block GPO and set specific OUs where you policies from parent OUs or domains to apply, but use this sparingly and only when needed. Use the no override setting to enforce specific GPOs, even if a child GPO would otherwise override it. This is useful for critical security policies or organizational standards. Leverage group policy modeling and simulation. Use group policy modeling and group policy results tools in the Group Policy Management Console to simulate and analyze what policies will be applied to a user or computer. This helps in understanding the impact of GPO changes before applying them in production environments. Use group policy modeling to simulate the GPO application on specific users, computers, or organizational units, and the resultant set of policies provides a detailed report of the policies actually applied, helping with troubleshooting. Use administrative template, a standardized set of registry-based. Always use ADMX files for the GPO to ensure compatibility and avoid outdated settings. Keep your ADMX templates in the sysvol folder. Sure, all GPOs are based on these updated templates. Avoid applying settings that are not required by your organization to reduce overhead and the risk of configuration drift. Implement loopback processing for computer-based policies. Loopback processing allows you to apply user settings based on the computer rather than the user. This is particularly useful in scenarios like terminal servers or kiosk environments where you want to enforce use based on the machine's location. Use loopback mode only when necessary, as it overrides normal GPO application and can lead to complexities if misconfigured. Test GPOs in a controlled environment. Always test GPO changes in a controlled, isolated environment before applying them to production. This can include using a test OU with a small group of users and computers. Use a Group Policy Results Wizard, or RSOP, to verify that the GPO is applied as expected in a test environment. Monitor and audit group policy. Enable auditing by using Windows event logs to monitor and audit GPO application. Enable the group policy operational log for events related to GPO processing, such as successful and failed GPO applications. Use advanced group policy management for version control, change management, and workflows. Maintain regular GPO backups. Backup regularly, especially before making any changes, to ensure that you can recover from accidental misconfigurations or you can export GPOs using the GPMC or commands like backup GPO. Minimize processing time. Keep the GPO size manageable, as excessively large or complex GPOs can slow down startup or login times. Avoid use of scripts in GPOs, particularly login scripts. If scripts, optimize them for performance and ensure they don't slow down the startup process. Regularly review and clean up obsolete GPOs are no longer needed or in use. Apply software restriction policies and secure settings. Use software restriction policies or app blocker to control which software can run on your network and security policies. Implement and enforce strong password policies, account lockout settings, to rights assignments, and auditing settings through group policy to harden your environment. Avoid using block inheritance and enforce frequently. Overuse of block inheritance or settings policy management and lead to unpredictable outcomes. Use them only when absolutely necessary for clarity and ease of troubleshooting. Finally, ensure group is up to date. Keep your ADMX templates updated to reflect new settings available in new Windows Server versions. Keep an eye on updates provided by Microsoft, especially if you're managing newer Windows OS versions. By adhering to best practices, you can create a streamlined, efficient, and secure group policy infrastructure that minimizes conflicts, ensures compliance, and provides consistent management across your network. Effective group management reduces administrative overhead, enhances security, and ensures that organizational policies are applied correctly across the enterprise. Group policy objects, or GPOs, are the backbridging settings in Microsoft Windows environments. Think of them as a powerful toolkit for administrators, allowing centralized control over user and computer configurations across a network. With GPOs, you can enforce security policies, manage software installations, and customize user experiences seamlessly. GPOs consist of two main components: user configuration and computer configuration. User settings can dictate everything from desktop backgrounds to control panel access, while computer settings manage system and network configurations. The beauty of GPOs lies in their hierarchical application: local, site, domain, and organizational units, ensuring that the right policies are applied in the order, with the most specific settings taking precedence. GPOs effectively requires tools like the Group Policy Management Console, which simplifies the creation and application of policies. And when it comes to troubleshooting, commands like gpupdate, salt are invaluable for ensuring everything runs smoothly. By keeping GPOs and avoiding conflicts, administrators can maintain a secure and efficient network environment. POs an essential part of any Windows administrator's toolkit. Group Policy Objects, GPOs, are a core feature in Microsoft Windows environments that allow administrators to centrally manage and configure operating system, application, and user settings across a network. Those are used to enforce security settings, software installation, and other policies on computers and users within an Active Directory domain. A Group Policy Object, GPO, is a collection of settings that control the user and computer accounts within the domain. These settings can include aspects such as security policies, user interface settings, software deployment, and Windows settings. The components of GPOs include user configuration, which applies to user accounts, and computer configuration, which applies to computers. Policies define rules for user and computer behavior, while preference is more granular control, customizing a user's environment. GPOs are applied in a specific order, with local group policy being the first applied to a system, followed by site GPO, domain GPO, and finally OU GPO. The general order of processing is local GPO, site GPO, domain GPO, and OU GPO, with views overriding parent OUs. The primary tool for managing GPOs in a Windows Server environment is the Group Policy Management Console, which allows administrators to create, modify, and apply GPOs. Other tools include the local Group Policy Editor for configuring local GPOs, the Group Policy Results command line tool for viewing applied GPOs, and group modeling for simulating GPO application. GPOs are inherited by child objects unless blocked or overridden, and you can block the inheritance of GPOs at a specific OU. Enforced GPOs will apply even if it is blocked. Common uses of GPO: enforcing security policies, software deployment, environment configuration, restricting access, and running logs. Best practice managing GPOs include keeping them organized, using GPO modeling and results for avoiding overlapping GPOs, and backing up GPOs. Troubleshooting tools include gpupdate to force a group policy update, gpresult to view applied settings, and event viewer for troubleshooting GPO application issues. GPOs are a tool for Windows administrators, enabling them to control the configuration of machines and users in a networked environment with centralized policies. Administrative templates in Windows Server are for managing and configuring Windows environments. Think of them as the control panel for your entire network. These templates, you can enforce policies that dictate everything from security settings to user interfaces. Each template is defined by .admx, which map directly to registries, allowing you to manage settings at scale without the hassle of manual edits. For instance, if you want to prevent users from accessing the command prompt, you simply navigate to the Group Policy Management Console, find the relevant policy under Computer Configuration, and enable it. Instantly, that setting is enforced across all targeted machines. These templates cover a wide range of categories, including Windows components, security settings, and network configurations. By leveraging administrative templates, ensure a consistent and secure user experience across your organization, making your job as an administrator not just easier, but also more effective. Administrative templates are a collection of policy settings in group policy that allow administrators to configure and control various aspects of the operating system and applications. These settings are primarily found under User Configuration and Computer Configuration in the Group Policy Management Console. Administrative templates are used to configure both system and user-specific settings, and they provide a way to define specific behaviors in Windows, from security settings to the appearance of the user interface. Group Policy Administrative Templates are a set of .admx files that define policy settings for Windows operating systems. These contain registry policy settings and a wide range of features, from desktop settings to security settings and system behavior. ADMX files are the administrative template files in the policies, while .adml are language-specific files that provide the localized text for each policy. You can find administrative in Group Policy Management under User Configuration, Policies, Administrative Template, Computer Configuration, Policies, Administrative Templates. Each policy represents a setting that can be configured or enforced. Most of the settings configured in templates map to registry keys on this machine. These templates essentially allow you to manage the registry keys at a group level, eliminating the need for managing of the registry. Administrative templates in group policy can be categorized into several broad groups, category containing various specific policies. The first category is components, which allows administrators to configure behavior for different built-in Windows components: Windows Explorer, Windows Update, Internet Explorer, and BitLocker Droption. The second category is security settings, which includes policies that control the security-related behavior of Windows systems, such as account lock policy, password policy, audit policy, and user rights assignment. The third category is system, encompassing settings related to system behavior and environment, including logon, logoff, remote desktop, Windows time service, and startup shutdown. The fourth category is control panel, where administrators can control users to control panel settings, such as hiding specific control panel items, restricting access to control panel, and setting wallpaper restrictions. The fifth category is desktop, focusing on the appearance and user interface of the desktop environment, including desktop background, start menu, and taskbar configurations. The sixth category is network, allowing admins to configure network settings across machines, such as offline files, network connections, and wireless network policies. The seventh category is Windows settings, which includes a variety of settings for system-level configurations, such as event logging, Windows Defender antivirus, and services. Applying administrative templates involves GPOs that are linked to an Active Directory site, domain, or organizational unit. Once applied, these settings will in policy on the target systems, based on the specified. When you configure an administrative template in a GPO, it modifies the Windows registry on the targeted systems. For example, an administrative template like prevent access to the command modifies the registry key with this setting, ensuring that the policy is enforced. Administrative templates are registry-based, so the setting is essentially a registry key that can be modified by group policy. Administrators can centralize the administrative template files in Azure, making them available across GPOs and ensure they are consistent across all domain controllers. Starting with Windows Server 2008 and Windows Vista, Microsoft introduced ADMX templates that replace the older ADM files. The ADMX files are more efficient and can be stored in a central store within Active Directory. For example, to prevent users from accessing the command prompt in your organization, you can do it using group policy and administrative. Open the Group Policy Management console, create a new GPO or edit anyone, and under Computer Configuration, navigate to Policies, Administrative Templates System. Find the Prevent Access to the command prompt and set it to Enabled. Link the GPO to the appropriate OU or domain. Once applied, machines will prevent users from accessing the command prompt, regardless of the user's permissions. In conclusion, administrative templates are a powerful tool in Windows and Active Directory environments, allowing administrators to enforce consistent policies across many systems. By using these templates, administrators can easily manage a wide variety of settings that control system behavior, security policies, user configurations, and much more, all through group policy. Understanding and utilizing administrative templates effectively is key to maintaining control and security in a Windows-based network environment. Effective group policy management is essential for maintaining a secure and efficient IT environment. Start by organizing your group policy objects logically. Use descriptive names and group similar policies together. Limit the scope of your GPOs by linking them to the smaller containers and utilizing security and WMI filtering to target specific users or computers. Understand the GPO processing order to avoid conflicts and use the enforce option for critical settings. Document every change meticulously to ensure accountability and simplify troubleshooting. Always test GPO changes in an environment before rolling them out widely. Optimize performance by limiting the number of GPOs and using group policy preferences for non-essential settings. Regularly review security settings to ensure compliance and delegate GPO management to prevent unauthorized changes. Finally, update your GPOs regularly and implement a center for ADMX templates to maintain consistency. Following these best practices will lead to a more manageable and secure organizational environment. Configuring group policy objects, or GPOs, is a fundamental task for managing user and computer behavior in an Active Directory environment. Think of GPOs as the rule book work, controlling everything from security settings to software installations. You manage these through the Group Policy Management console, where you can create and edit GPOs tailored to your needs. Each GPO has two main components: user configuration for individual user settings and computer configuration for system-wide policies. You can link GPOs to sites, domains, or specific organizational units, ensuring the right settings apply to the right users or devices. When conflicts arise, remember the precedents. Local GPOs take priority over site and domain-level GPOs, while OU-level GPOs can override domain settings. For targeted application, use security filtering to limit GPOs to specific groups, or WMI filtering to apply them based on system attributes. To troubleshoot, tools like gresult and resultant set of policy can help you identify which G are in effect and resolve any issues. By organizing config policy objects, GPO is a core task for managing behavior of users and computers in an Active Directory environment. GPOs allow system administrators to enforce settings across mixes and users to ensure consistency, security, and compliance. A group policy object, GPO, is a collection of settings that control how computers and users behave within an Active Directory environment. GPOs can apply settings to a wide range of system behavior, security settings, software installation, user permissions, desktop settings, and network configurations. GPOs are created and managed via the Group Policy Management console, GPMC, which is typically accessed on a Windows server via an administrative workstation with the remote server administration tools installed. To access GPMC, open Group Policy Management from the Start menu, expand your domain to see existing GPOs and manage new ones. To configure a GPO, first, create a GPO by opening the Group Policy Management console, right-clicking on the Group Policy Objects container, selecting New, giving the GPO a meaningful name, and clicking OK. Next, edit the GPO by right-clicking it and selecting Edit, which opens the Group Policy Management Editor. Here, you'll see two main nodes: Computer Configuration, which includes settings that apply to configuration, which includes settings that apply to users. You can configure various settings depending on what you want to achieve: password policies, software installation, top restrictions, startup, shutdown scripts, Windows firewall, and log management. Each setting is typically a policy which you can modify to meet your requirements. After configuring your GPO, link it to a container by right-clicking the container where you want the GPO to apply, selecting Link an existing GPO, choosing the GPO you created, and clicking OK. Once a GPO is applied, it may take time for the settings to propagate. You can manually force an update by running gpupdate force from the command line on a target machine. GPOs are applied in a specific order, and the settings can be overridden or inherited depending on their location and configuration. The order of precedence is local GPO, domain-level GPOs, and OU-level GPOs. When GPOs conflict, the more specific GPO can override the domain GPO. You can apply GPOs to specific groups or computers by using security filtering and WMI filtering. Security filtering limits the application of a GPO to specific groups or users, while WMI filtering allows you to apply GPOs based on system attributes. Troubleshoot group policy issues. Tools like gpresult and resultant set of policy can help determine which GPOs are being applied and if there are any conflicts. The command gpresult bar displays the group policy settings applied to a user or computer, and RSOP is a graphical tool for seeing the result of GPO processing. Best practices for managing GPOs include organized logically with descriptive names, testing GPOs in a test OU before full deployment, minimizing GPO complexity to ensure manageability, and using GPO delegate to restrict who can edit and manage GPOs for better security. GPOs are an essential tool for centralizing administrative tasks in a Windows environment, providing a powerful way for security, standardized settings, and automate configurations across many systems. By following a clear process for creation, application, and management, you can ensure consistency and security across your network. In group policy objects, you often face three key options when configuring a policy: not configured and disabled. Let's break them down. First, not configured, no specific action is taken. The policy retains its default state, allowing other GPOs or local settings to dictate behavior. Use this when you want to keep things flexible and let existing configurations take precedence. Next, we have enabled. This is where the magic happens. When you enable a policy, you're actively enforcing a setting. Think of it as flipping the switch to ensure that specific rules like password complexity are strictly followed. Perfect for when you need to enforce security measures or specific configurations. Finally, there's disabled. This option explicitly turns off a policy, overriding any defaults. Use this when you want to prevent a setting from applying, like disabling a firewall for a specific group where it's unnecessary. So whether you're keeping things flexible, enforcing rules, or preventing unwanted settings, understanding these options is crucial for effective policy management. In group policy objects, GPOs, when configuring a policy setting, you typically encounter three possible options for a setting: not configured, enabled, and disabled. Policy is set to not configured. It means that no specific configuration has been made for that policy. This option essentially leaves the policy in its default state. The setting will not be enforced by the GPO. If other GPOs or settings at different levels configure this policy, their settings will apply. You should leave policies set to not configured when you don't need to enforce a particular setting, when the policy should be left to the default configuration, or when you want to allow users or other GPOs to override the policy. When a policy is set to enabled, the setting is activated, and it will take effect. The associated setting will be enforced, meaning that the policy will be applied to the target system according to its configuration. Some settings may require you to provide additional configuration or specify options when enabled. You want to force a policy to be active and apply to users or computers. For example, enabling password policies, login restrictions, or enforcing desktop lock settings, or enabling specific security measures like Windows Defender antivirus or auditing settings. When a policy is set to disabled, the setting will be explicitly turned off. This will override any default behavior or other settings that would normally apply to that policy. Let's consider the password complexity setting, which enforces that passwords must contain a mix of uppercase, lowercase, numbers, and symbols. If the policy is not configured, the policy is not enforced, and passwords could follow any rules configured elsewhere. If enabled, password complexity is enforced, and all passwords must comply with the specified rules. If disabled, password complexity is disabled, users will not be required to meet the complexity criteria, even if the default domain policy enforces it. Not configured is the default, and is used when you don't want to specify any configuration for the policy. Enabled is used to in specific settings. Disabled is used to prevent the policy from being applied when you don't want that setting effect. In group policy objects, GPOs, when configuring a policy setting, you typically encounter three possible options for a setting: not configured, enabled, and disabled. Policy is set to not configured. It means that no specific configuration has been made for that policy. This option essentially leaves the policy in its default state. The setting will not be enforced by the GPO. If other GPOs or settings at different levels configure this policy, their settings will apply. You should leave policies set to not configured when you don't need to enforce a particular setting, when the policy should be left to the default configuration, or when you want to allow users or other GPOs to override the policy. When a policy is set to enabled, the setting is activated, and it will take effect. The associated setting will be enforced, meaning that the policy will be applied to the target system according to its configuration. Some settings may require you to provide additional configuration or specify options when enabled. You want to force a policy to be active and apply to users or computers. For example, enabling password policies, login restrictions, or enforcing desktop lock settings, or enabling specific security measures like Windows Defender antivirus or auditing settings. When a policy is set to disabled, the setting will be explicitly turned off. This will override any default behavior or other settings that would normally apply to that policy. Let's consider the password complexity setting, which enforces that passwords must contain a mix of uppercase, lowercase, numbers, and symbols. If the policy is not configured, the policy is not enforced, and passwords could follow any rules configured elsewhere. If enabled, password complexity is enforced, and all passwords must comply with the specified rules. If disabled, password complexity is disabled, users will not be required to meet the complexity criteria, even if the default domain policy enforces it. Not configured is the default, and is used when you don't want to specify any configuration for the policy. Enabled is used to in specific settings. Disabled is used to prevent the policy from being applied when you don't want that setting effect. When it comes to group policy objects in Windows Active Directory, understanding the differences between local, domain, and site GPOs is crucial. First, local GPOs are all about the individual machine. They apply only to that specific computer, making them perfect for standalone setups. You can tweak these settings using the local group policy editor, giving you control without needing a domain. Now, domain GPOs take it up a notch. These are linked to an entire Active Directory domain, affecting all users and computers within that domain. They're managed through Group Policy Management Console, allowing for centralized control and consistency across your network. Then we have site GPOs, which are tied to specific physical locations within your network. This means you can apply policies based on where computers are located, ensuring that settings are relevant to different offices or buildings. Remember, GPOs are applied in a hierarchy. Local first, then site, followed by domain, and finally, organizational units. If there's a conflict, the OU level GPO wins out. This layered approach allows for flexibility and precision in managing your environment. It seems like you're asking about the differences between local group policy objects, GPOs, domain GPOs, and site GPOs in the context of Windows Active Directory. Let me break them down for you. Local GPO, local group policy object, applies only to the local computer it is configured on. It is primarily used when you want to apply policies to a single machine without involving a domain. It can be edited on the local computer by running gpedit, MSC, or by using the local group policy editor. Every Windows machine has a local GPO by default, which is used if no domain GPOs are applied. Domain GPO, group policy object, is linked to a specific Active Directory domain and applies to all computers and users within that domain, or specific organizational units within it. It allows centralized management of group policy for all domain-joined computers and users. Domain GPOs are created and managed by the Group Policy Management Console, GPMC, on a domain controller or another machine with the necessary administrative tools. GPOs applied at higher levels can be overridden by GPOs applied at lower levels. Site GPO, group policy object linked to a site, applies to computers that are located in a specific Active Directory site. A site in Active Directory is typically defined by physical locations, such as specific IP subnets or network segments. These are generally used to apply policies based on the geographical or network location of computers, ensuring that settings are applied to machines in specific locations, like different offices or buildings. Key differences include that local GPO applies to a single machine, regardless of whether it's part of a domain. Domain GPO is applied to all domain-joined computers or users, and site GPO is applied to computers based on their physical location within an Active Directory site. GPOs are applied in a specific order based on where they are linked. Local GPO applies first, followed by site-level GPO, then domain-level GPO, and finally organizational unit, OU-level GPO, which has the highest precedence. If there are conflicts in policies between different levels, the OU-level GPO will generally take precedence, followed by domain, site, and then local GPOs. Let me know if you need more details or clarification on any of these. When comparing local computer GPO and domain controller GPO, we're diving into two distinct realms of group policy management. Local computer GPO is all about the individual machine. It applies to a single computer, whether it's part of a domain or not, and is managed through the local group policy editor. Think of it as your go-to for configuring settings on standalone machines or when domain policies aren't available. On the flip side, domain controller GPO is specifically for the servers that manage Active Directory. These GPOs are crucial for maintaining security and functionality within the domain. Managed through the Group Policy Management Console, they enforce strict security settings like password policies and account lockout rules. In essence, local GPO is your individual machine's toolkit, while domain controller GPO safeguards the entire Active Directory infrastructure. Both are vital, but they serve different purposes in keeping your environment secure and efficient. When comparing local computer GPO and domain controller GPO, we're diving into two distinct realms of group policy management. Local computer GPO is all about the individual machine. It applies to a single computer, whether it's part of a domain or not, and is managed through the local group policy editor. When discussing local computer GPO versus domain controller GPO in the context of group policy, we're essentially comparing policies applied to non-domain controllers and user machines versus domain controllers, the servers responsible for managing the Active Directory domain. Here's how they differ. Local computer GPO local group policy object, applies to a single machine. It is specific to the individual computer, regardless of whether the computer is a domain member or not. Located on each local computer in the CE Windows System 32Edge Group Policy folder, it affects that machine exclusively. You can manage the local GPO using the Local Group Policy Editor, GPEDIT MSC. It is primarily used for standalone machines, or domain GPOs are not available or not in place. Typically applied when you need to configure settings on a single machine, without affecting the entire domain. Also useful for applying emergency or recovery policies when the machine is not domain joined. Configurations in the local GPO include settings like security policies, user permissions, and software restrictions, which apply only to that machine. It is the lowest level in the group policy processing order, meaning it's applied first before any domain level or Active Directory policies. Domain Controller GPO applies specifically to domain controllers, the servers that handle authentication and directory services for an Active Directory domain. Managed through the Group Policy Management Console, GPMC, are stored on the domain controller in Active Directory. You cannot use the Local Group Policy Editor, GPEDIT.SC, to configure policies on a domain controller. Instead, you use GPMC to create and apply GPOs specifically for domain controllers. You can also manage domain controller specific settings by creating a domain controller's organizational unit, OU, and linking GPOs to that OU. These GPOs are applied to the machines running Active Directory Domain Services, ADDS. They define security settings, audit policies, and other domain-specific settings. Domain controllers often have stricter security requirements because they manage authentication, user rights, and other critical AD services. Examples of domain controller GPO settings include password policies, Kerberos settings, account lockout policies, replication settings, and security auditing. These GPOs are crucial for protecting the security and integrity of the Active Directory infrastructure. In Active Directory, there is a default domain controller policy that automatically applies to all domain controllers, and you can also create custom GPOs specifically for domain controllers. Key differences. Local Compute GPO applies to a single computer, domain or non-domain, while Domain Controller GPO applies specifically to domain controllers in the domain. The configuration tool for Local Computer GPO is a Local Group Policy Editor, GPEDIT MSC, whereas for Domain Controller GPO, it is the Group Policy Management Console, GPMC. Local Computer GPO is typically used for standalone machines, or if no domain GPOs are applied, while Domain Controller GPO is used for the security and management of domain controllers and AD services. Local Computer GPO is located in C Arch Windows R System 32 POSIT group policy on each machine, while Domain Controller GPO is stored and managed in Active Directory via GPMC. Local GPO is the first to be applied, while Domain Controller GPO is applied after local GPOs, but is usually more critical for security. Examples of local computer GPO policies include user rights, software settings, and security options, while Domain Controller GPO policies specific settings like password policies, auditing, etc. Domain Controller GPO special considerations. GPOs that are applied to domain controllers are critical for securing your Active Directory infrastructure. Incorrect configurations or overly permissive policies can introduce significant vulnerabilities. On domain controllers, settings are often stricter than those on regular workstations due to the sensitive nature of their role in the domain. You can apply GPOs to domain controllers either directly via the default domain controllers policy or create custom policies for specific domain controllers by creating a GPO and linking it to domain controllers OU. Some settings are specifically meant for domain controllers, such as user rights assignment, audit policies, account lockout policies, and security options. Key GPOs for domain controllers include the default domain controllers policy, which applies default security settings to all domain controllers, and custom GPOs for domain controllers, which administrators can create and link to further fine-tune domain controller configurations. In summary, local GPO affects a single machine, whether domain joined or standalone, while domain controller GPO applies to domain controllers and is used to manage critical Active Directory services and security settings. Both types of GPOs are essential, but serve different roles in managing and securing the environment. Hyper-V is a game changer in the world of virtualization. As a Type 1 hypervisor, it runs directly on hardware, delivering impressive performance. Imagine creating multiple virtual machines, each running its own operating system, all isolated from one another. With Hyper-V's virtual switches, these VMs can communicate seamlessly, whether internally or with the outside world. You can manage resources efficiently, allocating CPU and memory dynamically based on demand. And if something goes wrong, snapshots let you roll back to a previous state in an instant. Live migration means you can move running VMs between hosts without any downtime, perfect for maintenance or load balancing. Whether you're testing software, consolidating servers, or planning for disaster recovery, Hyper-V has you covered. It's not just a tool, it's a robust solution for businesses leveraging Windows environments, making virtualization both scalable and secure. Hyper-V is a game changer in the world of virtualization. As a Type 1 hypervisor, it runs directly on hardware, delivering impressive performance. Imagine creating multiple virtual machines, each running its own operating system, all isolated from one another. Hyper-V is a native hypervisor developed by Microsoft that allows you to create and manage virtual machines, VMs, on a physical host machine. It is part of the Windows Server family of products, but is also available in certain editions of Windows 10 and Windows 11. Hyper-V enables virtualization, which is the process of running multiple operating systems simultaneously on a single physical machine. Hyper-V is a Type 1 bare metal hypervisor, meaning it runs directly on the hardware of the host machine. This gives it a performance advantage over Type 2 hypervisors, which run on top of an existing operating system. Hyper-V allows you to create VMs, each of which can run its own operating system. These VMs are isolated from each other and from the host system. Hyper-V includes a virtual switch, which allows VMs to communicate with each other and with the external network. You can configure different types of virtual switches for different networking setups. Each VM in Hyper-V uses a virtual hard disk file, which emulates a physical hard drive for that VM. These files can be created in various formats, such as VHD or VHDX. Hyper-V allows you to take snapshots of VMs at a specific point in time. This allows you to roll back the VM to a previous state, which is useful for testing or disaster recovery. Hyper-V supports live migration, which allows you to move running VMs between different physical hosts without downtime. This is useful for load balancing or hardware maintenance. Hyper-V supports dynamic memory allocation, which means it can adjust the amount of memory allocated to a VM based on its needs, within predefined limits. This helps optimize resource utilization. Each virtual machine is isolated from the host and other VMs, ensuring that if one VM crashes, it doesn't affect the others. Hyper-V provides robust resource management tools to allocate CPU, memory, and storage resources to VMs based on workload requirements. Hyper-V supports large-scale virtual environments and can run on high-performance hardware with multiple cores, massive memory configurations, and large-scale storage setups. Hyper-V provides integration services for guest operating systems, improving VM performance and enabling features like time synchronization, shutdown integration, and backup support. Hyper-V includes several security features such as shielded VMs, which help protect against unauthorized access to the VM data and processes. VMware's hypervisor is often seen as the competitor to Hyper-V, and it is more feature-rich in some enterprise environments. However, Hyper-V benefits from seamless integration with Windows Server environments. KVM is a popular hypervisor for Linux-based systems and offers similar features, but it doesn't integrate as tightly with Windows-based environments as Hyper-V does. Developers can create isolated environments to test different operating systems and applications without affecting the host system. Hyper-V allows businesses to run multiple server workloads on a single physical machine, improving hardware utilization and reducing operational costs. By creating snapshots and using features like live migration, Hyper-V helps with backup and disaster recovery planning. Hyper-V is the foundation of Microsoft's private cloud offering and is used to run virtualized environments in data centers. The host machine must have a 64-bit processor with second-level address translation and virtualization support enabled in the BIOS. Hyper-V is available on Windows 10 Pro, Enterprise, and Education editions, as well as on Windows Server. Some versions of Windows 11 also support it. In summary, Hyper-V is a powerful and efficient virtualization tool that is particularly well-suited for businesses using Windows Server environments or those looking for a cost-effective solution for virtualizing workloads. It is designed to be scalable, secure, and manageable, making it a versatile solution for virtualizing both desktop and server workloads. Hyper-V operates in various modes, each tailored to specific needs and environments. First, there's Hyper-V Manager, the user-friendly GUI that simplifies VM management. For those who crave automation, Hyper-V PowerShell offers a powerful command line interface, perfect for scripting and bulk operations. Then we have Hyper-V Server, a standalone solution that delivers virtualization without the overhead of a full Windows server, ideal for cost-conscious businesses. In enterprise settings, the Hyper-V role integrates seamlessly with Windows Server, leveraging its management tools. For desktop virtualization, Hyper-V Client on Windows 10 allows developers to run test environments right on their PCs. Hyper-V Replica ensures high availability and disaster recovery, keeping your VM safe across different hosts. Lastly, Nested Virtualization lets you run Hyper-V inside a VM, perfect for testing and development. Each mode enhances flexibility, performance, and control in virtualized environments. Hyper-V operates in various modes, each tailored to specific needs and environments. Hyper-V operates in different modes, which define how it interacts with the host operating system and virtual machines, VMs. These modes can impact performance, configuration, and the capabilities of virtualized environments. The primary modes of Hyper-V are 1. Hyper-V Manager, UI mode. This is the graphical user interface mode for managing Hyper-V. It allows administrators to interact with and configure virtual machines and Hyper-V settings using a Windows-based interface. You can create, start, stop, and configure virtual machines, manage virtual networks and storage, configure VM settings, including CPU and memory allocation, and monitor performance and resource utilization. This mode is primarily used for local, user-friendly management of virtualized environments. It's best suited for users who prefer graphical interfaces over command line tools. 2. Hyper-V PowerShell, command line mode. PowerShell is a powerful command line tool that provides a more scriptable and automated approach to managing Hyper-V. The Hyper-V module in PowerShell allows administrators to automate the creation, configuration, and management of VMs, perform bulk actions such as creating multiple VMs or configuring resources, and run scripts to manage virtual switches, storage, and VM migration. This mode is useful for advanced users or system administrators who need to automate tasks or work with large numbers of VMs. PowerShell also allows for detailed control over Hyper-V settings and resources. 3. Hyper-V Server Standalone Mode. Hyper-V Server is a free, standalone version of Hyper-V that provides the hypervisor functionality without the overhead of a full Windows Server installation. It offers a minimal, stripped-down operating system designed for running virtual machines and the same virtualization capabilities as the full Windows Server version, but with limited features like GUI and fewer management tools. This mode is ideal for businesses that want a dedicated virtualization host without the cost of a full Windows Server license. It's commonly used in environments where VMs are managed remotely or through automation. 4. Hyper-V Role Hosted Mode. This mode refers to when Hyper-V is installed as a role on top of a Windows Server operating system. In this configuration, the host system runs a full Windows Server installation, and Hyper-V runs as a service, and virtual machines can be managed via tools like Hyper-V Manager, PowerShell, or System Center Virtual Machine Manager. This mode is used in most enterprise environments where Hyper-V is combined with the management and administrative tools provided by Windows Server. It allows for better integration with Active Directory, System Center, and other Microsoft technologies. 5. Hyper-V Client Desktop Virtualization Mode. In this mode, Hyper-V is installed on Windows 10 Pro, Enterprise, or Education editions. It enables users to run virtual machines on their desktop computers. Unlike the Hyper-V Server mode, Hyper-V on Windows 10 is often used for running development or test environments, virtualizing desktop OSs like Windows or Linux, and creating isolated environments for testing applications or configurations. This mode is mostly used by developers, testers, or IT professionals who need to create and manage virtual machines on a personal computer or for local testing purposes. It's not typically used for production workloads in enterprise environments. 6. Hyper-V Replica Mode. This is a high availability and disaster recovery feature where a virtual machine's state and data are replicated between different Hyper-V hosts. The VM on the secondary host remains in a ready-to-start state in case the primary host fails, offering protection against hardware or software failure. This mode is used in environments where uptime and business continuity are critical. Hyper-V Replica enables replication of VM data and syncs across multiple sites for disaster recovery purposes. 7. Hyper-V Nested Virtualization Mode. Nested virtualization allows you to run Hyper-V hypervisor inside a virtual machine. This feature is useful in scenarios like lab environments for testing Hyper-V features and run Hyper-V in cloud environments where hardware-level virtualization is not available. Ideal for developers or IT professionals who want to experiment with Hyper-V or set up Hyper-V environments within virtual machines for testing purposes. It's also valuable in cloud-based infrastructure where the physical hardware doesn't support virtualization natively. In summary, the different modes of Hyper-V include Hyper-V Manager, GUI, Hyper-V PowerShell, Hyper-V Server, Hyper-V Role, Hyper-V Client, Hyper-V Replica, and Hyper-V Nested Virtualization. Each mode serves specific use cases, allowing Hyper-V to be utilized across a wide range of environments, from small-scale desktop virtualization to large enterprise data centers with high availability and disaster recovery needs. When we dive into virtualization, we encounter three main modes: full virtualization, partial virtualization, and containerization. Full virtualization creates a complete illusion of a physical machine, allowing guest operating systems to run unmodified. This means high isolation and compatibility, but it comes with performance overhead. Then there's partial virtualization, where the guest OS knows it's virtualized. It can directly interact with some hardware, which can enhance performance but requires special drivers and modifications. Finally, we have containerization, the lightweight champion virtualization. Here, multiple containers share the same OS kernel, making them fast and efficient, perfect for microservices and cloud-native applications. However, this shared kernel can pose security risks. Each mode has strengths and weaknesses, so the choice depends on your specific needs, isolation, performance, and compatibility. When discussing virtualization, there are several types or modes that define how the hypervisor interacts with guest operating systems, OS, and their resources. These modes impact performance, isolation, and compatibility with guest operating systems. The three common categories are full virtualization, partial virtualization, and containerization or OS-level virtualization. Let's break down each mode. Full virtualization is a method of virtualization in which the guest operating system runs without knowing it's being virtualized. The hypervisor provides a complete virtualized environment to the guest OS, which behaves as though it's running on a physical machine. Key characteristics include that the guest OS is completely isolated from the host and other VMs. The hypervisor fully emulates all hardware components, CPU, memory, I/O, network devices, etc. To the guest OS, no modifications are required to the guest OS for it to run in a virtualized environment. And full virtualization can be hardware assisted by CPU features like Intel VTX or AMD V. Examples of full virtualization hypervisors include Hyper-V when using hardware-assisted virtualization, VMware, vSphere, ESXi, KVM, kernel-based virtual machine with hardware support, and Xen with hardware-assisted support. Use cases for full virtualization include running unmodified guest OSes, Windows, Linux, etc., in isolated environments, running legacy applications or operating systems that require complete hardware isolation, and it is ideal for server consolidation as it allows multiple OSes to run on the same physical hardware without requiring them to be aware of each other. Advantages of full virtualization include isolation, as each VM is fully isolated, so problems in one guest OS don't affect others, and compatibility, as full virtualization supports a wide range of guest operating systems, including those that are not designed to run in virtual environments. Disadvantages include performance overhead, as the hypervisor emulates all hardware. There is a performance penalty compared to running on physical hardware, and it is resource intensive, as emulating hardware and running multiple VMs can consume significant system resources. Partial virtualization is a method where the guest operating system is aware it's running in a virtualized environment. The hypervisor does not completely emulate all hardware components. Instead, it partially virtualizes them, allowing the guest OS to directly interact with some of the underlying hardware, while the hypervisor manages others. Key characteristics include that some part of the guest OS may be modified to work in a virtualized environment. The guest OS may need special drivers or support to run efficiently in the virtual environment. Not all hardware is virtualized, and it is typically used in scenarios where the guest OS can handle some operations itself, and the hypervisor only manages critical components. Examples of partial virtualization hypervisors include Xen in some configurations, VMware Workstation, and VMware Fusion when not using hardware-assisted virtualization, and OpenVZ for containerized virtualization, though it's closer to containerization. Use cases for partial virtualization include performance-sensitive applications where virtualization of only certain resources, CPU, memory, is necessary, and environments where guest OS supports some level of virtualization, e.g. older operating systems or proprietary OSs. Advantages include lower overhead, as the hypervisor does not need to fully emulate hardware, and better resource utilization, as the guest OS may be able to access some resources directly, reducing the strain on the hypervisor. Disadvantages include limited OS support, as the guest OS may need to be customized or aware of the virtualization environment, and complex configuration, as it may be harder to configure compared to full virtualization, especially for less experienced administrators. Containerization is a form of operating system level virtualization, where the hypervisor doesn't provide full hardware virtualization. Instead, it provides a shared kernel environment for multiple isolated containers. Each container runs as an isolated process in the user space, but all containers share the same underlying OS kernel. Key characteristics include a shared OS kernel, as all containers share the same OS kernel, but are isolated from one another, being lightweight, as containers are generally more lightweight than virtual machines because they don't require a full OS per instance, fast boot times, as containers can start and stop very quickly, and isolation, as containers are isolated from one another, but they run on the same OS and kernel. Examples of containerization platforms include Docker, Kubernetes for managing containerized applications, and LXC, Linux containers. When it comes to data storage in virtualization and IT infrastructure, local disks and storage area networks, or SANs, are two distinct approaches. Local disks are directly attached to a server, offering low latency and simplicity. They're great for personal computers and small servers, with limitations like scalability and redundancy. On the other hand, SANs provide a networked solution that allows multiple servers to access centralized storage. This means high performance and scalability, making them ideal for data centers and enterprise applications. However, SANs require a significant investment and specialized knowledge to manage. So, whether you choose local disks for their cost effectiveness or a SAN for its robust capabilities, the decision hinges on your specific needs and environment. When discussing storage types in virtualization, computing, and IT infrastructure, SAN, storage area network, and local disks represent two very different approaches to data storage. Each has its own use cases, advantages, and disadvantages. Local disks refer to storage devices directly attached to the physical server or machine. This can include hard disk drives, HDDs, solid-state drives, SSDs, or any other form of direct attached storage, DAS, inside the server. Local disks are physically connected to the server, meaning they are not shared with other machines. They don't rely on a network for communication. The storage is accessed directly by the server's operating system. Most servers or personal computers have local disks installed directly in the machine, such as SATA, SAS, or NVMe drives. HDDs are magnetic storage, larger capacities, and more affordable but slower speeds. SSDs are flash-based storage, much faster than HDDs but generally more expensive per GB. Local disks are commonly used in personal computers, entry-level servers, and virtualization hosts. The advantages of local disks include low latency, lower cost, and simplicity. However, they have disadvantages such as limit scalability, no centralized management, and no inherent redundancy. A storage area network, SAN, is a high-speed network of storage devices that provides block-level access to data. It allows servers to access storage as if it were local, but the storage itself is managed separately, often across multiple physical devices. SAN connects storage devices and servers over a dedicated network, such as Fiber Channel, ISCSI, or NVMe over fabrics. Unlike NAS, which provides file-level access, SAN provides block-level storage, meaning the data is presented to the server as raw blocks. The storage is typically centralized and can be shared across multiple servers, improving efficiency and reducing complexity. SAN systems are designed for enterprise-scale storage and can be expanded with additional storage devices without significant downtime or disruption. Types of SAN include fiber channel SAN, ISDSI SAN, fiber channel over Ethernet, and NVMe over fabrics. SANs are ideal for large data centers, enterprise applications, and backup and disaster recovery. The advantages of SANs include scalability, high performance, centralized storage management, and high availability and redundancy. However, they come with disadvantages such as cost, complexity, and network dependency. Key differences between SAN and local disks include connectivity, storage type, scalability, performance, cost, redundancy, management, and use cases. Local disks are suitable for smaller environments or individual machines where high scalability and centralized management are not a priority. They are easy to set up and cost-effective, but offer limited flexibility and redundancy. Storage area networks are designed for large enterprise-level environments where high performance, scalability, redundancy, and centralized management are needed. SANs are ideal for mission-critical applications, data centers, and virtualized infrastructures where high availability and performance are essential. Choosing between local disks and a SAN depends on the size, complexity, and performance requirements of your environment. For smaller setups, local disks may be sufficient, while for larger high-demand environments, SANs provide the necessary scalability and performance. Hyper-V is a powerful Type 1 hypervisor developed by Microsoft, running directly on physical hardware to enable efficient hardware virtualization. At its core is the Hyper-V hypervisor, which allocates resources like CPU and memory to virtual machines while ensuring they remain isolated from one another. The parent partition, or host OS, manages these VMs and runs essential tools like Hyper-V Manager and PowerShell. Each virtual machine operates in its own child partition, allowing different operating systems to coexist without interference. Networking is managed through virtual switches, connecting VMs to external networks or isolating them for security. Storage handled via virtual hard disks with options for dynamic allocation and snapshots. Integration services enhance performance and communication between the host and guest OS. This architecture is designed for scalability, making Hyper-V suitable for everything from small setups to large enterprise environments. Hyper-V is a powerful Type 1 hypervisor developed by Microsoft, running directly on physical hardware to enable efficient hardware virtualization. Hyper-V is a Type 1 hypervisor developed by Microsoft to enable hardware virtualization. As a Type 1 hypervisor, Hyper-V runs directly on the physical hardware rather than on top of an operating system, which differentiates it from Type 2 hypervisors. The architecture of Hyper-V is designed to manage and allocate physical resources to virtual machines efficiently while maintaining isolation between them. The host OS is the physical machine's operating system, which runs the hypervisor. In the case of Hyper-V, this host OS is typically Windows Server or Windows 10, 11 Pro, Enterprise, or Education editions for client-based installations. The host OS performs administrative functions and runs applications, services, and management tools that interact with the virtualized environment. Key components in the host OS include the Hyper-V hypervisor, which is the core component of the architecture, the parent partition, which is the first and primary virtual machine that runs on Hyper-V, and management tools like Hyper-V Manager, PowerShell, and System Center Virtual Machine Manager that administrators use to configure, manage, and monitor the virtual machines. The Hyper-V hypervisor is a critical component that sits between the hardware and the virtual machines. It provides the low-level virtualization capabilities that allow the creation and management of VMs, enabling them to share the host's hardware resources. Key functions of the hypervisor include resource allocation, isolation, scheduling and execution, and virtual device emulation. Key components of the hypervisor layer include the virtual machine monitor, which controls and manages the execution of virtual machines, and virtualization extensions like Intel VTX and AMDV that assist the hypervisor in managing virtualization. Each virtual machine in Hyper-V runs in its own child partition, which is a virtualized environment running on top of the hypervisor. These child partitions are isolated from each other, meaning they can run different operating systems and applications without interfering with the host or other VMs. Key characteristics of virtual machines include guest operating systems, virtual hardware, isolation, and dynamic resource allocation. Hyper-V provides a virtual switch to manage networking between the host, virtual machines, and the outside world. The virtual switch acts as a virtual network hub that can be configured to provide different networking setups. Types of virtual switches include external virtual switch, which allows VMs to connect to the external network, internal virtual switch, which allows communication between the host and the VMs, and private virtual switch, which allows communication only between VMs on the same host. Each virtual machine in Hyper-V requires a virtual hard disk, which is a file that simulates a physical hard drive. The virtual hard disk stores the operating system, applications, and data for the virtual machine. Key features of VHD/VHDX include VHD, the older format for virtual disks, and VHDX, the newer format that supports larger disk sizes and additional features. Hyper-V supports dynamically expanding virtual disks, where the VHD/VHDX file grows as data is written. Hyper-V provides integration services to improve the interaction between the host and the guest operating systems running on virtual machines. These are drivers and services installed in the guest OS that enhance the VM's performance and enable features such as time synchronization, heartbeat monitoring, shutdown integration, VSS support for backup, and mouse integration. Integration services are automatically installed when the guest OS is a supported version of Windows. While for Linux-based OSs, the Hyper-V Linux integration services need to be installed manually. Hyper-V manages virtual storage for virtual machines through virtual hard disks and virtual storage controllers. The storage resources for VMs can come from local storage, SANs, or network-attached storage. Hyper-V supports several storage options, including fixed VHD, VHDX, dynamic VHD, VHDX, and differencing VHD, VHDX. Hyper-V also supports live migration of virtual machines to different storage locations and virtual disk sharing for high availability and disaster recovery scenarios. Management tools for Hyper-V include Hyper-V Manager, a graphical interface for managing Hyper-V, PowerShell, a powerful scripting interface automation, System Center Virtual Machine Manager for centralized management, and remote server administration tools for remote management. In summary, Hyper-V's architecture is designed to provide efficient and scalable virtualization solutions with a clear separation between the host system and the virtual machines running on it. The key components include the hypervisor layer, virtual machines, virtual networking, and storage management, all controlled by powerful management tools. This modular and flexible architecture allows Hyper-V to scale from small deployments to large enterprise environments with multiple VMs, ensuring high performance, isolation, and manageability. Replication health is crucial for maintaining the integrity and availability of our data across systems. In Hyper-V, for instance, monitoring VM replication ensures that our virtual machines are ready for disaster recovery. We need to keep an eye on the replication status, whether it's normal, in progress, out of sync, or failed. Each of these statuses tells us something vital about our data's safety. Similarly, in storage replica, we track health indicators like replication rate and log shipping to ensure our data mirrors are consistent. If we see replication lag or errors, it's a clear sign we need to act fast. In SQL Server, monitoring replication status and latency is essential. High latency can indicate network issues, while a failed status might point to agent problems. Tools like SQL Server Management Studio and PowerShell are invaluable for keeping our replication process running smoothly. Regular monitoring, checking event logs, ensuring network stability, and maintaining sufficient disk space are best practices that can't be overlooked. By staying proactive, we can ensure our replication health is robust, safeguarding our data and ensuring business continuity. Replication health typically refers to the status and operational health of data replication mechanisms in a system, specifically in environments where replication is used to maintain consistency, redundancy, and disaster recovery. In the context of Hyper-V, Storage Spaces Direct, SQL Server, or other systems that leverage replication technologies, replication health indicates whether the replication process is functioning correctly and whether the data being replicated is consistent and up to date. In Hyper-V, virtual machine replication is a feature used to replicate VMs from one Hyper-V host to another, often in different locations. This is crucial for disaster recovery because it allows VMs to be quickly restored in the event of failure. Keeping track of the health of these replications ensures that the data and VM states are being correctly replicated to the target server or storage location. Replication status indicates whether replication is active, paused, or failed. Replication health can be affected by various issues, including network disruptions, disk space issues, or VM configuration changes. Health indicators include normal, where replication is healthy and up to date. Replication in progress, where data is being transferred to keep the replica synchronized. Out of sync, where the replica is behind the primary VM and requires manual intervention or troubleshooting to sync. And replication failed, where a critical error occurred that prevents replication from working correctly. Replication metrics include last replication time, the time of the last successful replication. Replication interval, the time period between replication cycles. Replication data size, how much data has been replicated. And replication health logs, detailed logs that help identify specific issues if replication fails or becomes unhealthy. Monitoring tools include Hyper-V Manager, which displays replication status for VMs and can alert you to issues. PowerShell CMDlets, such as Get VM Replication, Start VM Replication, and Stop VM Replication, which allow administrators to manage and check replication health programmatically. System Center Virtual Machine Manager, SCVMM, which provides a centralized management interface for monitoring Hyper-V replication in large environments. And Event Logs, which contain detailed information about replication status and errors. In Storage Replica, replication is used to create a mirrored copy of data between two storage locations, either within the same site or across geographically separated sites. This replication is often part of a disaster recovery strategy. Health indicators for Storage Replica include healthy, where replication is occurring correctly and the replicated data is consistent. In progress, where data is actively being replicated or synchronized. Fail, where replication has encountered an issue. And out of sync, where data between the primary and secondary replica is inconsistent and require manual intervention to bring them back into sync. Key metrics in Storage Replica include replication rate, the speed at which data is being replicated, log shipping, where logs of change are shipped between sites, replication lag, a delay between the source and the replica, replication errors, which can cause replication to fail, and replication logs, which can be checked in Event Viewer and PowerShell for any warnings or errors related to the replication process. SQL Server uses database mirroring, log shipping, always-on availability groups, and replication for high availability and disaster recovery. SQL Server replication health indicators include replication status, which tells you whether SQL Server replication is functioning correctly. Normal, everything is functioning properly. Suspended, where replication has been paused. And failed, where there is an error in replication. Replication latency is the time it takes for changes to propagate from the publisher to the subscriber, and high latency can indicate network or resource issues. Replication. Agent status involves monitoring the health of SQL Server replication agents responsible for different parts of the replication process. Monitoring tools in SQL Server include SQL Server Management Studio, SSMS, which provides a GUI to monitor replication health, Replication Monitor, a tool in SSMS specifically for monitoring replication performance, and PowerShell, where SAMDlets like SQL replication status can be used to check the health of SQL Server replication. Best practices for monitoring and maintaining replication health include regular monitoring, where alerts can be set up to monitor replication status in real time, checking event logs for errors or warnings, ensuring network stability, as replication relies on stable connections, ensuring sufficient disk space, as replication can fail if there is insufficient space, keeping the replication configuration consistent after any changes, and testing failover regularly to ensure that your replication disaster recovery strategy is effective. Replication health is essential for ensuring that replicated data remains consistent, available, and accurate across systems or sites. In Hyper-V, storage replica, and SQL Server, replication is a cornerstone of high availability and disaster recovery strategies. By continuously monitoring the status of replication, using the right tools, and responding promptly to errors or failures, organizations can maintain a healthy replication environment and ensure business continuity. In Hyper-V, virtual networks are crucial for seamless communication between virtual machines, the host, and external networks. Think of them as digital highways, allowing VMs to interact while ensuring security and isolation. At the core of this setup is the virtual switch, a software-based switch that connects everything. There are three main types of virtual networks. The external virtual switch, which links VMs to the internet and local networks. The internal virtual switch, allowing communication between VMs and the host without external access. And the private virtual switch, where VMs can only talk to each other, perfect isolated testing environments. Setting these up is straightforward in Hyper-V Manager or via PowerShell commands. Plus, with different virtual network adapter types, you can optimize performance based on your needs. Understanding these elements is key to creating a robust and secure virtualized environment. In Hyper-V, virtual networks are crucial for seamless communication between virtual machines, the host, and external networks. Think of them as digital highways that allow VMs to interact while ensuring security and isolation. Hyper-V employs a virtual switch, a software-based tool that connects VMs to each other and the outside world. There are three main types of virtual networks. First, the external virtual switch connects VMs to the internet and your corporate LAN, perfect for scenarios where VMs need to communicate with external resources. Next, the internal virtual switch allows VMs to talk to each other and the host, but keeps them isolated from the outside world, ideal for testing and development. Finally, the private virtual switch creates a completely isolated environment where VMs can only communicate with one another, perfect for secure testing or sandboxing. By mastering these virtual networks, you can optimize your Hyper-V environment for performance and security. Hyper-V, virtual networks are crucial for enabling seamless communication between virtual machines, the host, and external networks. Think of them as digital highways that mimic physical networks while ensuring security and isolation. At the core of this setup is the virtual switch, a software-based switch that connects VMs to each other and to the outside world. There are three main types of virtual networks. The external virtual switch, which connects VMs to the internet and local networks. The internal virtual switch, allowing communication between VMs and the host without external access. And the private virtual switch, which isolates VMs entirely, letting them talk only to each other. Each type serves unique purposes, from providing internet access to creating secure testing environments. With Hyper-V, you can easily configure these switches through the Hyper-V Manager or PowerShell, tailoring your virtual network to meet specific needs. Understanding these options empowers you to optimize your virtualized environment effectively. In Hyper-V, virtual networks are essential for enabling communication between virtual machines, VMs, the host, and external networks, such as LAN and internet. These virtual networks mimic physical networks and allow virtual machines to interact with each other, the Hyper-V host, and external systems, all while maintaining isolation and security. Hyper-V uses a virtual switch to manage virtual networking. A virtual switch is a software-based network switch that connects the VMs to each other and the external network. There are three main types of virtual networks in Hyper-V: external virtual switch, internal virtual switch, and private virtual switch. An external virtual switch connects virtual machines to an external network, such as the internet or a corporate LAN. It binds to a physical network adapter on the host, allowing VMs to access the same network as the host. This setup is ideal for scenarios where VMs need to communicate with the outside world or with other machines on the physical network. Key features include VMs being able to access the internet, other VMs on the same physical network, and external resources. The virtual switch connects to the physical NIC on the host, enabling communication between VMs and the physical network, including the host. Common use cases include internet access for VMs, virtual machines in the same network, and networking between Hyper-V hosts. To configure an external virtual switch, create it in Hyper-V Manager and select the physical NIC to bind it to. VMs connected to this switch will use the physical network adapter of the host for network communication. An internal virtual switch allows communication between virtual machines on the same Hyper-V host and the host itself, but does not provide access to external networks. This type of virtual network is used when you want to isolate VMs from the external network, but still allow communication between the VMs and the host. Key features include VMs being able to communicate with the host and other VMs on the same Hyper-V host, while VMs cannot communicate with external networks. This is useful for testing, isolated environments, or when you need to ensure VMs only interact with the host and other VMs. Common use cases include private networks for VMs and non-internet facing applications. To configure an internal virtual switch, create it in Hyper-V Manager that binds to the host virtual network adapter. The VMs can now communicate with each other in the host, but will be isolated from the physical network. A private virtual switch allows virtual machines to communicate only with each other on the same host. There is no communication between the VMs and the host, nor with any external networks. This is the most isolated network type in Hyper-V. Key features include VMs connected to a private virtual switch being able to communicate only with each other, while they can't communicate with the host or external networks. This is useful for scenarios where you want to create a completely isolated virtual network for testing or sandbox environments. Common use cases include isolated testing environments and creating virtual private networks. To configure a private virtual switch, create it in Hyper-V Manager, which will isolate the VMs from the host and external networks. VMs connected to the switch can only communicate with each other. To create a virtual switch in Hyper-V Manager, open Hyper-V Manager, click on Virtual Switch Manager, choose the type of virtual switch from the available options, and for an external switch, select the physical NIC on the host to bind to the virtual switch. Set the desired network adapter and click Apply. For internal or private switches, there is no physical NIC selection. You can simply create the switch. After creating virtual switch, you can go to the VM settings and assign it to desired virtual switch. VM will then have network connectivity as defined by the switch type. You can also use PowerShell to create virtual switches. For creating an external virtual switch, use the command new VMS switch, name external switch, net adapter name Ethernet, allow management OS true. For creating an internal virtual switch, use new VMS switch, name internal switch, switch type internal. For creating a private virtual switch, use new VM switch, name private switch, switch type private. Each virtual machine in Hyper-V can be connected to a virtual network through a virtual network adapter. Hyper-V provides different types of virtual network adapters, depending on the VM's needs. A standard network adapter works with both legacy and modern VMs, and is supported for both internal and external virtual switches. A synthetic network adapter uses Hyper-V integration services for high-performance communication, providing better throughput and lower latency compared to legacy network adapters, and is only supported in newer VMs with integration components installed. A legacy network adapter is used for older VMs, or when integration services are not installed and may be necessary for specific legacy operating systems that do not support synthetic adapters. A team network adapter allows the VM to connect to a network adapter team, combining multiple physical NICs into one logical NIC for redundancy and increased bandwidth. In terms of network isolation and security, Hyper-V allows you to configure VLAN tags on virtual switches, enabling VMs to participate in virtual LANs for network segmentation and security. Using different types of virtual switches, you can achieve the isolation necessary for various use cases, such as sandbox testing and isolated production environments. Hyper-V also integrates with network security policies and can support network security groups, firewall rules, and quality of service policies for VM to VM or VM to host communications. When performing live migration of VMs between hosts, Hyper-V maintains virtual network connectivity by ensuring the VM's virtual network adapters are reconnected to the appropriate network on the target host. In summary, Hyper-V provides flexible virtual networking capabilities that allow administrators to configure isolated external or internal networks to meet the needs of their virtualized environment. Virtual switches are at the heart of Hyper-V's networking architecture, providing options for network isolation, performance, and security. Understanding how to configure these virtual networks properly ensures effective communication between VMs, the host, and external resources in any virtualized environment. When discussing storage devices like HDDs, SSDs, and NVMe SSDs, it's important to understand key differences in technology, performance, and use cases. Here's a breakdown of each. HDDs are mechanical devices that store data on spinning magnetic platters. A read-write head moves over the platter to access data. HDDs are much slower than SSDs. Typical read-write speeds range from 80 MB/s to 160 MB/s. They offer high storage capacities, often in the range of 1 GB to 16 TB or more. HDDs are the most affordable per gigabyte of storage. However, they are more prone to failure because of their moving parts, such as the motor and spinning platters. They are ideal for mass storage needs, like archival, video storage, and backup, where speed isn't as critical. SSDs use NAND flash memory to store data, and unlike HDDs, they have no moving parts. SSDs are significantly faster than HDDs, with typical read-write speeds ranging from 200 Mbps to 550 Mbps for SATA SSDs. They are available in various capacities, typically between 150 GB to 40 TB. SSDs are more expensive than HDDs, but the price has been dropping steadily. They are more durable than HDDs due to the lack of moving parts, although they do have a limited number of write cycles. SSDs are great for operating systems, applications, and gaming, where fast read-write speeds improve overall performance. NVMe is a protocol designed specifically for SSDs that connects directly to a motherboard via PCIe lanes, often using M2 or U2 connectors. NVMe SSDs use NAND flash memory, but their interface is much faster than SATA SSDs. Key differences include speed, where HDDs are slower than SATA SSDs, which are slower than NVMe SSDs. NVMe SSDs are the fastest, with speeds several times greater than traditional HDDs or even SATA SSDs. In terms of interface, HDDs use SATA, which has a limited bandwidth. SATA SSDs also use SATA but are limited by the interface, while NVMe SSDs use PCIe and provide much faster data throughput. Regarding form factor, HDDs are typically 3.5 or 2.5 drives. SATA SSDs are also 2.5, but thinner, and NVMe SSDs are generally small, using an M.2 form factor. In conclusion, HDDs are best for large storage at a low price, with relatively slower performance. SATA SSDs offer a good balance of speed and cost for general-purpose computing tasks. NVMe SSDs provide cutting-edge performance, especially in high-demand applications or gaming. Choosing between these options depends on your needs. If you want storage capacity and cost-effectiveness, an HDD may be the way to go. If you want speed for your operating system and applications, an SSD or NVMe SSD is the better choice. When it comes to networked storage solutions, NAS and SAN are two heavyweights, each with its own strengths. NAS, or network attached storage, is like your friendly neighborhood file server. It connects to your network via Ethernet and allows multiple devices to access files using familiar protocols like SMB or NFS. It's perfect for homes and small offices where ease of use and file sharing are key. On the other hand, SAN, or Storage Area Network, is the powerhouse designed for high-performance needs. It operates at the block level, allowing to access storage as if it were a local drive. This makes SAN ideal for enterprise applications, databases, and virtualized environments where speed and reliability are crucial. While NAS is user-friendly and cost-effective, SAN offers unmatched performance and scalability, making it the go-to choice for data centers and mission-critical applications. So whether you need simple file sharing or robust high-speed storage, understanding these differences can help you choose the right solution for your needs. When it comes to networked storage solutions, NAS and SAN are two heavyweights, each with its own strengths. NAS, or network attached storage, is like your friendly neighborhood file server. It connects via Ethernet, allowing multiple devices to access files using protocols like SMB or NFS. Perfect for homes and small offices, NAS is user-friendly and great for file sharing, but it can slow down when many users access large files simultaneously. On the other hand, SAN, or Storage Area Network, is the powerhouse of storage solutions. It operates at the block level, connecting storage devices directly to servers through high-speed networks like Fiber Channel or ISCSI. This means lightning-fast data access, making SAN ideal for enterprise applications, databases, and virtualized environments. While SANs are more complex and costly, their scalability and performance make them indispensable for high-demand scenarios. So if you need simple file sharing and ease of use, go for NAS. But if your needs are more intensive, with a focus on speed and reliability, SAN is the way to go. File-level storage and block-level storage are two distinct methods of data management, each with its own strengths. File-level storage organizes data like files on your computer, making it user-friendly and perfect for sharing in collaborative environments. Think of NAS systems, where you easily access documents and media. However, it can struggle with performance when handling large data loads. On the other hand, block-level storage breaks data into fixed-size chunks, allowing for faster access and greater control. This method is ideal for high-performance applications like databases and virtual machines, where speed is crucial. While it offers efficiency and scalability, it requires more complex management and isn't as user-friendly. In essence, choose file-level storage for simplicity and collaboration, while block-level storage shines in performance-driven scenarios. Each approach serves its purpose, depending on your specific needs. File-level storage and block-level storage are two fundamental approaches to how data is stored, accessed, and managed in computer systems. They are used in different types of storage systems and have distinct characteristics that make them suitable for different use cases. Let's break down the differences. File-level storage refers to the method of storing data in files and directories, much like how you would organize files on your personal computer. The storage system manages files and directories, and when data is read or written, the file system is responsible for accessing specific files within the storage medium. In file-level storage, data is stored as complete files, and the storage system organizes these files in a hierarchy. The storage system, such as NAS, handles both the file system and the organization of data. When you access a file, the operating system calls a file protocol to access that file over the network or locally. Common protocols include FS, SMB, CIFS, and AFP. Key characteristics of file-level storage include data access to files and directories, management of file-level operations by the storage system, operations done at the file level, and suitability for environments where multiple users need to share files. Use cases include NAS systems for centralized file sharing, media storage, and file backup. Advantages of file-level storage are its simplicity, file-based access, and user-friendliness. However, it has disadvantages such as performance efficiencies for applications requiring high-speed access and less control over data structure. Block-level storage works by storing data in blocks, which are small, fixed-sized chunks of data. These blocks are not tied to files or directories. Instead, they represent raw storage that applications use to write and read data directly from the disk. It's often used in SAN and is ideal for applications that need fast, low-latency access to raw data. In block-level storage, data is divided into blocks of a fixed size, and each block is addressed individually. The storage system provides raw blocks of storage to the server, which then organizes them into file systems or databases as needed. COM protocols include ISCSI, Fiber Channel, and FPoE. Key characteristics of block-level storage include direct interaction with storage blocks, management through block division, operations done at the block level, and faster performance suitable for high-performance applications. Use cases include SAN systems for high-performance storage, database storage, virtualized environments, and transactional applications. Advantages of block-level storage are its performance, flexibility, and efficiency. However, it has disadvantages such as complexity in management, less user-friendliness, and no native file sharing. The key differences between file-level and block-level storage include granularity, access type, performance, protocol, use cases, management, cost, scalability, and data integrity. File-level storage is accessed through file protocols, has slower performance due to file system overhead, and is generally more affordable. Block-level storage allows direct access to raw blocks of data, provides faster performance, and is more expensive due to its complexity. In summary, file-level storage is best when simplicity, file sharing, and ease of access are needed, while block-level storage is suited for performance-intensive environments where speed and low-latency access to raw data are critical. File sharing protocols are essential for seamless communication between devices over a network. Take SMB, for instance. It's the backbone of file sharing in Windows environments, allowing users to access files and printers effortlessly. Then there's NFS, which shines in Unix Linux systems, letting clients treat remote files as if they were local. AFP caters to Apple users, ensuring smooth file sharing across macOS devices, while FTP, one of the oldest protocols, simplifies file transfers but lacks encryption. For secure transfers, SFTP steps in, using SSH to protect your data. Lastly, WebDAV enhances collaboration by enabling users to manage files over the web, perfect for teams working together. Each protocol has its unique strengths, tailored to specific environments and needs. Choosing the right one can make all the difference in how efficiently you share and access files. File sharing protocols are communication methods that enable different devices or systems to share and access files over a network. These protocols define how data is transmitted between systems and how files are managed on the storage server. Below is an overview of the most commonly used file sharing protocols. SMB is one of the most widely used protocols for sharing files and resources like printers over a network, especially in Windows environments. It's a file sharing protocol that allows applications to read and write to files and request services from server programs in a computer network. SMB allows computers to communicate by sharing access to files, printers, and other network resources. It works over TCP/IP, uses ports 445, direct, and 139, NetBIOS. Key features include file sharing across local and wide area networks, support for user authentication, encryption and access control, the ability to share printers over the network, and enabling discovery of devices in a network. Common use cases include Windows-based networks, file sharing in businesses or offices where multiple users access files stored on a central server. Versions include SMB 1.0, which is obsolete and insecure, and SMB 2.0 and 3.0, which are faster, more secure, and efficient. An example is a Windows computer sharing a folder on a network, and other Windows or even Mac OS Linux computers can access and modify files within that folder. NFS is a file sharing protocol developed by Sun Microsystems and primarily used in Unix Linux environments. It allows different systems to share files over a network as if they were local files. NFS allows a server to share directories and files, which clients can mount and access as part of their local file system. It communicates over TCP/IP and typically uses port 2039. Key features include cross-platform compatibility, enabling network clients to access remote files as if they were stored, being stateless, and being efficient and scalable for large-scale file sharing. Common use cases include shared network drives in Linux Unix environments and large-scale enterprise systems and data centers. An example is a Linux server sharing a directory, and other Linux or Unix systems can mount that directory as if it were part of their local file system. AFP, a file sharing protocol used in Apple Mac OS systems, allowing file sharing over a network. It was the standard Apple protocol before SMB became more widely supported in recent versions of Mac OS. AFP works over TCP/IP and allows Apple devices to access files stored on a network device, such as a file server or NAS. AFP uses port 548 for communication. Key features include tight integration with macOS, support for file permissions and resource forks, and file locking to prevent conflicts when multiple users access the same file. Common use cases include Apple ecosystems in homes and businesses that rely on Mac computers and integration with legacy Apple devices. An example is a Mac computer sharing a folder, and other Macs can mount and interact with the shared files using AFP. FTP is one of the oldest and simplest file sharing protocols used to transfer files between computers over a TCP/IP network. It is commonly used for uploading and downloading files to and from a server. FTP operates in a client-server model, where the client requests files from a server, and the server responds by sending or receiving files. FTP communicates over ports 20, data, and 21, control. Active mode and passive mode are two different methods FTP can use to establish connections. Key features include primarily transferring files between computers, standard FTP not providing encryption, though FTPS and SFTP offer secure alternatives, and requiring a username and password for access, though anonymous FTP is also supported. Common use cases include website management and transferring large files between systems. An example is a website administrator uploading a file to a web server using FTP. SFTP is a secure version of FTP, which uses SSH, secure shell, to encrypt the data transfer between the client and server, ensuring confidentiality and integrity. SFTP operates over an encrypted SSH connection, typically using port 22. It provides a secure method for transferring files, listing directory contents, and managing files on the remote server. Key features include encryption of all data using SSH, requiring SSH authentication, and allowing file management in addition to file transfer. Common use cases include secure file transfer for sensitive data, and remote administration for file management on servers, particularly in enterprise environments. An example is a system administrator securely uploading a file to a server using SFTP. WebDAV is an extension of HTTP that allows users to manage and edit files stored on web servers. It's often used to create a shared environment for collaboration and document management. WebDAV allows users to mount remote file systems and access files through HTTPS. It operates over port 80 HTTP or port 443 HTTPS. WebDAV allows for file locking, metadata management, and versioning, making it ideal for collaborative environments. Key features include users being able to read, write, and delete files, manage directories over the web, support for versioning and locking of documents for collaborative editing, and availability of WebDAV clients for all major platforms. Common use cases include collaborative file sharing and document management and web-based applications that require access to remote files. An example is a team collaborating on documents stored on a WebDAV server, with each user able to edit files and manage file versions securely. Choosing the right file sharing protocol depends on your environment and use case. SMB is best for Windows environments. NFS is ideal for Unix/Linux file sharing. AFP is suited for Apple-based networks. SFTP is suitable for file transfers, with SFTP being the more secure option. WebDAV is perfect for web-based collaboration and document management. Each protocol has its strengths and specific use cases, so selecting the right one depends on the operating systems you're using and the level of security and functionality you require.
Data deduplication is a game changer in data management. Imagine you have a mountain of files, but many of them are just duplicates. Deduplication steps in to slice that mountain down to size. It starts by breaking data into smaller chunks, creating unique fingerprints for each one. When a new chunk comes in, it checks against existing fingerprints. If it finds a match, it doesn't store the duplicate. Instead, it keeps a pointer to the original. This means only unique data takes up space, leading to massive storage savings. In backups, for instance, if only a fraction of files change, deduplication ensures you're not wasting space on unchanged data. It's not just about saving space, it speeds up data transfers and cuts costs too. However, it's not without challenges. There's potential performance overhead and complexity in implementation.
But when done right, deduplication transforms how we store and manage data, making it leaner and more efficient. Data deduplication is a game changer in data management. Imagine you have a mountain of files, but many of them are just duplicates. Deduplication steps in to slice that mountain down to size.
Data deduplication, or simply dedup, is a data optimization technique that eliminates redundant copies of data in order to reduce storage requirements. In simple terms, it ensures that only a single copy of a piece of data is stored, while any subsequent copies are replaced with pointers to the original data. The process of deduplication begins with data chunking, where the data is divided into smaller chunks, often called blocks or segments. These chunks can be a fixed size, like 4 KB, or variable size in variable length deduplication. Next, each chunk is processed using a hashing algorithm, such as MD5, SHA, or CRC32, to create a unique hash or fingerprint for that chunk. This ensures that identical chunks will have the same hash. The system then compares the hash of each new chunk with the hashes of previously stored chunks in a database or index. If a chunk's hash matches a previously stored chunk, the system doesn't store the chunk again. Instead, it stores a reference to the already existing chunk. This leads to storage optimization, where only unique chunks are stored, greatly reducing the amount of data that needs to be stored, discarding duplicates. There are different types of deduplication. File-level deduplication, also known as single-instance storage, looks at entire files and checks if an exact duplicate exists. If the file is already stored, any new copy of that file is not stored, but instead a reference to the original is created. This method is best for situations where files are mostly identical, such as backup files or documents. It is simple and easy to implement, but less efficient in environments where file contents change frequently. Block-level duplication, on the other hand, breaks files into smaller blocks and checks if individual blocks are duplicated. This method is more granular and efficient, especially in environments with many small, similar files, but it can be more complex and incur overhead for indexing and comparing blocks. Variable length deduplication dynamically determines the best way to break data into chunks of varying sizes, using a more sophisticated algorithm to detect similarities across different data patterns. This approach can be more efficient for certain types of data, but is also more computationally intensive. The benefits of data deduplication are significant. The primary benefit is storage space savings, as deduplication reduces the amount of storage space required by eliminating redundant data. It also improves backup efficiency, especially in backup environments where large amounts of redundant data are stored repeatedly. Common use cases for deduplication include backup and archiving, where it is most commonly used to reduce redundancy in traditional backup systems. Cloud storage providers also utilize deduplication to reduce storage costs and optimize data transfer. In virtualized environments, deduplication can significantly reduce storage requirements by eliminating repeated data across virtual machines. Email systems benefit from deduplication by reducing the storage overhead associated with redundant emails, while data replication and WAN optimization see advantages as only unique data is transmitted, speeding up data transfer. However, there are challenges and considerations with deduplication. Performance overhead can be a concern, as deduplication may add computational overhead, particularly when indexing data and comparing chunks. This can impact performance, especially on systems with high throughput data. The complexity of implementing deduplication, particularly at the block level or with variable lengths, can require more sophisticated infrastructure. Additionally, if the deduplication index or database is corrupted, there's a risk that pointers to deduplicated data might be lost, potentially affecting data recovery or integrity. Latency can also be an issue, especially in real-time deduplication systems, as they may experience delays while checking each piece of data for redundancy. Lastly, duplication can sometimes cause data fragmentation, which might affect performance over time. For example, in a backup environment, a company backs up a directory with 1,000 files. Over a few weeks, only 100 of the files change, while the remaining 900 stay the same. Without deduplication, each backup would store all 1,000 files. With deduplication, the system stores only the new or changed data and references the existing data, saving substantial storage space. In cloud storage, if a user uploads files multiple times, the cloud system with deduplication would store only one copy of the file and reference it each time it is uploaded again, reducing both storage costs and bandwidth consumption. In conclusion, data deduplication is a powerful technique for optimizing storage, reducing costs, and improving backup, recovery, and data transfer processes. It is especially useful in environments like backup systems, cloud storage, virtualization, and data replication, where large amounts of redundant data are common. However, organizations must balance the benefits of storage savings with the potential performance and complexity overheads that deduplication may introduce. RAID, redundant array of independent disks, is a data storage technology that combines multiple physical disk drives into one or more logical units to improve performance, increase storage capacity, and provide redundancy, protection against data loss. Here are the common RAID types. RAID 0, striping. Data is split into blocks and distributed evenly across all drives. Advantages include improved performance with increased read and write speeds and full storage capacity of all disks with no overhead for redundancy. Disadvantages are that there is no redundancy. If one drive fails, all data is lost, and it is not recommended for critical or important data. Minimum disks required. 2. RAID. 1. Mirroring. Data is duplicated, mirrored, on 2 or more drives. Advantages include high data redundancy. If one drive fails, data is still available from the other, AUS, and RAID performance can improve since data can be read from multiple drives. Disadvantages are that storage capacity is halved, e.g., 2 1 TB drives give you 1 TB of usable space, and write performance might not improve. Minimum disks required. 2. RAID 5. Striping with parity. Data is striped across multiple drives with distributed parity, error checking information. Advantages include a good balance of redundancy, performance, and storage efficiency, and it can withstand the failure of one drive without data loss.
RAID 6, striping double parity. This is similar to RAID 5, but with 2 sets of parity information, providing extra fault tolerance. Advantages include the ability to withstand the failure of 2 drives without data loss and a good balance of redundancy and storage efficiency. Disadvantages are that write performance can be slower in RAID 5 due to additional parity calculations, and there is increased storage overhead compared to RAID 5. Minimum disks required. 4. RAID 10, 1+0 mirroring plugging. This combines the redundancy of RAID 1 and the performance of RAID 0 by mirroring data and then striping it across multiple drives. Advantages include high redundancy, can withstand multiple drive failures, as long as not both drives in a mirror set fail, and high read and write performance. Disadvantages are that it requires a minimum of 4 disks and storage efficiency is 50%, like RAID 1. Minimum disks required. 4. RAID 50, 5+0 stripe of RAID 5. This combines RAID 5 and RAID 0 by stripping data across multiple RAID 5 arrays. Advantages include providing the benefits of both RAID 5, redundancy, and RAID 0, performance, and can tolerate one drive failure per RAID 5 array. Disadvantages are that it is a more complex setup and management and requires at least 6 drives, 2 RAID 5 arrays of 3 or more drives each. Minimum disks required. 6.
RAID 60, 6+0, stripe of RAID 6. This is similar to RAID 50, but with RAID 6 arrays instead of RAID 5 and double parity. Advantages include greater fault tolerance than RAID 50, can tolerate up to 2 drive failures per RAID 6 array, and a good combination of performance and redundancy. Disadvantages are that it is more complex and requires at least 8 drives, with higher storage overhead than RAID 50. RAID 2, 3, 4, legacy or rarely used. These RAID levels are based on variations of striping with dedicated parity or ECC, error correction codes. They are rarely used today due to their inefficiency or reliance on specialized hardware. Other RAID variants include RAID 1E, a hybrid RAID 1, and RAID 0, where data is mirrored across pairs of drives and then striped. It's less common. RAID 7, a proprietary RAID level developed by Storage Computer Corporation, using caching to improve performance. It's not widely supported. RAID 10E, an extension of RAID 10 with some parity and caching improvements. JBOD, just a bunch of disks. This is not technically RAID, but simply a configuration where multiple drives are used independently, without any redundancy or striping. Data is stored across multiple disks, but without any RAID features like mirroring or parity. Each RAID level offers a different trade-off between performance, fault tolerance, and storage capacity, so the best choice depends on the specific needs of the user or system. Dynamic disks are a type of disk configuration in Microsoft Windows operating systems, offering more advanced features than basic disks. They allow for more flexible storage configurations, such as the creation of volumes that span multiple disks, which is useful for larger storage needs, improved performance, or fault tolerance. Dynamic disk types include several types of volumes that can be created on dynamic disks. These volumes differ in how they organize data across multiple physical disks. The main types are simple volume, which is the basic type of volume that spans a single dynamic disk. It behaves similarly to a partition on a basic disk, but allows for better management features and can be extended onto other dynamic disks, but only after conversion to another type. It is best used for a single disk setup or for simple storage needs. Key points include that data is stored on one disk and it can be extended if more disk space is added, but only if the space is unallocated and available on the same disk. Dynamic disks are a type of disk configuration in Microsoft Windows operating systems, offering more advanced features than basic disks. They allow for more flexible storage configurations, such as the creation of volumes that span multiple disks, which is useful for larger storage needs, improved performance, or fault tolerance. There are several types of volumes that can be created on dynamic disks. These volumes differ in how they organize data across multiple physical disks. Below are the main types. A simple volume is the basic type of volume that spans a single dynamic disk. It behaves similarly to a partition on a basic disk, but allows for better management features and can be extended onto other dynamic disks, but only after conversion to another type. Best used for a single disk setup or for simple storage needs. Data is stored on one disk, can be extended if more disk space is added, but only if the space is unallocated and available on the same disk. A span volume allows data to be written across multiple physical disks. The data is spanned across multiple disks, using all the available space on each of the disks involved. Essentially allows a volume to span over 2 or more disks. Useful for extending storage without having to partition individual drives. Can span multiple dynamic disks. Does not provide redundancy, If one disk fails, the entire volume is lost, can be used when you have several smaller disks and want to combine them into one larger volume. A striped volume, RAID 0, divides data into blocks and writes them across multiple disks, improving performance. Data is striped across 2 or more disks, which allows for faster read and write speeds since multiple disks can be accessed simultaneously. Best for applications requiring high performance, such as video editing and gaming, provide improved performance, faster read-write speeds. No redundancy. If one disk fails, data on the entire striped volume is lost. Requires at least 2 disks. A mirrored volume is a copy of a volume stored on 2 or more disks, providing redundancy. Data is written to 2 or more disks, which means each disk is a mirror of the other EES. This redundancy protects against data loss in case one disk fails. Ideal for critical data, where uptime and data integrity are important. Provides fault tolerance. If one disk fails, data is still available from the other disk. Storage capacity is limited to the size of the smallest disk in the mirror, e.g., 2 1 TB disks will provide 1 TB of usable space. Requires at least 2 disks. A RAID 5 volume combines data striping for performance with distributed parity for redundancy. Data is striped across multiple disks, and parity information is distributed across the disks, allowing for data recovery in case of a single disk failure. The parity data is used to reconstruct the lost data if one disk fails, best for scenarios where both performance and data redundancy are required, such as for file servers or enterprise storage solutions. A RAID 10 volume is a combination of RAID 1, mirroring, and RAID 0, striping. It offers both redundancy and performance. Data is mirrored across pairs of disks, RAID 1, and then striped, RAID 0, across the mirrored pairs. This configuration provides fault tolerance as long as no more than one disk in a mirrored pair fails, while also improving performance. Suitable for high availability systems where both performance and redundancy are critical. Combines the benefits of RAID 1, mirroring, and RAID 0, striping. Provides fault tolerance. Up to one disk in each mirrored set can fail without data loss. Requires at least 4 disks, 2 pairs of disks. Provides better performance than RAID 5, especially for write-intensive applications. Storage capacity is half the total disk space due to mirroring. You can convert a basic disk to a dynamic disk, but the reverse process, basic dynamic, can be complex and requires data backup since the data may be lost during the conversion. Dynamic disks allow for great flexibility with resizing volumes. You can extend volumes, e.g., simple or spent volumes, and shrink them with some restrictions. RAID configurations, such as RAID 1, RAID 5, RAID 10, provide fault tolerance, meaning the system can survive a disk failure and keep functioning, while configurations like striped spanned volumes do not offer this protection. Windows supports dynamic disks, but they are not supported by other operating systems like macOS or Linux without third-party software. Dynamic disks are most beneficial for users who require flexible, high-performance, or fault-tolerant storage configurations that go beyond the capabilities of basic disks. However, these features come with complexity and should be used when appropriate for the system's needs. When it comes to file systems, each has its unique strengths tailored to different needs. Take FAT32, for example. It's like the reliable old friend of file systems, super compatible with almost everything, but it can't handle files over 4 GB. Then there's NTFS, the powerhouse of Windows, supporting massive files up to 16 TB and offering features like encryption and journaling for data recovery. Now, if you're in an enterprise environment, ReFS is your go-to. With its focus on data integrity and fault tolerance, it can manage up to 35 PB. And let's not forget exFAT, the cross-platform champion, perfect for flash drives and SD cards, handling files up to 16 without the overhead of NTFS. Choosing the right file system boils down to your specific need, compatibility, size, and whether you need those advanced features. Each option has its place in the digital landscape. When it comes to file systems, each has its unique strengths tailored to different needs. Take FAT32, for example. It's like the reliable old friend of file systems, super compatible with almost everything, but it can't handle file 4 GB. Then there's NTFS, the powerhouse of Windows, supporting files up to 16 TB and offering features like encryption and journaling for data recovery. FAT32, or File Allocation Table 32, is a file system that's like the Swiss Army knife of storage, widely compatible across Windows, macOS, Linux, and even game consoles. It's perfect for USB drives and memory cards, where you need that seamless plug-and-play experience. But it does have its quirks. The maximum file size is capped at 4 GB, so if you're trying to store that epic movie or a massive game, you're out of luck.
Plus, with a maximum volume size of 2 terabytes, it's not built for heavy lifting. While FAT32 is reliable, it's also a bit of a relic, lacking modern features like file permissions and journaling. So, while it gets the job done for small devices, it's not the go-to for advanced storage needs. FAT32 is widely supported across many operating systems, including Windows, macOS, Linux, and even embedded devices like game consoles.
The max file size is 4 GB, meaning larger files cannot be stored on FAT32. The max volume size is 2 TB with the default sector size. It's often used for smaller storage devices like USB drives and memory cards, where compatibility is essential. However, it's older and lacks some features, such as file permissions and journaling, that newer file systems provide. NTFS, or New Technology File System, is the backbone of Windows storage. It's designed for efficiency and reliability, supporting massive file sizes up to 16 TB and volumes as large as 256 TB. What sets NTFS apart are its robust features. It offers file permissions for security, encryption to protect your data, and even disk quotas to manage storage effectively. Plus, it includes compression to save space and journaling, which helps recover from crashes seamlessly. While primarily a WinMat, NTFS can also be accessed on Linux and macOS with the right drivers. This makes it the go-to choice for internal drives on PCs, especially when handling large storage volumes. If you're looking for a reliable file system that balances performance and security, NTFS is definitely the way to go. NTFS, New Technology File System, compatibility, primarily used but can be read and sometimes written on Linux and macOS with additional drivers. Max file size, 16 TB, with a default cluster size. Max volume, 256 TB. Features, supports file permissions, encryption, disk quotas, compression, and journaling. Helps recover from crashes. Use case, best for Windows installations and large storage volumes, especially for internal drives on PCs. ReFS, or Resilient File System, is a game changer for data management, especially in enterprise environments. Unlike NTFS, ReFS is specifically designed for Windows Server and advanced Windows 10 and 11 features, which means it's not as widely compatible. But what it lacks in compatibility, it makes up for in sheer capability. Imagine handling a staggering 35 petabytes of data. Yes, that's the maximum file and volume size. What really sets ReFS apart is its focus on data integrity. It comes with built-in resiliency features like error correction and self-healing, making it highly fault-tolerant. This means your data is not just stored, it's protected. For file servers and large storage solutions where every byte counts, ReFS is the go-to choice. It's all about keeping your data safe and sound, ensuring that you can focus on what really matters, your business. ReFS is designed for Windows Server and advanced Windows 10 to 11 features. It's not as widely compatible as NTFS. The maximum file size is 35 petabytes, and the maximum volume size is also 35 PB. It focuses on data integrity with built-in resiliency features like error correction and self-healing. It's designed to be highly fault-tolerant and is used primarily in enterprise environments, for file servers, and large storage solutions where data integrity is crucial. exFAT, or Extended File Allocation Table, game changer for file storage. It's designed for compatibility, seamlessly bridging Windows and macOS, making it the go-to choice for flash drives, external hard drives, and SD cards. Imagine a max file size of 16 exabytes. Yes, exabytes. That's a staggering amount, far surpassing FAT32. Plus, with a maximum volume size of 128 petabytes, you'll never run out of space anytime soon. What makes exFAT appealing is its simplicity. It lacks the overhead of NTFS, which is lighter and faster for removable media. However, it doesn't come with the advanced features of NTFS, like journaling or permissions. But for devices that need to be cross-platform, like cameras and USB sticks, exFAT is ideal. It's all about convenience and efficiency, ensuring your files are accessible wherever you go. When it comes to file systems, choosing the right one can make all the difference. Let's break it down. FAT32 is your go-to for USB drives and SD cards, but it caps file sizes at 4 GB. Perfect for smaller files, but a hassle for anything larger. Then there's NTFS, the heavyweight champion for internal drives on Windows. It supports massive files up to 16 TB and offers robust file permissions and journaling for data integrity. Now, if you're dealing with servers, ReFS is the way to go, boasting a staggering 35 PB max file size and built for resilience. But it's Windows Server only. For those who need cross-platform compatibility, exFAT shines, allowing for 16 EB, making it ideal for external storage across Windows and macOS. Each file system has strengths, so pick wisely based on your needs. When it comes to file systems, choosing the right one can make all the difference. Let's break it down. FAT32 is your go-to for USB drives and SD cards. Caps file sizes at 4 GB, perfect for smaller files, but a hassle for anything larger. Then there's NTFS, the heavyweight champion for internal drives on Windows. It supports massive files up to 16 TB and robust file permissions and journaling for data integrity. DFS, or distributed file system, revolutionizes how we manage files across multiple servers in a network. Imagine having a single unified directory that makes accessing files a breeze, no matter where they're stored. With DFS namespace, you can create a virtual file system that combines various file shares into one logical structure. Instead of hunting through R server 110 files or Dark server 2 files, you simply navigate to Hard company namespace files. But that's just the beginning. DFS replication ensures your files are always available, even if a server goes offline. It uses a multi-master model, meaning any server can be updated, and those changes will sync across the board. This not only enhances redundancy, but also keeps your data consistent across different locations. And let's not forget about fault tolerance and load balancing. If one server goes down, clients are seamlessly redirected to another server, ensuring uninterrupted access and improved performance. Plus, with offline files, you can work without a network connection, and your changes will sync up once you're back online. DFS is a game changer, especially for branch offices, keeping everyone connected and productive no matter where they are. DFS stands for Distributed File System. It is a set of technologies used to organize and manage files across multiple servers in a network, enabling centralized file access and easier file management. DFS is often used in large organizations where files are stored on multiple servers but need to appear as a unified single logical directory. Key features of DFS. DFS namespace allows administrators to create a virtual file system that aggregates multiple file shares into a single logical structure. This makes it easier for users to access files without worrying about which server they are stored on. For example, instead of users having to navigate to Dark server 1 dented files, RU server 2 dented files, and so on, they can access everything through RU company namespace files. DFS replication is a service that ensures files are replicated between multiple servers for redundancy and availability. It allows files to be replicated across different locations, such as branch offices, so that users can access the same files even if one server goes offline. It uses a multi-master replication model, meaning all servers can be updated and changes will be replicated across the system. DFS ensures that file access is not disrupted if one server becomes unavailable. If one server goes down, clients are redirected to another server hosting the same files. This also helps balance the load by allowing multiple servers to share the access requests, improving performance. DFS allows users to work with files even when they are offline, for example, in remote or disconnected environments. Changes made offline will be synchronized with the network once the user reconnects. DFS is particularly useful for remote or branch offices. Through DFS replication, files can be synchronized between the main office and remote locations to ensure data consistency. Imagine accessing a file without needing to know where it's physically stored. That's the magic of DFS, or Distributed File System. When you connect to a DFS share, the system seamlessly directs you to the right server using logical paths, instead of confusing server names. Now let's talk about DFS replication. This feature works quietly in the background, ensuring that any changes you make to files are automatically synchronized across multiple servers. This means your data is safe and sound, reducing the risk of loss. DFS is a game changer for organizations. It centralizes file access, so different locations can easily find what they need. Plus, with data redundancy, critical files remain accessible even if one server goes down. And for branch offices, DFS makes file sharing efficient by replicating data locally. It's all about keeping your files available and secure, no matter where you are. How DFS works: DFS namespace. When a user accesses a DFS share, the system directs the user to the appropriate server hosting the file. This is done using logical paths rather than physical server names. DFS replication, DFSR. Files are replicated between different DFS servers. Replication happens in the background, with changes to files being automatically synchronized across servers, reducing the risk of data loss. Common DFS use cases: centralized file access. Users in different parts of an organization can access files without needing to know the physical location of the files. Data redundancy. DFS ensures that critical files are available even if one server fails, as the data is replicated across multiple servers. Branch office file sharing. It helps provide efficient file sharing across branch offices by replicating data locally to each office. When it comes to managing files across multiple servers, Distributed File System, or DFS, truly stands out. Unlike traditional file systems like NTFS, which operate on a single server, DFS creates a unified file access experience across a network. Imagine accessing your files seamlessly, no matter where they're stored. Built right into Windows Server, DFS can be easily configured through the DFS Management Console. It works hand in hand with Group Policy and Active Directory, making it an essential tool for organizations looking to streamline file sharing and management. With DFS, you can ensure that your team has consistent access to the files you need, boosting productivity and collaboration.
It's not just about storage. It's about creating an efficient, organized, and accessible file environment. DFS is specifically for managing files across multiple servers in a network and providing a unified file access experience, while other file systems, like NTFS, manage files on a single server or computer. DFS is built into Windows Server and can be configured through the DFS Management Console. It can be used alongside other services like Group Policy and Active Directory to create a comprehensive file sharing and management solution for an organization.
Data deduplication in Windows Server is a game changer for managing storage. Imagine having countless identical files cluttering your disk space: backup files, virtual machine images, or repetitive documents. Deduplication tackles this by breaking data into small chunks. Instead of saving every duplicate, it keeps just one copy and creates references for the rest. This means if several files share the same data blocks, only one is stored, drastically reducing storage needs. The magic happens at the block level, allowing for a more granular approach to finding redundancies. This precision leads to significant space savings, especially in environments packed with similar files. Plus, it generates metadata to track these blocks, ensuring that when you need to reconstruct a file, everything in place. In short, data deduplication not only optimizes storage, but also streamlines data management, making your SIR more efficient and effective. Data deduplication, DDup in Windows Server, is a feature that helps reduce the storage footprint of data by eliminating duplicate copies of repeating data. This can save a significant amount of disk space, especially in environments where there are many identical or similar files stored. Key concepts of data deduplication. Deduplication works by breaking down data into small blocks and then identifying duplicates. Rather than storing duplicate blocks, only one copy is kept, and references to that block are stored instead. For example, if multiple files contain identical chunks of data, only one copy of that chunk is kept, and the other files will reference that chunk. Deduplication can result in substantial storage savings, especially in scenarios where multiple similar files are stored, such as in file servers, backups, and virtual machine storage. Windows Server's deduplication works at the block level, meaning it looks at small segments of data rather than entire files. This allows it to find more granular redundancies and improve space savings. Deduplication typically involves creating metadata to track which data blocks are referenced by different files. This metadata is stored separately from the actual data, but allows the system to reconstruct files when needed. Imagine a vast library filled with countless books, but many of them are just duplicates. Deduplication is like a clever librarian who identifies those duplicate books, saving space and keeping things organized. First, it scans through the shelves, pinpointing identical blocks of data scattered across storage. Once these duplicates are found, the system rewrites the storage, keeping only one copy of each block. Think of it as a master copy that every book can reference. When you need to access a file, the system springs into action, dynamically reassembling it by pulling together those unique blocks. It's like piecing together a puzzle, ensuring that the final picture is complete and intact, with no loss of data integrity. This process not only optimizes storage, but also enhances efficiency, making data management smarter and more streamlined. The process starts with identifying duplicate blocks, chunks of data across your data storage. Once duplicates are identified, the system rewrites the storage so that only a single instance of each duplicate block is stored. The system then references that block whenever the data is needed by any file. When accessing a file, the system dynamically reassembles it by referencing the unique blocks and ensuring the file is returned to its original state without any loss of data integrity. Imagine a vast library filled with countless books, but many of them are just duplicates. Deduplication is like a clever librarian who identifies those duplicate books, saving space and keeping things organized. Data deduplication is a game changer when it comes to managing storage. Imagine slashing your disk space usage. It's like finding hidden treasure in your data center. By eliminating redundant data, you not only free up valuable space, but also make your storage resources work smarter, not harder. This efficiency translates directly into cost savings. And let's talk about backup times. With deduplication, your backup files shrink significantly, meaning you can back up your data faster and with less storage overhead. It's a win-win. Overall, data deduplication isn't just a technical improvement. It's a strategic advantage that enhances performance and reduces costs across the board. The most obvious benefit is a reduction in disk space usage.
This is particularly useful for storage-intensive applications like backup systems, virtualization, and file shares. By minimizing redundant data, deduplication allows more efficient use of available storage resources, which can reduce overall costs. When used with backup solutions, deduplication can reduce the size of backup files, leading to faster backup times and less storage space required for backups.
Windows Server has revolutionized data management with its deduplication feature, starting from 2012 and evolving through 2016, 2019, and 2022. This powerful tool shines with large files that contain repetitive data. Think virtual hard disks and database backups. But beware, files that are already compressed or encrypted like .zip or .exe won't see any benefits from this process. The beauty of deduplication is that it operates quietly in the background, ensuring your regular file system activities remain uninterrupted. It works seamlessly with NTFS and ReFS file systems, with ReFS often preferred for its enhanced performance and resilience. You can even schedule deduplication to run during off-peak hours, minimizing its impact on your system's performance. What's more, data integrity is a top priority. Each chunk of data is hashed, safeguarding against corruption throughout the deduplication process. And whether you prefer manual or automatic optimization, you can enable deduplication at the volume level for any NTFS or ReFS volume, giving you control over how much storage you save. It's a smart way to optimize your server and keep your data safe. Windows Server supports data deduplication starting with Windows Server 2012, and it has been improved in later versions, such as Windows Server 2016, 2019, and 2022. Windows Server deduplication works best with files that are large and contain repetitive data, such as virtual hard disk, VHD files, database backups, and other types of archives. It is not recommended to deduplicate files that are already compressed or encrypted, e.g. .zip, .exe, .iso, etc., because they likely won't benefit from the deduplication process. The process happens in the background, meaning it doesn't interfere with normal file system operations. Deduplication works with NTFS and ReFS file systems, though ReFS is often used with modern data deduplication workloads for improved performance and resilience. You can configure when the deduplication process should run using the data deduplication setting in Windows Server. This helps manage performance impacts, as deduplication can be CPU and I/O intensive. You can schedule deduplication to occur during off-peak hours to minimize the impact on system performance. Windows Server's deduplication process is designed to be safe and reliable, ensuring that data integrity is maintained. Each chunk of data is hashed to ensure it's not corrupted during the deduplication process. Data deduplication can be enabled at the volume level for any NTFS or ReFS volume on the server. It supports both manual and automatic optimization, allowing administrators to control the optimization level based on needs. Imagine a file server cluttered with countless duplicate files, like backup copies taking up precious space. By enabling data deduplication, you can reclaim that storage, making room for what truly matters. Now think about virtualization. Virtual machine disk images often contain data, and deduplication can drastically reduce footprint, optimizing your virtual environment. And let's not forget backup systems. They tend to store similar data across multiple versions, leading to unnecessary bloat. Deduplication swoops in to cut down those storage significantly. But it's not all smooth sailing. Deduplication can be CPU intensive, especially during the initial phase, so timing is crucial. Plus, keep in mind that files already compressed or encrypted won't see much benefit. So, while deduplication is a powerful tool, it's essential to know when and where to use it effectively. Use cases for data deduplication. File servers. If a server has many similar or duplicate files, e.g. backup files, deduplication can save significant storage space. Virtualization. Virtual machine disk images, VHD, VHDX, often contain redundant data, and deduplication can save considerable storage space in virtualized environments. Backup systems. Backups often store similar data across multiple versions. Deduplication can significantly reduce the storage requirements for backup considerations. Performance impact. Deduplication can be CPU intensive and might impact the performance of the system, especially during the initial deduplication phase. It's essential to schedule deduplication tasks appropriately and monitor performance. Not suitable for all data. Files that are already compressed, like video, image, or archive files, or encrypted, won't benefit much from deduplication. DCDAG is an essential command line tool for anyone managing Microsoft Active Directory environments. It's like a health checkup for your domain controllers. When you run DCDAG, it performs a series of tests that cover everything from DNS resolution to replication. Imagine it as a diagnostic tool that ensures your Active Directory is running smoothly. You simply open your command prompt and type in DCDAG. Instantly, it starts checking the health of your domain controllers, looking for issues that could disrupt your network. It provides detailed reports on each test, highlighting potential problems. If you see errors, you can dive deeper into specific tests to troubleshoot effectively. Using DCDAG regularly can save you from bigger headaches down the line, ensuring that your Active Directory environment remains robust and reliable. It's a straightforward yet powerful tool that every IT professional should have in their toolkit. DCDAG is a command line tool used in Microsoft Active Directory environments to diagnose the health of domain controllers. It performs a series of tests to ensure that your domain controllers are functioning properly, checking everything from DNS resolution to replication to ensure that the Active Directory service is operating smoothly. Here's a quick overview of how to use In Windows Server, when we talk about database page size, we're diving into the heart of SQL Server's architecture. The standard page size is 8 KB, and that's where all the action happens. Data reads, writes, and modifications occur at this level. Now, you might wonder about a 32 KB page size. The reality is, SQL Server doesn't support that. It's locked into the 8 KB format. Sure, you can explore other configurations, like using multiple file groups to enhance performance, or leveraging data compression to optimize storage. And while SQL Server's index pages also default to 8 KB, you can look at memory configurations in Windows Server, which can utilize larger memory pages for specific applications. If you're considering alternatives, other database systems might allow larger page sizes, but in SQL Server, you're sticking with 8 KB. So focus on tuning your indexes and compression strategies to get the most out of your database performance. In Windows Server, the database page size typically refers to the size of individual pages used by a database management system, DBMS, such as SQL Server. The standard page size for SQL Server is 8 KB. However, you're asking about a 32 KB page size. Here's a breakdown of the concepts around this. SQL Server uses a default 8 KB page size. Each page consists of data, and database operations, such as reads, writes, and modifications, are performed at the page level. As of now, SQL Server itself does not natively support a 32 KB page size for its data pages. The default page size is 8 KB, and SQL Server does not allow users to change the page size to 32 KB at the database level. You would need to stick with the 8 KB page size unless using a custom file configuration or considering other database engines that allow a custom page size. SQL Server does use other structures, like index pages, that can have a different effect on performance depending on the type of index, e.g., clustered versus non-clustered, but these also default to 8 KB pages. You might be asking about memory pages on the operating system level. Windows Server typically uses 4 KB as the default memory page size, but it can also work with large pages, e.g., 2 MB or 1 GB, for improved memory performance in certain contexts like large-scale applications and in-memory databases. However, this is different from database-level page sizes. If you're interested in performance improvements using a different page size, other options could include using multiple file groups in SQL Server to distribute data across multiple files or disks for performance. And SQL Server offers row-level and page-level compression, which can reduce the I/O overhead and effectively handle larger amounts of data per page. If you're referring to a different database system, e.g., MySQL, PostgreSQL, the default page size can vary, and some systems might allow configuration of larger page sizes, up to 32 KB or more. In SQL Server on Windows Server, the page size is generally fixed at 8 KB, and there is no built-in support for changing to 32 KB. If you're looking for optimization, you may want to look into other tuning options such as indexing, compression, or hardware optimizations. In Windows Server, when we talk about database page size, we're diving into the heart of SQL Server's architecture. The standard page size is 8 KB, and every operation, reads, writes, modifications, happens at this page level. Now, you might be curious about a 32 KB page size, but here's the catch. SQL Server doesn't support that. You're locked into the 8 KB format unless you explore custom file group configurations or consider other database systems that allow for larger page sizes. While SQL Server's index pages also default to 8 KB, you can optimize performance through strategies like using multiple file groups to distribute data or leveraging data compression techniques. And if you're thinking about memory, Windows Server does utilize larger memory pages, like 2 MB or even 1 GB for specific applications, but that's a different ballgame for database page sizes.
So, if you're aiming for efficiency, focus on indexing, compression, and hardware tweaks rather than changing the page size.
In Windows Server, memory pages are the building blocks of virtual memory, typically set at 4 KB. Here's where it gets interesting. Windows also supports larger pages, specifically 2 MB and even 1 GB sizes. Why does this matter? Well, larger pages can significantly boost performance, especially in memory-intensive applications. Take 2 MB pages, for instance. They reduce the overhead of managing memory by cutting down the number of page table entries the OS has to track. This means faster access and less strain on the system. Now, for those heavy hitters like SQL Server or large in-memory databases, 1 GB pages come into play. They're perfect for applications that demand vast amounts of contiguous memory, allowing them to operate more efficiently. In short, leveraging these large pages can lead to smoother performance and better resource management, making them a game changer for high-demand environments. In Windows Server, memory pages are the building blocks of virtual memory, typically set at 4 KB. But here's where it gets interesting. Windows also supports larger pages, specifically 2 MB and even 1 GB sizes. In Windows Server, memory pages are the building blocks of virtual memory, typically sized at 4 KB. But here's where it gets interesting. Windows also supports larger pages, specifically 2 MB and even 1 GB, known as large pages or huge pages. These larger sizes can significantly boost performance in memory-intensive applications. Take 2 MB pages, for instance. They reduce the overhead of managing memory by cutting down the number of page table entries the OS needs to track. This means faster access and better efficiency. Now, for those heavy hitters like SQL Server or massive in-memory databases, 1 GB pages come into play. They're perfect for applications that demand large swaths of contiguous memory, allowing them to operate more smoothly and efficiently. So, whether you're optimizing a database or running virtual machines, understanding and utilizing these memory pages can make a world of difference in performance. In Windows, a memory page is a fixed-length, contiguous block of virtual memory. The operating system divides the virtual memory into small pages, and these pages are managed by the Memory Management Unit, MMU. By default, Windows uses 4 KB as the standard page size for virtual memory, but it also supports the use of larger page sizes under certain conditions. Windows Server offers support for large pages or huge pages, which are significantly larger than the default 4 KB pages. These larger pages can provide performance benefits in memory-intensive applications. The most common large page size in Windows is 2 MB. These pages can improve performance by reducing the overhead of managing large amounts of memory, as they minimize the number of page table entries the operating system needs to track. In some cases, especially for very large applications or databases, you can use 1 GB pages, but these are typically used for applications that require large amounts of contiguous memory like SQL Server, large in-memory databases, or virtual machines. When it comes to virtual memory in Windows Server, 32 KB page sizes are a bit of a mystery. Unlike the standard 4 KB pages or the larger 2 MB 1 GB pages, 32 KB just doesn't make the cut. Why? Well, Windows and most hardware are finely tuned to work with those standard sizes. They optimize memory management for efficiency and speed. If you're looking to handle larger memory blocks for applications like SQL Server, you're better off configuring those 2 MB or 1 GB pages. This allows for better performance and resource management. So, while 32 KB might sound appealing, sticking to the established page sizes will keep your system running smoothly and efficiently. When it comes to virtual memory in Windows Server, 32 KB page sizes are a bit of a mystery. You see, Windows primarily operates with 4 KB, 2 MB, and 1 GB page sizes. The 32 KB option is simply not on the menu. Why? Because the system and hardware are finely tuned to handle those standard sizes. If you're managing memory for applications, especially resource-heavy ones like SQL Server, you'll want to leverage those larger pages, 2 MB or 1 GB. They allow for more efficient memory management, reducing overhead and improving performance. Configuring these options, like enabling large page support, can make a significant difference. So, while 32 KB might sound appealing, sticking with what Windows supports will keep your system running smoothly and efficiently. In general, 32 KB is not a standard or configurable page size for virtual memory in Windows Server. The two most common large page sizes supported by Windows are 4 KB default, 2 MB, and 1 GB. 32 KB page size is not natively supported as a system-wide memory page size in Windows. If you need to manage larger memory blocks for specific applications, you would typically use the 2 MB or 1 GB pages instead, depending on the application's needs and your hardware configuration. Windows does offer a 32 KB page size in its standard memory management model, because the standard system pages are either 4 KB for typical memory management, or larger page sizes, such as 2 MB and 1 GB. The operating system and most hardware are optimized for 4 KB and large page sizes, 2 MB and 1 GB. If you're looking to optimize memory management or are interested in using large pages for specific applications, like SQL Server for example, you can configure 2 MB or 1 GB pages through specific system settings like lock pages in memory or enabling large page support for SQL Server. SMB over QUIC is revolutionizing how we think about file sharing. Imagine combining the robust server message block protocol, which has been the backbone of network file sharing, with QUIC, Google's cutting-edge transport layer protocol. QUIC is all speed and reliability, designed for low latency communication. This means that when you access files or printers over the network, you can expect faster response times and a more stable connection, even in challenging network conditions. By leveraging QUIC's capabilities, SMB can enhance its performance, making file sharing not just efficient but also resilient against interruptions. This fusion opens up exciting possibilities for businesses alike, ensuring that accessing resources is seamless and swift, no matter where you are. The future of network communication, and it's faster than ever. SMB over QUIC is an emerging concept that combines the server message block (SMB) protocol with QUIC UDP Internet Connections, a transport layer protocol developed by Google. QUIC is designed to provide faster and more reliable communication over the internet, particularly for applications that require low latency and robust connection management. Here's an overview of both components and how they might work together. SMB is a network file sharing protocol used for providing shared access to files, printers, and other network resources. Environments, but also supported on other operating systems like Linux and macOS. SMB operates over TCP/IP and uses port 445 by default. QUIC is revolutionizing how we experience the web. Imagine a transport protocol that combines the best of both worlds, speed and security. With QUIC, connection establishment happens in a flash, thanks to its clever integration of handshake and encryption processes. No more waiting around. And here's the game changer: multiplexing without head-of-line blocking. This means you can stream videos, download files, and browse simultaneously without one task slowing down the others. If one stream hits a snag, the rest keep flowing smoothly. Yes, QX Connection Manager is a lifesaver. Switching from Wi-Fi to cellular? No problem. Your connection stays intact, seamless functioning without a hitch. And let's not forget built-in encryption. QUIC encrypts all data by default, enhancing security without any effort. It's like having a secure vault for your information while you surf the web. QUIC is not just a protocol. It's a leap into a faster, safer internet experience. Imagine a world where file sharing is seamless, even across the most complex networks. That's where SMB over QUIC comes in. By integrating SMB with QUIC, we unlock faster and more resilient communication without sacrificing the robust file sharing capabilities we rely on. Think about remote access. Traditionally, SMB needs those pesky open ports like 445, which can be a security nightmare. QUIC changes the game, effortlessly navigating firewalls and NATs, making remote access smoother and safer. And let's not forget performance. QUIC's low latency and smart congestion control mean quicker file transfers and reduced connection setup times. Plus, with built-in encryption, your data is secure by default, eliminating the hassle of extra protocols. This combination not only enhances efficiency, but also fortifies security, making SMB over QUIC a game changer for modern file sharing. The integration of SMB with QUIC would theoretically provide the benefits of QUIC, while still maintaining the file sharing capabilities of SMB. This combination could be especially useful in scenarios such as remote access, where SMB traditionally requires opening ports like 445 on a firewall, which can be problematic due to security risks and NAT traversal. QUIC, being more firewall and NAT friendly, could enable SMB to work more easily across networks and the internet. Performance enhancements from QUIC's low latency and congestion control mechanisms could provide faster file transfers and reduce connection setup times when accessing files over the internet. With QUIC's built-in encryption, data in transit would be more secure by default, reducing the need for additional protocols or configurations for encrypted communication. Imagine a world where file sharing is not just fast, but lightning quick. That's what SMB over QUIC brings to the table. With QUIC's ability to establish connections faster and manage network congestion like a pro, latency becomes a thing of the past. You'll experience seamless file transfers, even in most challenging network conditions. Now let's talk about firewalls and NAT traversal. QUIC runs over UDP, making it a breeze to navigate through those pesky barriers that often slow down TCP-based protocols. This means SMB can operate more reliably, whether you're on a mobile network or a complex internet setup. And security? QUIC has that covered too. It encrypts all traffic by default, so your SMB communications are secure without the hassle of extra configurations. It's like having a built-in security system that just works. With SMB over QUIC, you get performance, reliability, and security, all in one powerful package. Benefits of SMB over QUIC: improved performance. QUIC's faster connection establishment and better handling of network congestion would reduce latency and improve the overall performance of file sharing over SMB. Firewall and NAT traversal. QUIC operates over UDP, which can more easily traverse firewalls and NAT devices compared to TCP-based protocols. This would make SMB work more reliably across the internet and mobile networks. Security. QUIC encrypts all traffic, which would mean that SMB communication could benefit from this improved security without requiring additional configuration, like SMB 3.0's encryption. In today's remote work landscape, seamless connectivity is crucial. Imagine accessing your file server securely and efficiently no matter where you are. That's where SMB over QUIC comes in. It revolutionizes remote office connectivity by ensuring fast, reliable access to files over the internet. Think about cloud storage and file sharing. With SMB over QUIC, transferring files between your local machine and cloud servers becomes a breeze, significantly boosting performance. Plus, it enhances cross-platform communication, making it easier to share files across different operating systems. This technology not only streamlines workflows, but also keeps your data secure, allowing teams to collaborate effortlessly, whether they're in the office or working from home. Embracing SMB over QUIC means embracing a future where remote work is not just possible, but efficient and secure. Potential use cases: remote office connectivity. In remote or hybrid work environments, where users need to access file servers over the internet securely and efficiently. Cloud storage and file sharing. SMB over QUIC could improve the performance of file sharing between cloud providers or between a user's local machine and a cloud-based file server. Cross-platform communication. SMB over QUIC could facilitate easier cross-platform communication for file sharing, particularly in environments. Imagine a world where accessing files remotely is as seamless as streaming your favorite show. That's the promise of SMB over QUIC. While it's not yet mainstream, the potential is enormous. QUIC, with its low latency and built-in security features, can transform how we handle file sharing in our increasingly connected environments. Think about it: faster transfers, reduced lag, and enhanced security protocols that keep our data safe from prying eyes. As more organizations recognize these benefits, we're bound to see a surge in experimentation and adoption. The future of file access is evolving, and SMB over QUIC might just be the game changer we've been waiting for. Role-based access control, or RBAC, is a game changer for managing user permissions in Windows Server. Instead of assigning permissions to each individual user, we group users into roles. Think of it as creating teams where each team has specific access rights based on their tasks. For instance, an administrator role might have full control, while a regular user role has limited access. Permissions define what actions can be taken on resources, like reading or modifying files. Groups simplify management by bundling users with similar access needs, such as administrators or guests. At the heart of this system is the Access Control List, or ACL, which details what each user or group can do with a resource. Active Directory plays a crucial role in the setup, storing all the information about users, computers, and groups, making it easier to enforce RBAC across the network. This approach not only streamlines administration, but also enhances security, ensuring that users only access what they need to do their jobs effectively. Role-based access control, RBAC, in Windows Server is a system for managing user permissions and access to resources based on roles rather than individual user accounts. By grouping users into roles, you can assign permissions to these roles, which simplifies administration and enhances security. In Windows Server, this is implemented in several ways depending on the service or feature you're working with. A role is a collection of permissions associated with a specific set of tasks or access requirements. For example, roles could be related to a user being an administrator, a regular user, or a server-specific role such as a DNS or file server. Permission is the ability to perform a specific action on a resource, such as read, write, modify, or delete permissions for files, folders, or other resources. A group is a collection of users that share the same access rights. For example, administrators, users, and guests are typically created as groups. A user is an individual account representing people or systems that need access to resources. An access control list, ACL, is a list of permissions associated with an object, like a file, folder, or system resource, specifying what actions users and groups can perform on it. Active Directory, AD, is a directory service that stores and manages information about resources in the network, including users, computers, and groups. It is often used in enterprise environments to enforce RBAC. Role-based access control, RBAC, in Windows Server is a system for managing user permissions and access to resources based on roles rather than individual user accounts. By grouping users into roles, you can assign permissions to these roles, which simplifies administration and enhances security. Implementing role-based access control, or RBAC, in Windows Server is a game changer for managing user permissions. First, we leverage security groups to streamline access. By creating these groups in Active Directory users and computers, we can define who gets access to what. Just right-click on your domain or organizational unit, select New, and create a group. Next, it's all about assigning users to these groups based on their roles. Simply right-click a user, select Add to Group, and choose the right security group. This keeps things organized and efficient. Finally, we assign permissions to these groups, ensuring they have the necessary access to resources like files, folders, or applications. By adding the group to the object's access control list, we control who can do what. This method not only enhances security, but also simplifies management, making it easier to keep track of user access across the board. Implementing role-based access control, or RBAC, in Windows Server is a game changer for managing user permissions. In Active Directory, role-based access control is a game changer for managing user permissions. Imagine having the power to define specific roles right within the Active Directory Administrative Center. You can tailor permissions based on these roles, ensuring users only access what they truly need. Now let's talk about delegation of control. This feature allows you to grant permissions on specific AD objects without handing over the keys to the kingdom. Using the delegation of control wizard, you can assign administrative tasks like password resets or managing group memberships, all based on defined roles. And then there's group policy, or GPO, which acts as a powerful tool for enforcing access control across your organization. With GPOs, you can set security settings, software restrictions, and user permissions, ensuring compliance and security are always top-notch. In essence, these tools in Active Directory not only streamline administration, but also enhance security, making your IT environment more robust and efficient. Group policy objects, GPOs, can be used to enforce role-based access control across multiple machines in an organization. You can use GPOs to enforce policies like login restrictions, software installation rights, and access to network resources based on the user's role. By applying different GPOs to organizational units, you can manage different security configurations for different groups of users. Example, a GPO could be used to enforce password policies for administrators, but allow more lenient policies for users in a non-sensitive role. Group policy objects, GPOs, can be used to enforce role-based access control across multiple machines in an organization. You can use GPOs to enforce policies like login restrictions, software installation rights, and access to network resources based on the user's role. Implementing role-based access control, or RBAC, in Windows Server is crucial for maintaining security. The principle of least privilege is key. Always grant the minimum access necessary for users to perform their roles. This means avoiding high-privilege groups like administrators unless absolutely essential. In larger environments, leverage group policies to enforce consistent security settings tailored to specific roles. Regularly auditing access and permissions is vital. Utilize event logs or advanced auditing tools to ensure users only have the access they truly need. Delegating administration in Active Directory allows you to assign specific roles without relinquishing full control over the domain. And if you're integrating with cloud services like Azure Active Directory, take advantage of conditional access to enforce security policies based on user roles or locations. This approach not only enhances security, but also streamlines management across your network. Best practices for RBAC in Windows Server. Principle of least privilege. Always grant the least amount of access necessary to perform a role's function. Avoid assigning users to high-privileged groups, e.g. administrators, unless absolutely necessary. Use group policies. For large environments, group policy is a powerful tool for enforcing consistent security settings based on roles. Audit access and permissions. Regularly audit user and group permissions to ensure that users have only the necessary access. This can be done through event logs, the Advanced Security Audit Policy, or third-party auditing tools. Delegate administration. Use delegation in Active Directory to assign roles and responsibilities to specific administrators without giving them full control over the entire domain. Use conditional access. If you are integrating with cloud services, like Azure Active Directory, you can use features like conditional access to enforce additional security policies based on the user's role or location. Threat detection on a Windows server is essential for safeguarding your IT infrastructure. It's all about spotting and responding to malicious activities that could jeopardize your server's functionality or data. One of the most effective tools at your disposal is Windows Defender Antivirus. This built-in feature offers robust protection against malware and ransomware. With real-time protection, it detects threats as they happen, ensuring immediate action. The cloud-based protection feature taps into Microsoft's vast resources to identify emerging threats before they become a problem. Plus, it can automatically remediate issues, saving you time and effort. You can easily configure and monitor Windows Defender through the Windows Security app or PowerShell, giving you control over your server's security. By leveraging these tools, you can maintain a secure environment and keep your data safe from potential threats. Threat detection on a Windows server is a critical part of maintaining the security and integrity of your IT infrastructure. It involves identifying and responding to malicious activities or vulnerabilities that could compromise the server's functionality or data. Here are several methods and tools you can use to detect threats on Windows Server. Windows Defender Antivirus. Windows Server comes with Windows Defender Antivirus, which is a built-in security feature that provides basic protection against malware, ransomware, and other threats. Real-time protection detects threats as they occur. Cloud-based protection leverages Microsoft's cloud to identify emerging threats. Automated remediation can automatically respond to detected threats. You can configure and monitor Windows Defender using the Windows Security app, PowerShell. Event logs in Windows Server are crucial for keeping our system secure and running smoothly. Security logs are like the watchful eyes of our server, tracking login attempts, account lockouts, and end privilege escalations. They help us catch suspicious activities before they escalate. Then we have system logs, which provide a window into operational anomalies and system-level issues, helping us troubleshoot effectively. Application logs are equally important. They capture data from various software and services, allowing us to detect any abnormal behavior that could indicate a problem. For a deep dive, we can use Event Viewer to inspect these logs manually. But for those who prefer automation, tools like Windows Event Forwarding and Windows Event Collector streamline the process, ensuring we never miss a critical event. Monitoring these logs is not just a task, it's a vital part of maintaining a secure and efficient environment. Windows Server generates event logs that record system activities and security events. You can use these logs to monitor suspicious activity. Security logs track login attempts, account lockouts, and privilege escalations. System logs provide insights in system-level issues and operational anomalies. Application logs include logs from software and services, which may help in detecting abnormal behavior. You can use Event Viewer to manually inspect logs, or automate the process by using tools like Windows Event Forwarding and Windows Event Collector. Event logs in Windows Server are crucial for keeping our system secure and running smoothly. Security logs are like the watchful eyes of our server, tracking login attempts, account lockouts, and any privilege escalations. When it comes to advanced threat detection, SIEM tools are game changers. Take Splunk, for instance. It's like having a supercharged detective that sifts through massive amounts of data, pinpointing anomalies in real time. Then there's Microsoft Sentinel on Azure, which leverages the power of the cloud to provide seamless integration and scalability. It's perfect for organizations looking to enhance their security posture without the heavy lifting. And let's not forget SolarWinds Security Event Manager. This tool simplifies log management, making it easier to spot suspicious activity across your network. By aggregating and analyzing logs from various sources, these SIEM solutions empower you to stay one step ahead of potential threats. In a world where cyber threats are constantly evolving, having the right SIEM tool is not just an option, it's a necessity. For more advanced threat detection, you can use SIEM solutions like Splunk, Microsoft Sentinel, Azure, and SolarWinds Security Event Manager. These tools aggregate, analyze, and correlate logs from various sources, including Windows servers, to identify suspicious activity or potential threats. Advanced threat detection with Microsoft Defender for Identity is a game changer in safeguarding user identities and accounts. Imagine a tool that not only detects brute force login attempts, but also identifies lateral movement across your network, alerting you to potential threats before they escalate. It's like having a digital watchdog that never sleeps. Now, let's talk about network intrusion detection systems, or NIDS. They're essential for monitoring traffic to and from your Windows server, spotting malicious patterns in real time. Tools like Smart and Suricata are open source heroes in this space, while Microsoft Defender for Endpoint adds another layer of network-level detection and response. And don't overlook file integrity monitoring. Implementing FIM is crucial for tracking changes to critical system files and configurations. With tools like Tripwire or OSEC, you can receive immediate alerts for any suspicious modifications, ensuring your system remains secure. In today's threat landscape, staying proactive is key to protecting your digital assets. Advanced Threat Protection, ATP, Microsoft Defender for Identity, formerly Azure Advanced Threat Protection, is a cloud-based tool for detecting suspicious activity related to user identities, accounts, and machines within a network. Detects brute force login attempts. Identifies lateral movement when attackers move across the network. Detects privilege escalation and suspicious behavior.
Network Intrusion Detection Systems, NIDS. Network intrusion detection systems can monitor the traffic to and from your Windows server for malicious patterns. Snort, an open source network intrusion detection system. Suricata, another open source NIDS solution. Microsoft Defender for Endpoint provides network level detection and response. File integrity monitoring implement file integrity monitoring, FIM, to detect changes to critical system files, configuration files, and executables. Tools such as Tripwire or OSSEC can help monitor your file system for changes, and they provide alerts if suspicious modifications are detected. In today's threat landscape, staying proactive is key to protecting your digital assets.
Endpoint detection and response, or EDR, is essential for safeguarding our Windows servers and endpoints. Solutions like CrowdStrike and Carbon Black are at the forefront, constantly monitoring for suspicious activities. They utilize both signature-based and heuristic detection methods to catch abnormal behaviors. Think process injection, lateral movement, and data exfiltration. To effectively combat threats, we need a multi-layered approach. Start with built-in tools like Windows Defender and Event Viewer to lay a solid foundation. Then, layer in third-party software for advanced detection and protection. Regularly monitoring logs and system behaviors is crucial. It's like having a security camera for your digital environment. And don't forget automation. Implementing scripts and SIEM solutions can provide real-time alerting and response, ensuring that when a threat emerges, you're not just reacting, you're ready to act. This comprehensive strategy is key to staying ahead in the ever-evolving landscape of cybersecurity. EDR solutions such as CrowdStrike or Carbon Black monitor and respond to suspicious activities on Windows servers and endpoints. EDR tools use both signature-based and heuristic-based detection methods to identify abnormal behaviors, including process injection, lateral movement, and data exfiltration. For effective threat detection on Windows Server, you should employ a multi-layered approach that combines built-in tools like Windows Defender and Event Viewer, third-party software for more advanced detection and protection, regular monitoring of logs and system behaviors, and automated scripts and SIEM solutions for real-time alerting and response. Windows Update. Hot patching is a game changer for maintaining system uptime. Imagine being able to apply crucial security updates or bug fixes without the hassle of a reboot. That's hot patching in action. It allows updates, especially those addressing critical vulnerabilities, to be applied directly at the kernel level or to running components. This is vital in enterprise environments where every second counts. Windows updates fall into three main categories. Security updates, which tackle vulnerabilities that need immediate attention. Quality updates, focusing on system improvements and bug fixes. And feature updates, which roll out new features and major changes. By leveraging hot patching, administrators can ensure their systems remain secure and operational, minimizing disruptions and maximizing productivity. It's all about keeping everything running smoothly while staying ahead of potential threats. Windows Update. Hot patching refers to the ability to apply updates or patches to a running system without requiring a reboot or interrupting the ongoing operation of the system. This process allows administrators to install important security updates or bug fixes without disrupting service, which is especially useful in enterprise environments or situations where uptime is critical. Hot patching in the context of Windows updates can be broken down into two main concepts. Hot patching in Windows allows certain updates, primarily those related to security, to be applied to the system without needing to restart. This helps to minimize downtime for the user or applications. A hot patch is typically applied at the kernel level or to running system components. It's used in particular to address critical vulnerabilities and prevent exploitation, especially in enterprise scenarios where rebooting servers or critical systems can be disruptive. Windows update mechanisms categorize updates into security updates, which fix vulnerabilities and often require immediate application, quality updates, which address general system improvements and bug fixes, and feature updates, which introduce new features and major system changes. Hot patching is a game changer in the world of software updates, especially when it comes to security. Imagine being able to apply critical updates without rebooting your system. This is essential when vulnerabilities could be exploited in the wild. Windows has a robust patch management system, utilizing tools like WSUSE and Microsoft Endpoint Configuration Manager to deliver these hot patches efficiently. For Windows Server, live kernel patching is a lifesaver, allowing updates to be applied to the kernel while the system is running, particularly in data centers or Hyper-V environments. And let's not forget about dynamic link libraries. When a vulnerability is found in a DLL, patches can be applied directly in memory, keeping everything running smoothly. However, Windows Patch Guard complicates things for kernel updates, making it tough to modify certain system parts without a reboot. Yet modern Windows Server versions are embracing hot patching to tackle these challenges dynamically. While Windows 10 and 11 typically require a reboot for major updates, they're starting to incorporate dynamic patching for critical security fixes. This means faster, more efficient updates, keeping systems secure without the downtime. Hot patching usually applies to security updates and sometimes to quality updates, specifically when critical issues arise that could be exploited in the wild. These patches are designed to be applied dynamically without a system restart. Some updates, however, may still require a restart to take full effect, especially those that affect low-level system components or require resources to be reloaded. Key technologies supporting hot patching. Windows uses a robust patch management system that is responsible for delivering updates to the system. Tools like Windows Server, Update Services, WSUSE, Microsoft Endpoint Configuration Manager, and Windows Update for Business play a central role in the process. These tools can manage hot patches for security vulnerabilities. Windows Server Edition, particularly in environments running Hyper-V or data centers, have support for live kernel patching. This allows critical updates to be applied to the kernel while the system is running, which eliminates the need for reboots. The feature is part of Windows Server 2016 and later. Hot patch can be applied to specific DLLs in memory. When vulnerabilities are found in these DLLs, patches can be applied to memory space without requiring a full system reboot. Some updates target the Windows kernel, and Windows Patch Guard, kernel patch protection, makes it difficult to modify certain parts of the system without a reboot. However, modern versions of Windows Server are moving towards hot patching technology to handle these kernel-level updates dynamically. While Windows 10 and 11 generally require a reboot for major updates, especially those affecting the kernel or system files, Windows Update has started to incorporate mechanisms that allow for some patching to occur dynamically. This is especially true for security patches that need to be applied without delay. Hot patching is a game changer for anyone managing critical systems. Imagine a server that never has to go down. No costly interruptions, just seamless operation. That's the power of hot patching. It allows us to deploy security fixes instantly, closing vulnerabilities before they can be exploited. This means we can respond to threats in real time, keeping our data safe and our services running smoothly. Plus, the efficiency is remarkable. Patching without rebooting means users experience minimal disruption. It's all about maintaining high availability and ensuring that everything runs like clockwork, even in the face of potential threats. Hot patching isn't just a technical advantage, it's a strategic necessity in today's fast-paced digital landscape. Reduced downtime is essential for systems that require high availability, such as servers or critical infrastructure, where downtime can be costly. Hot patching allows security fixes to be deployed immediately, reducing the window of vulnerability. The ability to patch systems without rebooting means fewer disruptions to end users or processes. Hot patching is a game changer for anyone managing critical systems. Imagine a server that never has to go down. No costly interruptions, just seamless operation. That's the power of hot patching. Hot patching is a fascinating yet complex process. While it allows us to apply updates without rebooting, it's not a one-size-fits-all solution. Certain patches, especially those impacting low-level system components, can be tricky. Compatibility issues often arise. Some updates simply can't be hot patched due to dependencies that demand a full system restart. And let's face it, hot patches can be temporary fixes. They might solve an immediate problem, but the real solution often requires a reboot down the line. In enterprise environments, where uptime is critical, hot patching becomes essential. Organizations leverage tools like Windows Server update services or third-party management systems to deploy these updates seamlessly. The ability to implement security fixes without disrupting vital applications is invaluable for businesses that operate around the clock. It's a balancing act between maintaining functionality and ensuring security, and that's what makes hot patching so intriguing. Hot patching can be technically complex and may not be suitable for every type of patch, especially those affecting low-level system components. Not all updates can be hot patched due to dependencies or system-level changes that require a reboot. Hot patches may be temporary solutions, with full fixes requiring a reboot or system restart in the future. In enterprise environments, hot patching plays a critical role in maintaining uptime. Organizations often rely on specialized systems such as Windows Server update services or third-party patch management tools to manage and deploy updates. The ability to apply security fixes without interrupting critical applications or services is an important feature for businesses relying on 24/7 operations. Hot patching technologies in Windows are game changers for system reliability. Take Windows Server Live Patching, for instance. Introduced in Windows Server 2016 and 2019, it allows kernel mode patches to be applied without a reboot. Imagine that, fixing critical issues on the fly. Then there's Windows Update for Business, which lets you schedule updates outside of peak hours, ensuring minimal disruption while keeping your system secure. And let's not forget about memory patching. For specific vulnerabilities, Windows can load fixes directly into memory, eliminating the need for a full system restart. These innovations not only enhance security, but also keep your operations running smoothly. It's all about maintaining uptime while staying protected. Hot patching in Windows Update is a game changer, especially when uptime and security are non-negotiable. Imagine applying critical security patches without the dreaded reboot. Sounds like a dream, right? While hot patching isn't a one-size-fits-all solution, it's a powerful tool in our arsenal. It allows us to keep systems running smoothly while addressing vulnerabilities in real time. This means less downtime and more productivity. Environments where every second counts, hot patching can be the difference between a secure system and a potential breach. Embracing this feature not only enhances security, but also optimizes our workflow, ensuring that we stay ahead in an ever-evolving digital landscape. Hot patching in Windows Update is a game changer, especially when uptime and security are non-negotiable. Imagine applying critical security patches without the dreaded reboot. Sounds like a dream, right? Windows Server Update Services, or WSUS, is a game changer for IT administrators. Imagine having a tool that lets you manage updates of entire network from a single location. With WSUS, you can control when and how updates are applied to client machine servers, ensuring that everything runs smoothly. The approval process is a standout feature. You can decide which updates to push out, giving you the power to maintain stability while keeping systems secure. Plus, with granular control, you can categorize updates into critical, security, or service packs, and target specific groups of computers, making management a breeze. Reporting is another key aspect. Detailed insights into which systems are missing updates help you stay on top of your environment. And let's not forget about automatic deployment. Set your policies, and WSUS takes care of the rest. By deploying updates locally, you save bandwidth, which is crucial for any organization. Finally, synchronization with Microsoft ensures you always have the latest updates at your fingertips. WSUS truly streamlines the update process, making life easier for IT teams everywhere. Windows Server Update Services, or WSUS, is a game changer for IT administrators. Imagine having a powerful tool that lets you manage updates to your entire network from a single location. Windows Server Update Services, WSUS, is a Microsoft tool that enables IT administrators to manage the distribution of updates released through Microsoft Update to computers in a corporate environment. It provides a central location to manage the approval, deployment, and monitoring of updates on operating systems. WSUS allows administrators to control when updates are applied to client machines and servers within a network.
Administrators can approve or decline updates before they're pushed to client machines, providing more control over what gets installed. It allows administrators to categorize updates, such as critical updates, security updates, service packs, with specific groups of computers. WSUS provides reports about the status of updates on systems, including which systems are missing updates.
It can automatically deploy updates to client systems based on defined policies. By deploying updates locally from the WSUS server, organizations can conserve bandwidth that would otherwise be used to download updates from the internet. WSUS can synchronize updates with Microsoft Update to get the latest updates for Windows and other Microsoft products. Once my WSUS server was set up and the clients were configured, that began. I watched as the server with Microsoft Update, pulling in all those crucial updates. It's like having a personal assistant who knows exactly what my systems need. After synchronization, I dove into the WSUS admin console, manually approve or decline updates with just a few clicks. But why stop there? I set up automatic approval rules to streamline the process for specific updates, saving me time and effort. Monitoring and reporting became my best friends. The WSUS console provides a clear view of the updates across all client machines. I can easily track which devices have installed updates and identify those that are lagging behind on critical updates. It's empowering to have that level of control and insight, ensuring my network stays secure and up to date. Managing WSUS isn't just about updates. It's about maintaining a healthy environment. Once my WSUS server was set up and the clients were configured, the magic began. I watched as the server synchronized with Microsoft Update, pulling in all those crucial updates. Once my WSUS server is up and running, the real magic begins. It starts synchronizing with Microsoft Update, pulling in all those crucial updates. After that, I dive into the WSUS admin console, where I have the power to manually approve or decline updates. It's like being the gatekeeper of my network security. To make life easier, I can set up automatic approval rules for specific updates, ensuring that critical patches are deployed without delay. But it doesn't stop there. The WSUS console is a treasure trove of reporting features. I can track which machines have installed updates and identify those that are lagging behind. It's all about keeping my systems secure and up to date. With WSUS, I have the control I need to manage updates efficiently. Once the WSUS server is set up and the clients are configured, the WSUS server will begin to synchronize with Microsoft Update to download the available updates. After synchronization, you can manually approve or decline updates in the WSUS admin console. You can also configure automatic approval rules to streamline the approval process for specific types of updates. The WSUS console offers reporting features that help you track the update status of your client machines. You can see which machines have installed updates and which are missing critical updates. Managing WSUS updates can feel like a juggling act, but it doesn't have to be overwhelming. If there are updates you want to keep at bay, like unwanted software or unnecessary patches, you can easily decline them right from the WSUS admin console. This keeps your systems clean and efficient. Now, let's talk about cleanup. Over time, WSUS can become cluttered with outdated files. That's where the WSUS Cleanup Wizard comes in. It's your best friend for removing unneeded updates, obsolete files, and even computers that aren't reporting anymore. And don't forget about client-side targeting. This feature lets you assign client computers to specific update groups, ensuring that updates roll out according to your organization's unique needs. It's all about tailoring the experience to fit your environment. With these tools, managing WSUS becomes a breeze, keeping your systems running smoothly and securely. Managing WSUS updates can feel like a balancing act. If you want to keep unwanted software or unnecessary patches at bay, the WSUS admin console is your best friend. Just decline those updates you don't want, and you'll streamline your deployment process. But it doesn't stop there. Over time, WSUS can become cluttered with outdated files. That's where the WSUS Cleanup Wizard comes in. It's like spring cleaning for your update server, removing unneeded updates and obsolete entries so everything runs smoothly. And let's not forget about client-side targeting. This feature lets you assign specific update groups to your client computers. This way, you can ensure that each department gets exactly what it needs without any unnecessary fuss. It's all about tailoring the update experience to fit your organization's unique needs. Keep it clean, keep it efficient, keep it. Client not reporting to WSUS can be a real headache. First, check those group policy settings. Make sure they're applied correctly. If clients can't reach the WSUS server, they're not going to report in. Now, if WSUS itself isn't synchronizing, that's another layer. Ensure your server has internet connectivity and can reach the Microsoft Update servers. Don't forget to investigate any firewall or proxy issues blocking the connection. And let's talk about database issues. If your WSUS database is bloated or corrupted, it's time for some maintenance. Regular cleanups are essential to keep everything running smoothly. Address these points, and you'll have a well-oiled WSUS machine in no time. Setting up WSUS in a hierarchical structure can significantly enhance your update management. Securing an upstream WSUS server to sync directly with Microsoft Update, you create a centralized point for updates. This upstream server can then distribute to multiple downstream servers, streamlining and reducing bandwidth usage across your network. For larger environments, consider using an external SQL server instead of the default internal database. This shift not only boosts performance, but also offers better scalability as your organization grows. An external SQL server can handle more simultaneous connections and larger databases, ensuring that your WSUS infrastructure remains robust and responsive. By optimizing your WSUS setup in these ways, you can maintain a seamless update experience across your entire organization. Setting up WS in a hierarchical structure can significantly enhance your update management. By configuring an upstream WSUS server to sync directly with Microsoft Update, you create a centralized point for updates. Windows Server Backup is an essential tool for anyone managing a Windows server. Imagine having the power to create a complete backup of your entire server, operating system, applications, settings, and all your data. That's right. With a full server backup, you're not just safeguarding your files, you're ensuring seamless recovery from any disaster. And here's the kicker. If your hardware fails, you can perform a bare metal restore. This means you can take that backup and restore everything to a brand new machine, just like it was before. No more sleepless nights worrying about data loss or system failures. Windows Server Backup gives you peace of mind, knowing that your entire server can be brought back to its exact previous state in no time. Windows Server Backup is a feature in Windows Server Editions that provides tools for creating backups of your data, system state, and full server images. This feature is designed to help organizations recover from data loss, system failures, and other issues by providing various backup options. Here are some key features of Windows Server Backup. Full server backup, complete backup of the entire server. Windows Server Backup can create a full server backup, including the operating system, installed applications, system settings, and all data. This enables a complete recovery in case of a system failure. Bare metal recovery. With a full server backup, you can restore the entire system even if the hardware is replaced. This is known as a bare metal restore, which allows you to bring the server back to its exact previous state. Windows Server Backup is an essential tool for anyone managing a Windows server. Custom backups are a game changer for managing data. Instead of backing up the entire server, you can select specific files or folders that matter most to you. This means more efficient use of storage and quicker recovery times when you need them. Plus, with custom scheduling, you can set your backups to run daily, weekly, or at intervals that fit your workflow perfectly. Now, let's talk about system state backups. These are crucial for protecting your critical system components. They include essential data like the Windows registry, boot files, and even Active Directory data if you're using a domain controller. In the event of a failure, a system state backup allows you to restore Active Directory, ensuring that your domain services come back online seamlessly. This level of control and precision in backups not only safeguards your data, but also gives you peace of mind. You can perform backup of selected files or folders instead of backing up the entire server. This allows for more granular backups for specific datasets. You can configure backups on a scheduled basis to run daily, weekly, or on custom intervals based on your needs. The system state backup includes important data required for system recovery, such as the Windows registry, boot files, and Active Directory data for domain controllers. On a domain controller, the system state backup ensures that Active Directory data can be restored in the event of a failure, allowing for a complete recovery of domain services. When it comes to backups, understanding the difference between incremental and differential backups is crucial. Incremental backups only capture the data that has changed since the last backup, which means you save both time and storage space. It's like taking a snapshot of your progress without redoing the whole picture. On the other hand, differential backups save all changes made since the last full backup, making it easier to store your system without sifting through countless files. Now let's talk about the Volume Shadow Copy Service, or VSS. This powerful tool allows Windows Server Backup to create backups even while your applications are running. Imagine being able to back up your data without interrupting your workflow. VSS creates point-in-time snapshots of your volumes, ensuring that you have a consistent backup ready when you need it. This means you can keep your services running smoothly while safeguarding your data. Efficient, effective, and essential. This is how modern backups should work. Incremental backups. Windows Server Backup supports incremental backups with only backup data that has changed since the last backup. This helps to save storage space and reduces the time required to perform backups. Differential backups. It also supports differential backups, where changes since last full backup are backed up. This can help reduce the amount of data to be backed up compared to full backups. Volume Shadow Copy Service. VSS. Integration. Backup while data is in use. Windows Server Backup uses Volume Shadow Copy Service, VSS, to create consistent backups of live, running systems. This ensures that application services can continue to run while a backup is being taken. Point-in-time snapshots. VSS can be used to create point-in-time snapshots of volumes, which can be used for backup purposes. When it comes to data backup, flexibility is key. You can easily back up your data to local hard drives or external drives, giving you quick access whenever you need it. But what if you want to ensure your critical data is safe off-site? That's where remote backup comes in. With Windows Server Backup, you can back up to a remote server or network location, perfect for disaster recovery. Need to share backups across machines? Just store them in a shared folder. It's simple and efficient. For larger organizations still using legacy systems, Windows Server Backup even supports tape drives, keeping that old infrastructure relevant. And let's not forget about backup compression and encryption. Compressing your backup files saves valuable storage space, while encryption ensures your data remains secure. With these features, you can rest easy knowing your backups are both accessible and protected. Restoring an entire server from a backup can be a lifesaver in disaster recovery scenarios. Imagine the peace of mind knowing that your entire system can be back up and running in no time, but it doesn't stop there. Windows Server Backup also lets you recover individual files or folders without the hassle of restoring the whole system. Managing backup retention is crucial. You can set policies to keep your storage in check, preventing old backups from piling up.
Plus, with backup catalogs, finding and restoring specific backups becomes a breeze. And let's not forget about scheduling. You can audit your backups to run at specific times, ensuring they happen consistently without any manual effort. Notifications keep you in the loop, alerting you via email or event logs about the success or failure of your backups. This way, you can rest easy knowing your data is safe and sound. You can restore the entire server from a backup, which can be critical for full disaster recovery scenarios.
Windows Server Backup also supports recovering individual files or folders from a backup without needing to restore the entire system. Windows Server Backup allows users to manage backup retention policies to prevent old backups from consuming unnecessary storage. You can set retention periods for backups. It keeps a catalog of backups, making it easier to manage and restore specific backups. You can schedule regular backups to run at specific times, ensuring that backups happen consistently without manual intervention. Administrators can receive email or event log notifications about the success or failure of backups, helping to ensure that backup jobs are completed properly. Managing backups through the command line with wbadmin is a game changer. It offers advanced options for backup and recovery, plus the power of automation and scripting. Imagine handling backups across multiple servers remotely, no more running around. For those using Hyper-V, you can back virtual machines even while they're running, ensuring minimal downtime. And if you ever need to restore to different hardware, Windows Server Backup has you covered with its hardware-independent restore feature. Integration with the Windows recovery environment means you can easily restore your system using bootable recovery tools. Need to create bootable media? Just grab a USB drive or DVD, and you're set for any emergency. While Windows Server Backup can back up volumes with SQL databases. For detailed SQL backups, it's best to leverage SQL Server's own features. With these tools at your disposal, you can ensure your data is safe and recoverable, no matter the situation. Backup via command line, wbadmin. Command line interface. Windows Server Backup can be managed through the wbadmin command line tool, allowing for more advanced backup and recovery options, automation, and scripting. Remote backup management. You can manage backups remotely using wbadmin, making it easier to handle backups across multiple servers. Backup for Hyper-V virtual machines, VM. Backup environments using Hyper-V. Windows Server Backup can back up virtual machines, VMs. These backups can be performed while VMs are running, ensuring minimal downtime for virtualized environments. Restore to different hardware independent restore. Windows Server Backup supports restoring backups to different hardware configurations. This feature is useful in situations where the original hardware is unavailable. Integrated with Windows Server recovery options. Windows Recovery Environment, WinRE. Windows Server Backup integrates with Windows Recovery Environment, allowing for easy restoration through the system's bootable recovery tools. Bootable media. You can create bootable media, USB drives or DVDs, to help restore a server when the operating system is not bootable. Backup for SQL Server through additional tools. Although Windows Server Backup itself does not provide detailed backup options for SQL Server, it can back up volumes that contain SQL databases. For more advanced SQL-specific backups, it is recommended to use SQL Server's own backup features. trigger actions based on certain events, such as the event viewer in Windows Server is like a detective's notebook, meticulously logging every system event, error, and warning. Imagine diving into a treasure trove of information where you can track down issues before they escalate. You can filter logs by type, date, or even specific event IDs, making it easier to pinpoint the root cause of a problem. Ever faced a sudden server crash? The event viewer holds the clues. By checking system and application logs, you can uncover what went wrong, whether it was a failed update or a hardware failure. And let's not forget about the security logs, which are crucial for monitoring unauthorized access attempts. Navigating through the event viewer might seem daunting at first, but with practice, it becomes an invaluable tool in your IT toolkit. So the next time you encounter a glitch, remember, the answers are just a few clicks away in the event viewer. The event viewer in Windows Server is like a detective's notebook, meticulously logging every system event, error, and warning. Imagine diving into a treasure trove of information where you can track down issues before they escalate. The event viewer is a powerful tool that organizes system logs into distinct categories. First, we have Windows logs, where you can dive into application logs for software-related events, security logs that track login attempts and user rights, and system logs that reveal hardware and driver issues. Don't overlook the setup logs, which document the installation of your OS and applications. Then, there are forwarded events, which gather logs from other computers, creating a centralized view. Moving on to applications and services logs, this section is tailored for specific applications and services like Microsoft IIS or SQL Server, giving you detailed insights. Finally, custom views allow you to create personalized filters, showcasing logs based on your criteria, whether it's date, event type, or source. With this structure, navigating through events becomes a breeze, empowering you to troubleshoot and maintain your system effectively. The event viewer is divided into the following categories: Windows logs, application, logs related to software applications, security-related events such as login attempts, audit policies, and user rights. System, logs generated by the operating system itself, like hardware and driver issues. Setup, logs related to the setup of the operating system and applications. Forwarded events, logs are forwarded from other computers or servers. Applications and services logs. This section contains logs for individual applications, services, and drivers. For example, logs for Microsoft IIS, SQL Server, or other specific services may appear here. Custom views. Custom views are user-defined filters that can show a specific set of logs based on criteria like date, event type, or source. Event logs are the heartbeat of any system, providing crucial insights into its operation. First up, we have the information log type, which signals that everything is run smoothly or that a task has been successfully completed. Then, there's the warning log. This one's a heads up, indicating a potential issue that isn't critical yet, but should be ignored. Next, we encounter the error log, which points to significant problems that demand immediate attention. And let's not forget the critical log. This is the alarm bell, indicating a serious failure that can render a system inoperable. Finally, we have audit success and audit failure logs, which are essential for security. They track access attempts, logging both successful entries and failures, helping to safeguard our systems. Each log type plays a vital role in maintaining system health and security, ensuring we stay one step ahead of potential issues. When troubleshooting system issues, the event viewer is a go-to tool. I dive into the system and application logs to pinpoint performance hiccups or crashes. It's like having a backstage pass to my server's health. Monitoring security is crucial too. The security logs reveal login attempts and access control issues, which is vital for compliance with standards like HIPAA or PCI DSS. Application logs are gold mines for spotting software-specific errors or things, helping me keep everything running smoothly. And let's not forget about hardware problems. System logs can flag driver issues or hardware failures before they escalate. I even create custom views to keep an eye on critical logs tailored to my server's needs. With the right insights, I'd ensure everything operates seamlessly. Use the system and application log to diagnose performance issues or crashes. Use the security logs to monitor login attempts, access control, and audit failures. This is especially critical in environments that require compliance with security standards like HIPAA or PCI DSS. Check the application logs for any errors or warnings specific to software running on the server. The system log may contain errors related to hardware failures, driver issues, or system crashes. You can create custom views to monitor specific logs that may be critical to your server's operation, such as specific application or service logs. Filtering events in logs is like having a powerful magnifying glass at your fingertips. Each event comes with a unique event ID, allowing you to zero in on specific occurrences with precision. Want to sift through a sea of data? Just type in that event ID, and voila! But it doesn't stop there. You can also filter by severity, whether it's a simple information log, a warning that raises an eyebrow, or an error that demands immediate attention. This helps you prioritize what really matters. Time is crucial too. By setting a date and time range, you can pinpoint issues that cropped up during a specific period, making troubleshooting much more efficient. And let's not forget about event sources. If you know which application or service triggered an event, filtering by source can save you time and effort. It's all about getting to the heart of the matter quickly and effectively. Every event is associated with unique event ID number. You can filter logs by event ID to focus on specific types of events. You can filter based on event severity, information, warning, error, etc. Filter events by a particular time range to isolate issues that occur during a specific period. If you know which application or service generated an event, you can filter by the source. Managing event logs is crucial for maintaining system health. Over time, these logs can balloon in size, so it's wise to clear them periodically. Just right-click on a log and select Clear Log. It's that simple. But don't stop there. Configure log retention settings to automatically overwrite old logs once they hit a certain size, or archive them for long-term storage. For those managing multiple servers, event subscriptions are a game changer. They let you collect logs from various remote systems into one centralized hub, making monitoring a breeze. And if you want to hone in on specific data, create a custom event view. Filter by event types, sources, or keywords to keep your focus sharp. Plus, integrate with Task Scheduler to automate responses to critical events, like restarting a service or sending alerts. This proactive approach not only saves time, but also enhances your system's reliability. Event logs can grow large over time, so you might want to clear them periodically. This can be done by clicking a log and selecting Clear Log. You can configure log retention settings to overwrite old logs after a certain size limit is reached, or to archive logs to a separate location for long-term storage. Set up event subscriptions to collect event logs from multiple remote servers to a centralized system. You can create a custom view based on filters like event types, sources, or specific keywords for more targeted monitoring. You can create tasks that automatically trigger actions based on certain events, such as restarting a service or sending an alert. Windows DHCP Server is a game-changer in network management. Imagine a world where devices like computers, printers, and smartphones automatically receive IP addresses without any manual setup. That's the magic of Dynamic Host Configuration Protocol. With DHCP, your server dynamically allocates IP addresses from a defined range, ensuring every device gets what it needs to connect seamlessly. But it doesn't stop there. IP address reservation guarantees that specific devices always get the same IP based on their MAC address. While lease durations keep things organized, devices must renew their leases periodically. Plus, with scope options, you can automatically assign essential settings like DNS servers and default gateways to clients. For high availability, DHCP failover lets two servers work together, ensuring your network stays up and run. And if you need to exclude certain IP ranges to avoid conflicts, scope exclusions have you covered. Finally, the DHCP relay agent allows requests to be forwarded across subnets, making it a versatile solution for any network. With Windows DHCP Server, managing your network has never been easier or more efficient. Windows DHCP Server is a game changer in network management. Imagine a world where devices like computers, printers, and smartphones automatically receive IP addresses without any manual setup. That's the magic of Dynamic Host Configuration Protocol. DHCP, or Dynamic Host Configuration Protocol, is a network management protocol used to automatically assign IP addresses to devices on a network, such as computers, printers, and smartphones, without requiring manual configuration. In a Windows Server environment, the DHCP server role allows the server to manage IP address allocation dynamically, ensuring that devices on the network can easily obtain an IP address, subnet mask, default gateway, and other necessary configuration settings. Key features of Windows DHCP Server include dynamic IP address allocation, which automatically assigns IP addresses to devices on the network from a defined range, IP address reservation, which allows specific devices to always receive the same IP address based on their MAC address, lease duration, which assigns IP addresses with a lease time, after which the device must renew the lease or release the address. Scope options, which include settings like DNS servers, domain name, and default gateway that can be assigned to clients automatically. Failover and redundancy, which supports DHCP failover between two DHCP servers for high availability. Scope exclusions, which allow you to exclude certain IP ranges within a scope to avoid assigning IPs that are statically configured. And the DHCP relay agent, which supports forwarding DHCP requests from clients to a remote DHCP server in other subnets. As we wrap up this Windows Server Administration course, let's reflect on the essential skills you've acquired. You've delved into the world of Windows Server, mastering installations and configurations, whether through GUI or Server Core. Active Directory has become second nature with user and group management at your fingertips, and you've learned to enforce security with group policy. You've tackled DNS and DHCP, ensuring smooth network operations, and set up file and print services like a pro. Security management is now part of your toolkit, with firewall configurations and auditing practices to safeguard your environment. Remote access and networking skills will empower you to connect users securely, while storage and backup management ensure your data is safe. You've explored Windows Update services for effective patch management, and learned to monitor server performance with tools like Performance Monitor. PowerShell scripting has opened doors for automation, making your administrative tasks more efficient. Finally, you've grasped the importance of high availability and disaster recovery planning. As we conclude this Windows Server Administration course, let's summarize the key concepts and skills you've learned throughout the course to ensure you're well prepared for real-world administration tasks. You gained an understanding of what Windows Server is and how it differs from client editions. This includes different editions of Windows Server like Standard, Data Center, Essentials, and the respective features. We covered the basics of installing Windows Server, including both GUI and Server Core installation options. You learned how to set up the initial configuration, including network settings and Active Directory roles. You were introduced to the concepts of Active Directory, including domain controllers, users, groups, and organizational units, OUs. We explore how to manage users and groups using Active Directory users and computers, including best practices for creating, modifying, and deleting users, OSH groups. You learned how to configure and apply group policy objects, GPOs, to enforce security and system settings across an organization. You learned how to configure and manage DNS on a Windows server, including setting up zones, forwarding, and troubleshooting DNS issues. We covered how to install and configure DHCP servers to automatically assign IP addresses to clients within a network. You gained hands-on experience in setting up file shares, configuring permissions, and managing access to shared folders. You learned how to configure printers and print servers, including troubleshooting print jobs and managing print queues. We discussed Windows firewall settings and how to configure them for securing servers and allowing necessary traffic. You learned how to manage Windows Defender for real-time protection and set up antivirus policies. We covered auditing tools to monitor and log security events, including setting up audit policies and reviewing logs. You learned how to enable and configure remote desktop for users, including managing user sessions and security settings. You gained an understanding of how to configure VPN connections to securely connect remote users to the corporate network. We explored common networking tools like ping, tracert, and ENS-lookup for troubleshooting connectivity issues. You learned about partitioning, formatting, and managing disks on a Windows server, including configuring RAID and configuring virtual hard disks, VHDs. We covered strategies for backing up Windows servers using built-in tools like Windows Server Backup and how to restore data when necessary. You learned how to configure and manage Windows Update settings and implement WSUS, Windows Server Update Services, for centralized patch management. You understand the importance of patch management in securing the server environment and ensuring software stability. We covered tools like Performance Monitor, Task Manager, and Event Viewer for monitoring system health and performance. You learned how to manage resources like CPU, RAM, and disk space efficiently and configure alerts for system performance issues. You were introduced to PowerShell for automating administrative tasks and configuring servers efficiently. You learned how to use CMDLets for user management, file system tasks, and service configuration. You gained experience in writing simple PowerShell scripts to automate repetitive tasks. You learned the basics of creating and managing failover clusters to ensure service availability. We discussed the importance of having a disaster recovery plan, including backup strategies and maintaining high availability. This course focused heavily on practical skills. You've had opportunities to configure and troubleshoot various services, which will help you in real-world scenarios. We highlighted the importance of security throughout the course, including securing your servers, protecting data, and monitoring for any potential threats. PowerShell and automation practices are critical in Windows Server administration, making it easier to manage large-scale environments. Maintaining server health through regular monitoring, patching, and backups is essential for long-term system stability. Always keep an eye on new updates, features, and best practices for Windows Server. Consider pursuing certifications like the Microsoft Certified Windows Server Hybrid Administrator Associate, Exam AZ800, or the Microsoft Certified Windows Server Administrator, Exam AZ801. The more you work with Windows Server, the more you will become proficient in managing and troubleshooting it. Set up a home lab to experiment and hone your skills. Engage in online communities and forums for Windows Server admins to exchange tips and troubleshoot complex issues. By mastering these concepts, you'll be ready to manage and maintain Windows Server environments effectively, ensuring smooth operations and minimizing downtime. Good luck with your journey in Windows Server administration. Remember, hands-on practice is key. Stay updated, consider certifications, and engage with the community. With these skills, you're well equipped to excel in Windows Server administration. A network operating system, or NOS, is like a conductor of an orchestra, ensuring that all the instruments, our computers, and devices play in harmony. Unlike regular operating systems that focus on a single machine, a NOS connects multiple devices, allowing them to communicate seamlessly. Imagine sharing files, printers, and applications across a network without a hitch. It's all about collaboration. With the NOS, resources are efficiently managed, enabling users to access shared data and services from anywhere within the network. This creates a dynamic environment where teamwork thrives, whether in a small office or a large enterprise. So, when you think of a NOS, picture a powerful system that transforms isolated machines into a cohesive unit, making our digital lives more connected and productive. A network operating system, or NOS, is the conductor of an orchestra, ensuring that all the instruments, our computers and devices play in harmony. Resource sharing is a game changer in our digital world. With a network operating system, multiple computers can effortlessly share files, printers, and applications, making collaboration a breeze. Imagine working on a project where everyone has access to the same resources, all centralized for easy access. User management is another crucial aspect. Administrators can create user accounts, set permissions, and ensure that only authorized individuals access sensitive information. This level of control is vital for maintaining security. Speaking of security, NOS comes equipped with robust features like firewalls and encryption. These tools safeguard our data from unauthorized access, keeping our network safe and sound. And let's not forget about network services. With email, file transfers, and remote login capabilities, devices can connect and communicate seamlessly. Finally, centralized management allows system administrators to monitor and configure all network devices from one location, streamlining operations and enhancing efficiency. In a nutshell, a network operating system is essential for a secure, collaborative, and well-managed network environment. Resource sharing is a game changer in our digital world. With a network operating system, multiple computers can effortlessly share files, printers, and applications, making collaboration a breeze. Imagine working on a project where everyone has access to the same resources, all centralized for easy access. Welcome to the world of Windows Server administration. Today, we're diving straight into the essentials. First up, installation. Getting your server up and running is crucial. Once that's done, let's talk about Active Directory. This powerful feature allows you to manage users and resources efficiently, make it easier to keep everything organized. Next, we'll explore user management, creating, modifying, and deleting accounts to ensure your team has the right access. And don't forget about configuring roles. Whether you need a file server, web server, or application server, understanding these roles is key to optimizing your environment. By mastering these concepts, you'll be well on your way to confidently managing your own server setup. Like, share, subscribe. DaVinci channel. Let's get started.